Hello guys, so today we are going to discuss another sorting algorithm, that is bubble sort, right? So what bubble sort says that if you are given any unsorted sequence of integers, so what bubble sort algorithm will do, it will just try to bubble up the largest possible number in the whole unsorted sequence, right? So here you can see that currently in this unsorted sequence 5 is going to be the largest number. So what bubble sort will do, bubble sort will try to just place this largest number from the unsorted sequence to its best possible position, right? So it will just place it to the best possible position. So what bubble sort will ensure that after each iteration, whatever the unsorted part is left, we will just make sure that the maximum of that unsorted part is going towards its best possible position after every iteration, right? So it will just bubble up, it will just try to make sure that these integers are getting bubble up to the best possible positions in the sorted sequence, right? So let's see what is the basic intuition behind bubble sort, right? So suppose that you are given any unsorted sequence. Suppose you have an unsorted part from a sequence. Suppose this is A1, A2 till the position AM, and after that if you start from M plus 1, AM plus 2 till AN, which is a sorted part. So this is a sorted region and this is the unsorted region. So what we are going to do, we will just make sure that inside this sorted part, this is going to be the minimum element, right? Inside this sorted part, this is going to be the minimum element, and say inside this unsorted part we have some element x as the maximum element, right? So what we will try to ensure that after each iteration, whatever the division is, we will make sure that this minimum element of this sorted part is every time greater than the maximum element of this unsorted part, right? And what we are going to do at each iteration, we will just pick out this maximum element and put it to its best position. So if this maximum element is just smaller than this minimum element of the sorted part, then what will be the best possible position after the whole sequence is sorted for this maximum element? It will be just behind this AM plus 1 element. So we will try to just place x here, right? So at each iteration we will just divide our array into two parts. In the initial iterations, the whole array will be considered as the unsorted part and the size of the sorted part will be 0. And after the complete sorting algorithm has been executed, this sorted part will be equal to the size of the array and the size of the unsorted part will become equals to 0, right? So let us just see how a basic dry run and see that how we can just apply bubble sort in the following case, right? So suppose the array given to you is 5, 4, 3, 2, 1. So here you can see that this array is arranged in the descending order. So if it is 5, 4, 3, 2, 1, right? So at each iteration, what we are going to do, we will just keep a tracker I as well as a tracker J, right? We will just keep a tracker J. So now what we are ensuring that if the current element which I is pointing, if it is greater than the just next adjacent element, then we will just swap these two elements, right? So here you can see 5 and 4 will be swapped and 4 will come here, 5 will come here, right? Now I will be incremented. Let's say we are just keeping things on a simpler note by keeping just I as our variable. Now I is pointing to 5. Now I will be compared with I plus 1th index, and here you can see that 5 is greater than 3. So again we will just swap things from here to here. So here you can see this is 3 and this is 5. Now again 5 will be compared with 2, and here you can see it will again be swapped. So 2 will come here, 5 will come here. After that 5 will be swapped with 1. So this will be like this sequence, right? Now again we will just start I from the very 0th index, that is this one, and now here you can see when 4 and 3 will be compared, 4 will be greater than 3, so we will just swap 4 and 3, right? So 4 and 3 will be swapped and 3 will come here and 4 will come here. Again 4 and 2 will be swapped, so 2 will come here and 4 will be swapped to here, and again 4 and 1 will be swapped, so these two come here. So again here you can see that we just picked out 4 as the maximum element from the unsorted part, and we just placed 4 at its best position. So at each iteration at least one of the element is getting placed at its best possible position. Now if you compare 3, so here you can see we will start again from I is equals to 0. We will compare I with the next corresponding element. So here you can see 3 and 2 will be compared. So 2 will come here and 3 will come here. Again 3 and 1 will be swapped. So here you can see 3 and 1 are going to be swapped. So 1 comes here and 3 comes here. And now if we just compare 3 and 4, so no swapping will occur because 3 is lesser than 4. Now at last what will happen is we will just compare 2 and 1. So 1 will come here, 2 will come here. 2 is also present at its best position, and at last 1 is also present at its best position. So here you can see that we just at every iteration we were just bubbling up the maximum possible element from the unsorted sequence, and we just place this bubble to the sorted part, right? And at last the size of this sorted part will grow up till the size of the original array, right? So let us just see that how we can just implement this algorithm. So what we are supposed to do, we can just try to mimic the same algorithm in the code. Like we will just have one pointer which will be pointing to the first position, right? And what we can say is we can just have a variable which can just keep a track on the fact that if we are sometimes swapping an element or not, right? So here you can see when 5 was present here and 4 was present here, you can see that when we were just swapping both the elements, we know that swapping will occur only in those times when the some part of the array is unsorted, right? But if the whole array is already sorted, then obviously no swapping will occur. So we can just keep a variable that can just track the fact that if we are swapping some element or not. And if in the whole iteration, if we are not doing any kind of swapping, then obviously the whole sequence is sorted and there is no point of reiterating to the whole sequence again and again, right? So let us just try to think in this manner only. So we will just keep a track on a flag. That is, suppose we are keeping a flag track on the done flag. So initially what we can suppose is this done flag is marked as what? False, right? And what we can do is while this flag is false, right? While this flag is false, we will just try to implement the algorithm. Now what the algorithm will say, suppose at each iteration I will mark this flag as true, right? I will mark this flag as true, and if at any time any swapping will occur, I will just change the flag to false again and the loop will be implemented again, right? Now we will start from I is equals to 0, and what we can do is while I is less than n minus 1, right? We will just go till the last index and we will just check that if array at I is greater than array at I plus 1, then what we can do is we can just swap the element present at the ith index with the element present at the I plus 1th index. And as I said that if any one swapping is also occurring, then also we are at an unsorted sequence and we are supposed to sort the sequence. So we will just again mark this done variable as false, right? We will just mark this as false. We will just close this if loop, if conditional, and increment the value of I, right? So here you can see that as soon as we will just come at this while loop, we will just check that if we are greater than our adjacent element, and if that is the case, then we will just swap myself and just change the variable of the done flag, right? So here you can see that if the sequence is already sorted, suppose that sequence is like 1 2 3 4, so here you can see that the sequence is already sorted. We will start with the done variable as false. We will check that while not done, that is while the value of done is false, we will mark the value of done as true. So we will just mark the value of done as true, right? We will start the variable I is equals to 0. We will check that while I is less than n minus 1, we will check if I is greater than the adjacent element. So here you can see 1 is not greater than the adjacent element. So this if conditional will not be executed. I will be incremented. Now I will become equal to 1. So 2 will be compared to 3. Again, no if conditional check will execute. Now I will become 2. 3 is not greater than 4. 3 is lesser than 4. So again, this conditional will not be executed and we will just come out to the while loop. Now here you can see that after we just came out to the while loop, the value of this done variable is true. So if we will just try to reiterate in this corresponding while loop, then obviously this while loop will terminate. This while loop will terminate as soon as we have got our whole array as sorted. So what happens in the case of bubble sort is if the array is already sorted, right? So no swapping generally occurs and we can just in linear time check that the whole array is getting sorted. But in the worst case, what can happen is we can get an unsorted kind of sequence, and in this unsorted kind of sequence, every time we are starting from this very first index and going till the last index, right? We can even optimize this approach by not iterating till the last index. Why? Because we know that at the first iteration, the largest number will be present at its best possible position, that is last. After the second iteration, the second largest number will be present at its best position, that is second last, and so on. So we can just reduce the searching part, the searching space at every corresponding iteration. But let us say that in the worst case, we are just iterating to all the n sequences. So the number of iteration will lead to the complexity of big O of n square in asymptotic notation. While in the best case, this is going to be a linear kind of scenario. In the best case, the bubble sort algorithm will run in linear time, that is big O of n, right? So I hope the logic for the bubble sort algorithm is clear to you all. This is one of the very fundamental algorithm in sorting algorithms, and this will lay down the concepts of more sorting algorithm for you guys, right? So I hope you like the lecture, and if you have any suggestion, you can just put them down in the comment section. We will meet in the next video. So thank you guys. See you next time. Hello guys. So today we are going to discuss one of the very important sorting algorithm, that is selection sort, right? So let us just see what the selection sort algorithm say to sort an unsorted array. Suppose that this is the given unsorted array that we are supposed to sort. So what selection sort says is that at every iterations, what we are going to do is just divide the array into two parts such that one part will be completely sorted and one part will be unsorted. And at every iteration, what we are going to do, from the unsorted array, we are going to find the minimum element and we will place this minimum element at its best position. So let us see how to iterate over this array using the selection sort algorithm. So to implement the selection sort algorithm, what we will do, we will take help of 3 pointers. So let us just name it as I, and we will make one pointer j that will start from I plus 1th position. And we will also take a minimum index pointer, right? So at every iteration of I, what we will say is this minimum index element will be equal to the element pointed by the ith pointer, and then what we will do is just start our iteration in this particular subarray, and we will find that if there exists any element which is smaller than the element present at the minimum index, and as soon as we will be finding more elements which will be lesser than the element pointed by the minimum index, we will just update the minimum index. But for the time being, we will start the iteration saying that the minimum index element is the element pointed by the ith pointer. So here you can see the indexing will be 0, 1, 2, 3, 4, 5 and 6, right? So let's just start. So on the initial node, the I will be pointing to the 0th element and j will be pointing to the I plus 1th element, right? So as I earlier said, in every iteration I will say that the minimum index element is the element pointed by the ith index. So I will mark minimum index element as 0. Now what we will do, we will start the iteration of j from I plus 1th index to the n minus 1th index, and in this subarray we will find the element which is smaller than the element pointed by the minimum index. So now here you can see, is 2 less than the element pointed by the minimum index, which is 17? Yes. So what we will do is just update the value of the minimum index as 1, and what we will do is just increment the value of the j pointer, because there can be more elements which will be still smaller than the element pointed by the minimum index element. Now j is pointing to 1. So is the element pointed by the jth index smaller than the element pointed by the minimum index? And minimum index pointer is pointing to 2. So here you can see j is pointing to much lesser element. So we will again update the value of minimum index as 2. And again j will be incremented, right? So now j will be pointing here, and here you can see 9 is not less than 1 because 1 is pointed by the minimum index. So we will not update the value of the minimum index, and again j will be pointing here. So now here you can see 8 is also not less than the element pointed by the minimum index, which is 1. Again j will be incremented. So here you can see j is pointing to 7, and here you can see 7 is also not less than 1, and at last j will be pointing to 13. J will be pointing to 13, and again 13 is not less than 1. So we will stop the iteration of j, and now as soon as the loop of j will end, what we will have in our hand is the minimum index element and the element at the ith index. What we will do is just swap the elements present at the ith index and the element present at the minimum index element. So now after swapping, 1 will come here and 17 will come here, right? So here you can see we have just placed 1 at its best position. Now we will increment the value of I will be pointing here. Again a new fresh loop will start and minimum index will be initially pointing to the same element pointed by the ith index, that is 1, and we will start the jth pointer from I plus 1th index. Now we will compare, is the element pointed by the jth pointer is smaller than the element pointed by the minimum index? So no, j is not smaller than this, so we will just increment the value of j. Now j is pointing to 9. Is 9 less than the element pointed by the minimum index, that is 2. So 9 is not less than 2. Again j will be incremented. Here you can see 8 is also not less than 2. J will be incremented. 7 is also not less than 2. Again j will be incremented. And at last here you can see j is pointing to 13 and 13 is also not less than 2 because 2 is the element pointed by the minimum index. So we will just complete the loop, and here you can see we will again swap the values pointed by the ith pointer and the minimum index pointer, and here you can see the both are pointing to the same element, so the array will be remaining at its original position only, and we will increment the value of I. So here you can see we have also placed 2 at its best position. Now again minimum index will be equal to 2, I will be pointing to 2 and j will start from I plus 1. So again, is 9 less than 17 because 17 is pointed by the minimum index? So again yes, 9 is less than 17, so we will update the value of minimum index, that is 3. Now we will increment the value of j. So j is pointing to 8, minimum index is pointing to 9. Is 8 less than 9? Yes, 8 is less than 9. We will again update the value of minimum index as 4. Now j will be pointing to 7 and minimum index is pointing to 8. So is 7 less than 8? Yes, 7 is less than 8. So again we will update the value of minimum index as 5, and at last j will be pointing to 13, but 13 is not less than 7, so we will do nothing and the loop of j will be completed, and at last what we will do, we will swap the elements pointed by the ith pointer and the minimum index pointer. So here this will be swapped and 7 will come here and 17 will come here, right? So again the loop of I will be incremented. So I will come here, minimum index will start from 3, right, and j will come here, right? So again, is 8 less than 9? Yes, 8 is less than 9, minimum index will be 4. Now j will be pointing to 17. Is 17 less than 8? No, 17 is not less than 8, j will be incremented, and at last j will be at 13, so 13 is also not less than 8. So we have our minimum index pointer pointing at element 8 and I is pointing at 9, so we will swap these elements. So this will become 8 and this will become 9, right? So now I will come here, minimum index will start again from 4. Now j will start from 17. Is 17 less than 9? No, j will be incremented. Is 13 less than 9? No. So j will complete its loop, and again I and minimum index are pointing to the same element, so no swapping will occur. And even if we just swap the element will be at its original position only. So now I is pointing to element index 5, minimum index is also pointing to 5, and j will start from here. Now is 13 less than 17? Yes, 13 is less than 17. We will update the value of j, minimum index with the value of j, that is 6, and j's loop will be completed, and we will swap the element present at the 6th index and the 5th index. So 30 and 17 will be swapped, and here you can see we have completed the sorting of our array. So as soon as I reaches the n minus second index and completes its procedure, our whole array will be sorted, right? So let us write the pseudo code for the following algorithm. So the pseudo code will be pretty easy for this algorithm. What we will do is just start our loop of I from 0 and iterate I till I is less than n minus 1, that is the instance when I will reach the n minus second index, right? And we will increment the value of I. We will keep a minimum index pointer starting from the value of I at every iteration, and then we will start a loop of j starting from I plus 1. J will go up to j less than n and j plus plus. Then what we will do, we will compare that if array at minimum index is greater than array at j, we will update the value of minimum index. So here you can see minimum index will become equals to j, right? And as soon as the for loop of j will be completed, we will just swap the values of the ith index as well as the minimum index. So by following this particular algorithm, you will be able to implement the selection sort algorithm. So here you can see the selection sort algorithm is pretty easy to implement. And talking about the time complexity of the selection sort algorithm, so here you can see that starting from the very first index, we are initially making n-1 iterations, then n-2 iterations, and so on, right? Till the time when we will do just one iteration. So the sum of these terms will be n into n minus 1 by 2, and in asymptotic big O notation, this will lead to big O of n square time complexity, right? So selection sort has a very intuitive and a very simple algorithm, right? And it has a very important application also in modern computer science, because suppose that you have a lot of data in your hard disk, right? And you have to just sort that data. So here you can see the swapping procedure is occurring very lesser number of time as compared to the other algorithms of sorting. So the conditions where you have to minimize the number of swaps and still you have to just sort the array, selection sort can perform way better than other algorithms, right? So I hope the logic for the selection sort algorithm is clear to you all. So whenever there is a condition that as I explained in the earlier example, that there are a lot of data in your disk and you have to do some sorting kind of thing, so there is a condition that you have to minimize the swap, then selection sort algorithm can perform way better, right? So I hope you like the video, and we will be continuing our series on this sorting algorithm videos, and we will be uploading more videos on these algorithms, as well as if you have some specific topics that you wish that we should teach in our YouTube channel, so please comment down in the comment section, and if you like the video then please hit the like button. We will meet you in the next video. So thank you guys, see you next time.
Hey guys, so today we will understand how merge sort works. Merge sort. So guys, merge sort is one of the most classical sorting algorithms, and this is based on one of the most important paradigms of algorithm, and that paradigm is called as divide and conquer. Okay, divide and conquer. So first let us understand what divide and conquer is. So basically, let's say if I have got a problem 1, okay, whose size is say n, okay. So divide and conquer strategy is that you divide this problem into smaller problems, okay, in the problem into the problems of smaller size. So let's say I divided it into a problem of size n by 2 and another problem of size n by 2. Now, once let's say this subproblem somehow magically gets solved. Once this gets solved, I receive its solution, that is solution 1. Okay, this also somehow gets solved, so I receive its solution, that is solution 2. Once I have got solution 1 and solution 2, that means the divide part of divide and conquer is over. Okay, so now I can conquer these solutions and formulate the final solution. So that final part which leverages solution 1 of subproblem 1 and solution 2 of subproblem 2 and does something on top of it to get the final answer is called as conquer. Okay, so this is the very high level explanation of divide and conquer paradigm. Now let's try to correlate this divide and conquer paradigm with our merge sort, that how our merge sort leverages it. So let's say I have got an array of size n. So what I would do is I would break this array of size n into 2 subarrays of size n by 2. Okay, these are 2 subarrays of size n by 2, and let's say somehow this particular subarray gets sorted magically. Okay, so I receive the sorted version of this. Okay, now this also gets sorted magically. I receive the sorted version of this. So now finally I need to conquer the 2 sorted portions. This is sorted 1, this is sorted 2. So now somehow I need to conquer these two sorted portions such that I get the eventually sorted array of the larger problem. Okay, so how do I do that? This conquer thing with respect to merge sort is called as merge procedure. Okay, so what merge procedure does is it receives two sorted arrays and it merges them into final sorted array. Okay, so let us try to understand how merge procedure would actually operate. So if I have an array that contains 8, 7, 6, 5, 4, 3, 2, 1. Now let's say I divide it into two parts, 8, 7, 6 and 5, and the other part containing 4, 3, 2, 1. By the time this problem is solved, this portion has become, 5, 6, 7, 8, and this portion has become, by the time this has been solved, 1, 2, 3, 4. Now I need to perform a merge action. I need to perform a merge action so that this gets converted into 1, 2, 3, 4, 5, 6, 7, 8. So how do I do that? So let's learn about merge procedure. It takes in two sorted arrays. First sorted array is 5, 6, 7, 8, and the second sorted array is 1, 2, 3, 4. It takes two pointers I and j. Okay, both of them are initially pointing to the first element of both the subarrays, and it takes an auxiliary array of size equal to size 1 plus size 2, where size 1 is the size of this and size 2 is the size of this. So since there are 8 elements, I need 1, 2, 3, 4, 5, 6, 7. Okay, so these I and j pointers are positioned in a way that either of them qualifies to be the current element. So whichever is smaller qualifies to be the current element. So since this is the smaller, 1 comes here and I move this pointer. 2 is smaller than this, 2 comes here, I move this pointer. 3 is smaller than this, 3 comes here, I move this pointer. 4 is smaller than this, 4 comes here, I move this pointer. Now this array is over. The moment one of the sorted arrays is over and some elements are remaining in the other, that means all the remnants of that array are greater than all the elements that have been inserted till now. And since this is sorted in itself, it can be pushed as it is in this particular auxiliary array. So it's just a matter of putting them one by one over here. Okay, so I will do 5, 6, 7. So this is what the merge procedure is. The time complexity of this is order m plus n, where m is the size of first sorted array and n is the size of second sorted array, because you can see that every element is getting touched only once. Okay, every element is getting touched and pushed only once. So that is the reason. Now, in context of merge sort, let's try to understand how this merge procedure actually operates. So I will take an array, let's say that contains 8, 7, 6, 5, 4, 3, 2 and 1. So first what I do, I divide it into 8, 7, 6, 5 and 4, 3, 2, 1. I will merge once this problem and this problem has been solved. So first this problem will be solved, right? According to recursion, first this branch has to be solved, then only this would proceed. Now to solve this, again I break it into 8, 7 and 6, 5. And then I perform merge. Merge would be performed when this is sorted and this is also sorted. Now for this it gets broken into 8, into 7, and then merge would be triggered. Okay. Now see, the moment the two subarrays are of size 1 each, no further breaking down can happen. So this is the termination condition. The moment I have reached termination condition, what is termination condition? When both the subarrays are of size 1 each. So no further calls happen, merge happens. So merge happens, what would happen? That I take an auxiliary array of size 2, and as I described, I would get a sorted array 7, 8 in that auxiliary array, and then from that auxiliary array I can copy that contents back to here. So if I got merged auxiliary array like this, I copy this back in the original input. So now this has become 7, 8. So basically this problem has been solved. Similarly, same thing happens here. This gets broken to 6, to 5, and then merge kicks in. The moment merge kicks in, it merges them into an auxiliary array and copies the content back over here. So I get 5, I get 6. Now this merge would kick in because for this problem, the half of this has been solved and half of this has been solved. So the next thing is merge. So it merged this and this in an auxiliary array and it would give me 5, 6, 7, 8, which would be copied here and it would become 5, 6, 7, 8. Same thing that happened for this part would also happen for this part, and this would get converted to something like 1, 2, 3, 4. Once this is sorted, so the merge of this entire thing would happen and there would be an auxiliary array that would contain 1, 2, 3, 4, 5, 6, 7, 8. This entire thing would be copied here and I would get the eventually sorted array as 1, 2, 3, 4, 5, 6, 7 and 8. So this is how merge sort operates. So if I have to write the pseudo code for merge sort, it is simple. Merge sort would take in an array its start index and end index. Okay. As I told you, the termination condition is size 1. So I would make further calls only when the size is not 1. It is greater than 1. So if I is not equal to j, it indicates that there are more than one element. So in that case, first thing I do is I find the mid, which is I plus j upon 2. And then first I call the merge sort for the left portion, which is from I to m. Then I call the merge sort for right portion, which is from m plus 1 to j. Once this portion is sorted and this portion is sorted, I call merge of this sorted portion and this sorted portion, m plus 1 to j. So this is the pseudo code for merge sort. Merge procedure you can easily write on your own, where merge procedure would take in starting and ending of one sorted array, sorted subarray, and starting and ending of second sorted subarray, and merges them accordingly. So now let's discuss about the time complexity. So you can see that at every level the size is getting halved. So how many levels will be there? In the last level there is only one element, and since this is becoming n to n by 2, n by 4, n by 8 and so on, number of levels would be log of n raised to. And now in each level how many operations are happening? So in each level, in the last level, okay, in the last level there are n elements of size 1 each. Okay, in the second last level there are n by 2 elements of size 2 each. In the third last level there are n by 4 elements of size 4 each. So I can say that at each level number of elements are n into 1, that is n, n by 2 into 2, that is n, n by 4 into 4, that is n. So how many merges would happen? Number of merges would be equal to the number of elements. So in each level order n merge operations are happening, and since there are log n such levels, so overall time complexity would be order n log n. Let's also discuss about the space complexity. Since I told you I need an auxiliary array to temporarily merge and store the contents, okay, so what would be the size of that auxiliary array? That would be aux of size n, because at max there would be 2 subarrays of size n by 2, n by 2 each. To merge them I need an auxiliary array of size n. So that's it. That's about the time complexity and the space complexity. I hope you understood it. That's it. Thank you.
Merge sort is, if imagine you had to sort a deck of cards. One possible way, which is by the way also called divide and conquer, could be that I break down this deck of card to half deck of card and half deck of card. So I divide into 2 parts, right? Like half goes, let's say, to the left, half goes to the right. I sort those individually, right? So half deck of cards, I sort them somehow by some magic. And right side also I sort somehow by some magic. So now I have 2 sorted deck of cards, right? I have 2 sorted deck of cards. Now the problem becomes, if I have 2 sorted deck of cards, can I merge them? so that they still remain sorted. Imagine, let me give you an example, right? So let's say I have an array 2, 3, 5. Let's say I have another array 1, 6, 8. If I was given these two arrays, can I merge them into another array which is completely sorted? Is that possible or not? If that is possible, then this could become another algorithm, which is like whenever I need to sort an array, I can divide it into two parts, recursively sort them, and then I can merge them. So merge becomes the important step. The question is, I have given you a problem. You have two arrays, not necessarily of the same length. Let's say this is of size A, this is of size B. Can you create another array of size A plus B where all of the elements come from A or B and they're all sorted? Is the question clear? Like you have some A number of arrays in array A, you have B number of elements in array B. Array A and B are individually sorted. So A is a sorted array, B is also a sorted array. You have to merge them into another sorted array. How would you do that? Basically, if I have been given two numbers, let's say I have an array A, 2, 3, 5, and I have an array B, which is, let's say, 1, 4, 8. And I have to create a sorted array, right? Which is of size 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6, correct? This is the eventual sorted array I have to contain or create. One thing is, the first element in the sorted array is going to be the completely minimum of everything in the array, right? So given array A is sorted, minimum from array A is on position number 0, correct? Minimum from array B is also on position number 0. So therefore, whichever is the minimum of these two, I don't need to look at any other element. Whichever is the minimum of these two is going to be the first element in the sorted array. Is that something you all agree with? And what is the minimum of these two? Minimum of these two is 1. So 1 comes here. Now, if I have inserted 1 here, then it is as good as saying that now I remove 1 from B. It is the same thing, right? So what I just do is, how do I remove 1 from B? I just change this pointer to now point at this number 4. This is as good as saying that I'm now merging two arrays, one array which is A and one array which is B, but B is starting from this point onwards. And I again do the same thing. What is the next number that should come here? It should be the minimum of numbers here and minimum of numbers here. What is the minimum of numbers here? Array at this pointer. What is the minimum of numbers here? The array at this pointer. Whichever is smaller, which is 2, comes here, and this pointer moves one step forward. So in short, the approach becomes that you have two pointers. Let's say there's a pointer 1, which is for array A. There's a pointer 2, which is for array B. And you just say the following: while pointer 1 is less than whatever is the size of A, and pointer 2 is less than size of B, you do the following. You figure out which one is smaller. You just check. If A of pointer 1 is smaller than equal to B of pointer 2, then simple. This is what goes in the sorted array. So let's say sorted of, let's keep an index, A of pointer 1. You increment the pointer 1 plus plus because now pointer 1 has been assigned here. Else you put pointer 2 element here. So sorted of, again, index plus plus is equal to B, pointer 2 plus plus. The only thing is, when I'm done with this while loop, it is possible that all of the smaller elements are in one of the array. Imagine like this array was 1, 2, 3 here, and there were, let's say, 4, 5, 6 here. My pointer 1 will end up going here, and I'll end up breaking out where I've only filled in 1, 2, 3 in the sorted array. 4, 5, 6 is yet to be filled. So I'll have to check for that, which is at the end of this while loop, if whichever pointer is not done. So I just check while pointer 1 is less than size A, I just keep adding sorted of index plus plus is equal to A of pointer 1 plus plus. And very similarly, I do the same thing with pointer 2. While pointer 2 is less than size of B, same thing, sorted B of pointer 2 plus plus. Right. That will cause the merge to happen. Does this make sense? Right. Now, if that can happen, which means now if merging can happen, and what is the time complexity of this merge? Imagine I have two arrays of size n and n each, n plus n, right? Like, so it takes me order n time to merge. If in fact the array A was of size m, this was of size n, it takes me order of n plus n time, right? That means if I have a order n array to be sorted, if I divide it into two parts, I say that sort the first part separately, sort the second part separately. Once they are sorted, then merging them will take me order of n by 2 plus n by 2 time, which is order n time. So merging them will take me order n time. Now, how do I sort the first half of the array? I can do the same thing with the first half as well. I can say that even to sort the first half, again break it down into two parts, and then sort the first half, sort the second half, merge it. With the end condition being that once I have an array of only size 1, it is already sorted. How about I modify this and I say that I have 3 arrays that need to be merged, right? Imagine I have an array 2, 5, 10. Imagine there is another array 1, 8, 9. And imagine there's another array 3, 4, 12. Let's say there were 3 arrays, right? How would you merge these 3 arrays into one array, which has all elements are sorted? We can do 2 at a time, but we don't necessarily need to, right? Like we look at this, right? What is the first element going to be in the merged array? It is the smallest of all. Where does the smallest come from? It is either the first element from here, or the first element from here, or the first element from here. Whichever is the minimum from here, that becomes your smallest. So I can have 3 pointers. Pointer 1 pointing to the 0th element, pointer 2 here, pointer 3 here. Whichever is the smallest of these 3, which in this case is 1 comes here. And then all I do is I move this pointer 1 step to the right. And I again repeat the same thing. Whichever is the smallest of these 3, which is 2 comes here. And then 2's pointer moves 1 step to the right. Now again, 5, 8, 3, whichever is the smallest, 3 is the smallest, 3 comes here. And 3's pointer moves to the right. 5, 8, 4, 4 is the smallest, so 4 comes here. And its pointer moves to the right. 5, 8, 12, 5 is the smallest, so 5 comes here. And 5's pointer moves to the right. And then so forth, right? In the case of merge sort, it is only 2 arrays. An extension of the previous question. Then instead of 2, if there were 3 arrays, how do you go about merging 3 arrays? I mean, you can merge 2 arrays at a time. You can merge these 2 at a time, and then you end up merging these 2. But you'll end up using more memory, because to merge these 2, you'll need an additional array of size 6. Then you'll create an array of size 9. What I'm doing is I'm just directly creating an array of size 9 so that I reduce the amount of memory required to maintain that intermediate re-array. Also, I reduce a step. Okay, all right. Coming back to the merge sort. How does merge sort work? As the name suggests, it's divide and conquer, which is basically, now that I know that I have the superpower of taking 2 sorted arrays and merging them, what I can do is, given an array A, I sort the first half. So sort A to 0 to n by 2, sort A of n by 2 plus 1 to n, and then merge these guys. That can become my approach. And this, how do you sort the first half? This also can happen in the same way, where you again divide into 2 parts, 0 to n by 4, and then n by 4 to n by 2, and again, then you merge, etc., right? And if I have to write code for this, it becomes fairly simple, which is, let's say if the question was, how do you sort array A from index I to index j? If obviously like the size of the array is already 1, which means if j is equal to I, let's just put that, then your array is already sorted, so you can just directly return. If not, then what you do is you basically sort the first half, which is you say, I'll go from A of I to mid, where my mid is I plus j by 2. Then I'll sort A from mid plus 1 to j. And once these 2 guys are sorted, then I will need a temp array where I'll merge the array from I to mid and mid plus 1 to j. And then I'll make sure that A of I to j becomes equal to temp. I'll just do that. But basically, I'm just applying recursion here. And what I'm saying is, if you want me to solve, by the way, let's say there are 4 numbers, right? 5, 3, 2, 6. Let's say those were the 4 numbers. I say that first sort the first half. So let me call the function to solve these 2 numbers, 5 and 3. Somebody sort this and then give it to me. And then sort the second half separately. So somebody sort 2 and 6 and give it to me. And once I have them sorted, then I will actually merge them, right? Now to sort 5 and 3, I again do the same thing. I split it half. I say somebody sort 5 for me and somebody sort 3 for me. Here also, and somebody sort 2 for me and then 6 for me. Once they are sorted, then I'll merge. 5 is sorted, 3 is sorted. How do I merge? In my merge step, the same way we had seen, we have 2 arrays. We have to merge. When we merge, this will become 3, 5. And that is what I replace my original array with. So this array becomes 3 and 5. Very similarly, 2, 6 remains 2, 6. And then once I have 3, 5 and 2, 6, then I merge them to find 2 comes first, then comes 3, then comes 5, then comes 6. And this becomes my actual sorted array, which I replace this with. Just out of curiosity, why do we divide them into equal halves? Although in the end, we move 2 single elements and merge them in sorted order. Can't we take pairs in the array and do the same way of merging? Let's say I have more numbers, right? So imagine I had 5, 6, 8, 1, 2, 13, 15, 12, 3. How many do we have? We have 4. And let's imagine I remove 12 from here. Question is, if we have to sort anyway, why don't we take pairs by pairs, right? So let's just take pair 5, 6, 8, 1, 2, 13, 15, 3. And let's just first sort them. So we end up sorting them. And for example, we end up finding that this is 5, 6. This becomes 1, 8. This is 2, 13. And this becomes 3, 15. Right? Now, the problem is like we've done pairwise sorting, but the array is still not sorted. Then we'll have to do sorting of 4 elements each, right? How do we do that? We say that, you know what, like there are first 4 elements here. The first half is sorted. The second half is also sorted. Let's merge somehow, which again, I'll take another array and then I'll merge, etc. So this will get sorted. Then I'll do again the same thing, which is I take 4 elements, half is sorted, and I'll do the same thing. And then finally, I'll look at all of the 8 elements. So you're going just in the reverse order. What I just said, you're just going in the reverse order, which is also correct. It's just harder to code because the previous approach can be coded using recursion, which I'll just show. In your approach, what you're doing is you're building bottom up, right? Like you're sort of saying that let's first sort all pair of elements. Once they are sorted, then let's look at all 4 size elements. Great. Once they are done, then let's look at all 8 size chunks. Once they are done, then look at all 16 size chunks and then 32 size and then 64 and so forth. Right? And finally, I'll have the entire array sorted, which works. It's just harder to code. What I said was the other way around, that instead of going from 1 to 2 to 4 to 8 and so forth, let's start from n. Let's divide that into n by 2 parts, then n by 4, then n by 8. And I'll finally reach the 1 part anyway. And then my recursion function will keep returning and I'll have the eventual answer. So if you look here, my recursive function, this will do the same thing. My recursive function here will also do the same thing. Let me also just write it as merge step. So what is happening is, if I have an n-sized array, I'm dividing it into 2 arrays of size n by 2 each, n by 2 each. I'm sorting it using the same methodology, which is this n by 2 will create arrays of size n by 4, n by 4. Here also, again, same, n by 4, n by 4. These will create arrays of size n by 8, n by 8, again, n by 8, n by 8, same thing. And this n by 16, n by 16, and so forth. How many levels will you have here? I mean, we go from n to n by 2, n by 2 to n by 4, n by 8, 4 to n by 8, n by 8 to n by 16. How many levels? Log n levels, right? So in every level, n is becoming half of what it was. As we have seen the same pattern in binary search, etc., etc. I mean, as you go, if n is becoming half of what it was, it takes you log n steps to finally come to 1. At every step, what is happening? At every step, basically, I have n by 2 sorted array. I'm merging them, which takes me order n time. This takes me order n time. N by 2 plus n by 2 and order n. What happens on this level? These 2 guys merge and it takes them n by 4 plus n by 4, which is n by 2 time. These 2 guys merge and it takes them n by 2 times. If you add them up, it will take you order n time on this level as well. Very similarly, on the other level as well, where you have n by 8, there are 8 instances of n by 8. It will again take you order n time. So the total time taken on every level, it takes you order n time. There are log n levels. The total time taken is n log n. That is an intuitive way to understand. I can also explain the mathematical way of explaining this. But the intuitive way of understanding the time complexity of merge sort is that on every level, you're doing one merge. The merge is order n. Number of levels is log n. And therefore, in fact, if you look at Arvind's approach, if you were to implement it, In every iteration, what you're doing is you're first creating pairs and you're merging the pairs. Takes you order n time. Then you're looking at all four blocks, right? Like blocks of 4 each. In one order n operation, you will have sorted blocks of 4 each. Then in again one order n operation, you would have sorted blocks of 8 each. And you'll keep doing that till you cover the entire array. So the number of steps to cover the entire array would be log n, and every single iteration is an order n iteration. So it takes you an order of n log n. I can explain the math behind it as well. Is it n log n in every case? Best case is, sure, I mean, you can probably put an optimization there that if the array is already sorted, if a half is already sorted, you don't need to do all of the splitting, etc. So best case, you can still make order n. But yes, worst case is order n log n. Worst case, it takes you order n log n. And you can put a check to make sure that you're not doing the entire splitting, etc. if the array is already sorted. All right. What is the space complexity of merge sort? So if you look at the implementation here, we are allocating this additional memory temp to calculate this merged part, right? Why? Because when we are merging two sorted arrays, we need this temporary space where we put in the result, which is not a part of the original array. This is additional space. If I have to look at this tree, in this n by 2 part, I would have taken a temp array, which was of size n by 2. Here, I would have taken a temp array, which was of size n by 2. In fact, let's look at total space allocation, right? So this n by 2 will make a call to n by 4, 8, etc., etc. So this is a log n stack memory space. Plus, in each of these, so imagine I was sorting this array of size n. This will end up calling for n by 2. This will end up calling for n by 4, n by 8, and so forth. In each of this, I would have a temp array allocated, which will be freed as long as, I fill it back, right? So this temp array here is of size n by 4. As soon as I'm done, then this will be freed. Then I come back here. Here it will be of size, additional size of n by 2. As soon as I'm done, it will be freed. And then I'll come back here and I'll have a temp array additional size n. So maximum space that I end up using additional is I have log n stack of recursion, plus I have this additional order n size array that I might have used, which is my temp array. So order n extra space is what we end up using apart from the array space. So space complexity becomes order n. Time complexity becomes order of n log n. There's one more way to, by the way, calculate time complexity. If you assume that the time taken for sorting an array of size n is tn, then tn is nothing but, I'm saying first sort array, first half of the array, then sort second half of the array, which is also of size n by 2, and then merge them, which is it takes you some n time. Let's say it takes you n time. This is basically saying 2 times t n by 2 plus n, right? If you break it down further, your n by 2 is 2 times t n by 4 plus n by 2, which is the same as 4 times t n by 4 plus 2n, which you'll see will finally come to 2 to the power I t times n by 2 to the power I plus n into I. This is just a little mathematical. Therefore, I explain the intuitive way first, which if you want this to become equal to 1, I becomes log n. So you have n into t times 1 plus n into log n, which is n log n. This is how Master's theorem actually works. I'm just elaborating that, expanding that equation. Even if you don't know about Master's theorem, that is fine, as long as you understand the intuition of why it is n log n. Because in the recursion tree, there are log n levels. On every level, I'm using order n time. So time complexity becomes order of n log n. Space complexity becomes order of n. Is there any way without using the extra space? So actually merging two sorted arrays without using extra space in order n is not possible. That becomes the blocker, right? So if you can merge the array in place without using extra memory, then your problem would have been sorted. But the problem is merging without extra memory is the issue. All right, does this make sense? Merge, sort, space complexity, time complexity, all of that. All right.
If you like the video, please do not forget to like, comment and share this video with all your friends. Also, subscribe to our channel to get notified about the new upcoming videos.
Hello everyone. If you want to learn binary search from the scratch, this is the perfect video for you. In this 3-hour Snyder cut, we will explain you what is binary search, intuition behind binary search, the code, and the time complexity. After that, we'll jump into problems. First set of problems, given a sorted array, apply binary search. Second set of problems, array is not sorted, but you still have to apply binary search. Third set of problems, nothing is given. You have to build your own search space and then apply binary search. Finally, under which scenarios we can apply binary search. All these things will be covered in this 3-hour Snyder cut. So watch, learn, have fun. Thank you.
So hello everyone. So the topic for today is going to be searching, right? So we are going to look at different searching algorithms. We will start with linear search, and then we will move on to binary search. We will look at ternary search, and we will solve some problems related to binary search. Okay. Now, as always, after the class, we will have an assignment for you guys. So after every class, you are given an assignment so that you can actually apply what you have learned in the class and solve problems so that you can solidify the concepts. The link for the problem set will be in the video description. Apart from that, there will also be a link for a chat forum so that you can talk to your peers and discuss any issues that you face while solving problems. So that is for today. There is one more announcement that I would like to make, which is that a lot of students come to us and they say that, hey, I need help with interviewing. Right, so they tell us that they somehow get nervous during interviews, and a lot of students say that when I'm doing competitive coding online, I am able to solve problems, but when I'm in a face-to-face interview, I somehow get nervous, or I'm not sure what the correct approach or what correct approach should I take while solving the problem in an interview. So to handle that, we have organized a mock interview for you guys today. Right? So suppose that you wanted to see how an ICPC World finalist, right, someone who is very strong at data structures and algorithms, how such a person would behave, would approach a problem in a Google interview. All right, without further ado, let us dive into today's lecture. So let me just share my screen. All right, I hope that this is visible to everyone. Can someone just confirm these? Perfect. All right, let's begin. So I assume that most of you would be familiar with some sort of searching, right? Suppose that you have a collection. Suppose that you have a haystack. And you are looking for something in this haystack, right? Suppose a needle. Then how do you usually search? Well, the way we usually search is we pick each item one by one. Pick each item one by one. One by one, and we inspect it. Right? We see if this is the correct item, if this is the item that we are looking for. Now, this can be very, very time consuming, right? So just to prove this point, let us play a very simple game. Okay? So I want you all to play this game. So I have a number in my mind, right? And I'm telling you that the number is between 0 to 1000. Okay. Now, what you're supposed to do is you're supposed to guess what the number in my mind is. I'm not telling you the number right away. So you're supposed to make guesses between 0 and 1000. So if you could please start spamming in the chat, just tell me your guesses in the chat. And whenever I see the number that I'm guessing, that is in my mind, I'll let you guys know. All right, so can you guys please start? I have a number between 0 to 1000 in my mind, and you have to guess that number. So start placing in the chat. What do you think the number is? You have no other information. 786, not really. That is not what I had in my mind. Okay, I got 52, 30, 91, 900, 100, 99. No, none of those. A lot of zeros, some 500, some 304, 300, 666, 120, 76, 2. None of these. 50, no, 3, 404, 545. None of these. None of these. Please give some hint. So Tushar has a very important thing over here. Tushar says, if you could give us something, then we will be able to approach that particular solution much faster, perhaps. Right? So we see that if you have no information, right? If you have no information about how to search, then your best chance is to randomly check, randomly guess, right? Or if you don't want to randomly guess, your best chance is to basically check each possibility, right? So it could happen that first you say that, okay, you are guessing the number 1, then you move on to number 2, then you move on to number 3, and you keep doing that, you keep making guesses till I say that, yes, your guess is correct, right? So this is an example of something called linear search. Why linear? Why linear? Because you are going over each item linearly, right? Basically, you're going over each item once. So this is called linear search. And let us suppose that you have n elements, and you're looking for some value, right? You're looking for some key in this set of n elements. Then how much time will linear search take us? So what is the time complexity of linear search? It is order of n time, right? And while we are at it, let us also quickly discuss the space complexity. So how much space does it take to do a linear search? Well, this is just order of 1, right? Because we don't really have to store a lot of memory. We can just use a couple of temporary variables and perform the linear search. All right. So I assume that everyone is familiar with this linear search. So linear search is very inefficient. Now the question comes, can we search faster? Can we search faster? Right? What do you think the answer to this is? So this is the question. Now I'm asking you, what do you think the answer will be? Now, as most things in life, the answer is it depends, right? It depends. Well, it depends on what? It depends on, is there some pattern in the data that we can exploit, right? If we have some pattern in the data that we can exploit, then perhaps we could search faster. Does that make sense? For example, let us play this game once again. Right? Let us play this game once again. I am going to guess, I'm going to have a number from 0 to 1000 in my mind. And you are supposed to guess that number once again. However, this time, whenever you make a guess, I'm going to tell you if your guess is too high or if your guess is too low. All right? Cool. So let us begin once again. I have a number in my mind. And could you start guessing, please? So Mudasir says 2. Well, 2 is too low. Then Mudasir has guessed 34. 34 is too low, once again. Then the next guess is 123. It is too low. The next guess is 233. That is too high. Sahil says 500. That is too high. All right. Keep them coming. Keep the guesses coming. The next guess is 150. This is too high. Then, what is your next guess going to be? So 188. No, 188 is still too high. 200 is still too high. 10 is way too low. Yes. So 130. 130 is too low. And then what do we have? All right. So 130 is too low. Can you make more guesses now? 143, right? Someone guessed 143, and that is exactly the value that I was thinking of, right? This was my guess. This is correct. All right. So we see it took us some time. Right? It took us some time. It was not that we were able to guess the answer immediately. However, we were able to hone in on the answer. Right? So you know of homing missiles, right? The homing missile doesn't really know where the target is, but as it moves forward, it will get closer and closer to the target. Right? That is what we were able to. We were able to home in, right? Home in on the answer. Why were we able to do that? Because there was some pattern in the data that we could exploit. The pattern was that we were able to figure out whether our guess was too low or whether our guess was too high. Right? Now, a lot of students think they have this misconception that some sort of a binary search, right? Binary search can only be applied when the data is sorted. And that is not the case. The data need not be perfectly sorted for you to be able to apply binary search. Right? So what we are looking for in the data is we are looking for some pattern or some sort of ordering. Okay? So let us define some nomenclature over here. Let us define some theoretical nomenclature over here so that we can make concrete progress over what binary search is. All right? So suppose that you have some search space. And let us represent the search space like this. In the search space, this search space is basically a set of possibilities, of possible answers. Right? So there's one answer possible over here. So this is another possible answer, this is another possible answer perhaps, another possible answer, and so on. What binary search says is that when you make a guess, let us suppose that you made this as the guess. When you make a guess, if you are able to eliminate a large fraction of your search space, then you can search efficiently. If this is the case, then you can search efficiently. Right? Let's see how. So let us look at the previous game that we played. In the previous game, whenever you came up with an answer, right? Let us say that you came up with an answer that, hey, the guess is 200. Then all I told you was whether the guess was correct or not. Right? All I told you was whether the guess was correct or not. And that basically allowed you to eliminate this possibility itself. Right? So you made a guess 200. I told you it is not correct. So you can eliminate this possibility. Can you eliminate any other number? Did you get information about any other number? You did not. Right? On the other hand, in the second version of the game, suppose you guessed 200 and I told you that it was too high, then you could have eliminated every number. You could have eliminated all these numbers that were greater than 200. And your search space would only remain with the numbers that are less than 200. Right? Does that make sense? Yes? So this is something that we will try to exploit in binary search. So basically, binary search can be applied whenever you can remove, right? Remove or prune a large chunk of your data, of your search space with every guess. All right? Cool. So let us look at a more concrete example of this. So mostly when we are talking about searches, the first thing that would come to our mind is that we have an array. Right? We have an array. Suppose we have an array of integers. Right? This array has multiple values. Let us say that the size of this array of size n. Right? The size of this array is n. And we are supposed to search for a particular value in them. So given an array, what type of things are we able to binary search over? So whenever we try to binary search, we try to come up with a proposition. Does everyone understand what a proposition is? Yes? A proposition is something that takes two values, any of two values, right? A proposition can either be true or it can be false. Right? A proposition can either be true or it can be false. Now, if you can come up with a proposition, such that your array starts looking something like this. That for this particular element, the proposition is true. For this element, the proposition is true. For this element, the proposition is true, and so on. At some point, the proposition starts becoming false. Right? If you are able to come up with a proposition that can make your array look like this, then you are able to perform binary search on this array. And what will that binary search give you? That binary search will give you this boundary point. That binary search will give you this point where the proposition flips. All right, is that clear? So we will look at a little more concrete examples of these. Cool. So let us once again go back to this game of guessing the number. Right? Let us suppose that I gave you an array from 0, 1, 2, all the way till 1000. Right? All the way till 1000. And I had a guess. Let us say my guess was this number G. The correct answer was this number G. Now, what is my proposition over here? What is my proposition over here? So what is the proposition that makes sure that everything to the left of G is true and everything to the right of G is false? Can someone tell me that? So what proposition should I make so that every number to the left of G should result in false, while every number to the right of G should return in true? Exactly. So the proposition can be as simple as, is A of I less than G? Right? Is A of I less than equal to G? Right? What happens in that case? So if G is my guess over here, then every value to the left of it, yes, it is less than equal to G. So all these values will be true. All these values will be true. On the other hand, on the right hand side, all these values will be false because they will be, if the array is sorted, all these values will be false because they will be larger than G. So if I'm able to come up with this proposition, then binary search will allow me to find this junction. It will allow me to find this point where the true flips from true to false. Is that clear? All right. And now we have basically come up with the final definition of binary search. Right? Binary search does not require you to have a sorted array. Right? That is a misconception, that you need to have a sorted array to perform binary search. What you really need is you need this proposition. If for any search space you can come up with such a proposition, then you can apply binary search on that search space, right? Irrespective of whether that search space is sorted or not. All right. Perfect. So let us dive into some more concrete things, and let us try to look at the implementation of binary search. Right. So once again, suppose that we have been given an array, right, of size n, and this array is of integers. Right? And we are also given a key, suppose k, that we are looking for. And for now, let us suppose that the array is sorted in ascending order. Right? Then what we have to do is we have to search the element. We have to find the index of k in this array, if it exists. Right? If it exists in the array, then we are supposed to find the index and return the index. Otherwise, what we are supposed to do is we are supposed to return the index where k should be inserted. K should be inserted in the array. Is that clear? Yes, is that clear? So once again, suppose that we have an array that looks like this: 0, 3, 7, 12, 15, 16, 20, right? And I give you the key, let us suppose 12. Right? So in this case, what are you supposed to return? So let me give the index as well. This is 0, 1, 2, 3, 4, 5, 6. So in this case, what are we supposed to return? If this is the array and this is the key, then what value will we return over here? The answer we are supposed to return over here is the index 3, right? Because 12 is at the index 3, right? On the other hand, if I ask you to find the value, let us say k equals to 17, right? If I ask you to find the value k equals to 17, then what are you supposed to return? So there are multiple variants, right? In some cases, I might ask you to return -1 because 17 is not present in this array. I might ask you to return -1, but that is what we are looking for over here. We are saying that if the value is not present in the array, then tell me the index where that value should be inserted. Right? So if 17 was inserted in this array, then what value, what index should it be inserted at? Should it be inserted at this location? Should it be inserted at this location? No, it should not be, right? Because 16 is less than 17. It should be inserted at 20's position, and 20 should be shifted to the right. Yes, 17. If 17 was inserted, 17 would come in the 6th position, and 20 will be moved to the right. Right? So if the search key is 70, then you are supposed to give me back the answer index equals to 6. Is that clear? Right? So this is the classic problem of binary search. We have been given an array. We have been given an array which is sorted, and we have been given a key, and we have to search this key within the array. Right? Now let us first look at the implementation of how we would do this binary search, and then we will discuss the time complexity, right, and the corresponding analysis. All right. So let us start with this thing. So suppose that we have this function int binary search, right? And in this we are receiving a vector, right? We are receiving a vector. So we can say that, okay, we have an vector AR, vector of int AR, right? Apart from that, we also have the key. So we have an int. So this is not a semicolon, this is a comma. We have an int key. All right. This is the function that we are going to write. Yes, Shubrata, yes, in this case, we are accepting a sorted array. All right. We will come to binary searching over non-sorted arrays in some time. We are starting with the most simple thing, that the array is sorted. All right. Cool. So how would we write this particular piece of code? So when binary searching, there are certain things that we would like to identify. There are certain things that we would like to identify. If we are going to search, then the first thing that we need to identify is our search space, right? Is our search space. Now, if we have an array, then what do you think the search space is going to be? If we have an array, then what is the search space? Well, the search space is all the possible different indexes in the array, right? The value could be at index 0, the value could be at index 1, and so on till the last index. So the search space is the indices of the array. Well, what is the minimum value of that search space and what is the maximum value of that search space? So can we somehow draw a boundary? Can we draw a boundary around that search space? Yes, right? So in this case, the boundary is from 0 all the way till n minus 1, where n is the length of my array. Is that clear? All right. So when I'm defining the boundary, I will basically wrap my search space around this within this boundary. So I will say that, okay, let us suppose that we have some low, right? And that is the minimum possible value in my search space. And I also have some high. And that is the maximum possible value in my search space. And I can write over here that n is perhaps n equals to ar.size. All right. Cool. Now that we have the boundary, we are supposed to perform the binary search. Okay. So this was the first step of binary search. The first step of binary search was to bound or to establish the boundary of the search space, right? The second thing, once you have established the boundary, the second thing is to make a guess. So how do we make a guess? let us suppose that we have some search space and we want to make a guess. What guess do you think we should make? What guess do you think we should make? So we can make any guess, right? We can make any guess. However, we should try to make a guess that allows us to eliminate a very, very large chunk of the search space, right? Does that make sense? So if I have this array, and this is sorted, right? And this is my low, and this is my high, right? If I make this guess, if I make a guess over here, then what will I be able to eliminate? What will I be able to eliminate? I will either be able to eliminate this part, or I will be able to eliminate this part. Yes, I will either be able to eliminate this left half if my guess was too high, right? Or I will be able to eliminate this right half entirely if my guess was too low. Now, what is these values? What are these values over here? What are these values over here? Let us say that this is x, then this will be n minus x, right? Now the question is, in the worst case, right? If I'm very, very unlucky, then my guess will be on this side, right? I will be able to eliminate a smaller value. I will not be lucky. I will not be able to eliminate a very large value, right? So I should try to make it so that x is as large as possible, right? Both x and n minus x are as large as possible, right? So that no matter whether I'm lucky or not, I'm able to eliminate a large chunk of my search space, right? So what guess should we make over here? We should perhaps guess the middle element. We should perhaps be guessing the middle element. Is that clear? Right? So this is the second thing. Once we have decided the search space, once we have the low and the high, now we are supposed to find a mid, right? So we will guess a mid. So we will say int mid equals to low plus high by 2, right? And notice that this is integer division, right? This is integer division. All right, cool. So is this part clear? Is this part clear? That we calculate the mid. All right. Once we have the mid, then what do we do? Once we have the mid, then what do we do? The third step is to check the proposition. Check the proposition and prune, right? And prune our search space. Right? We have to check the proposition and prune our search space. Now, the proposition can be either true or false. Right? The proposition can be either true or false. However, in most of the cases, we can have 3 values. Right? We can have 3 values. Either my guess is too high, or my guess is too low, or my guess is exactly correct. Right? So let us look in this case. Let us look at that in this case. So what possibilities can I have over here? What possibilities can I have over here? If AR of mid is less than the value I'm looking for, is less than the key. If AR of mid is less than the key, then what does that mean? Is my guess too high or is my guess too low? If the location that I'm looking at the location mid. If the element at that location was less than the key, then is my guess too high or is my guess too low? Well, the element was less than the element I was looking for. So I am sure that since the array is sorted, any value that is at AR of, let's say, 0 or AR of mid minus 1, right? Mid minus 1, all these different values are going to be less than the key as well, because the array is sorted. So my guess was too low, right? My guess was too low. So what should we do? We should adjust something, right? We should adjust the search space. How should we adjust the search space? We can say that low equals to mid plus 1, right? Mid plus 1. Right? So basically, earlier, this was the search space, this was low, and this was high. Right? I made the guess at mid. I made the guess at mid, and I found out that this guess was too low. Right? This guess was too low. So what should I do? I should shift this low. I should shift this low to the element just right of it. Right? So this element should now be low. And basically by doing that, I am eliminating all these different possibilities. Right? I am eliminating all these different possibilities. Is that clear? So we should move up the low. Is that clear? We should increase the low. All right, so that is one case. So what other cases can we have? What other cases can we have? Else if AR of mid was greater than key, right? If AR of mid was greater than the value I'm looking for, then what happens? Then my guess is too high. And by the same argument, now I need to decrease the high. Right? And now I need to say high equals to mid minus 1. Right? Otherwise, if even that is not the case, then what possibility remains? If it is neither too high, if it is neither too high nor too low, then what possibility remains? Then it must be exactly correct. Right? Else my guess was exactly right. Right? I guessed the perfect answer. So in that case, I can just return the index. Right? Because I looked at this particular index, AR of mid, I looked at this particular index and I found a value that was exactly equal to the key. Right? It was neither greater than key, it was not less than key, so it must be exactly equal to the key. So I can just return this index because this is the index that I am looking for. Is that clear? Yes? Perfect. Now let us look at the code that we have and let us see if there is something missing over here. Right? Let us see if there is something missing over here. So once again, in the code, what we are doing is we are saying let us initialize a search space. Initialize space, right? Then we make a guess. So this is our guess. And based on the guess, we adjust the search space. So will we be able to, after one adjustment, will we be able to reach the answer? Will we be able to reach the answer after just one adjustment? No. Right? We have to continuously adjust our guess. Right? So we have to do this entire thing again and again. We have to repeat this. Right? We have to repeat this entire thing. So how should we repeat this entire thing? Let us put it inside a loop. Let us put it inside a loop. So let me add some space over here. And let me say, right, let me say, I will loop. Let us say I loop forever, right? While some condition. So I don't really know what this condition is, but as long as this condition is true, I will keep looping. Right? I will keep looping till this condition is true. Is that clear? Right? So we could have done several things over here. We could have called this function recursively as well. Right? Based on the adjusted guess, we could have called this function recursively as well. But recursion will have a lot of different issues with itself. So it will use a lot of memory because it will use the recursion stack. So let us not do that. Let us go with the iterative approach. Right? So once we have made a guess, and we check the guess, after we check the guess, we will adjust our search space. Right? Now once we have adjusted the search space, what do we have to do again? We have to make the guess again. Right? We have to make the guess again and again. But till what time should we continue this? Till what time should we continue this? Should we continue this forever and ever? Should we continue this forever and ever? No, we should only continue this as long as our search space has elements in it. Right? If our search space has elements in it. So basically, if our search space is empty, then it does not make sense to keep looking inside that search space. Right? If our search space is empty already, then it does not make sense to keep looking inside that search space. So when will our search space be empty? Right? When will our search space be empty? Let us suppose that this is my array. This is the low and this is the high. At what point would I say, for what values of low and high would I say that my search space, that this particular area, this particular range over here, this is empty? When will I say that? What happens when low equals to high? When low and high are the same. What happens when low and high are the same? Well, then my search space is not empty. Then my search space has one element, which is a of low. Right? If low equals to high, then my search space has one element, which is a of low. So when will my search space be empty? When low will be greater than high. Yes. As soon as this happens, as soon as this is my low and this is my high, right? Then I'm saying that the search space is everything that starts from low and goes till high. Well, it cannot go till high, right? My search space is empty now. Is that clear? So I am supposed to continue this loop till my search space is not empty, right? So what will be the opposite condition over here? What will be the opposite condition over here? So if this tells me that the search space is empty, then how do I check if the search space is not empty? I will check it by saying while low is less than or equal to high. Is that clear? Yes? Right? And this is very important, right? If you miss this equal to, you might get an incorrect answer, right? Or if you do something else, you might run into an infinite loop. So it is very crucial that we have this condition right, because this condition tells us when to terminate. It tells us when our search space is empty. Okay? And I mean, a lot of the times people are worried that, okay, I don't really know how to determine what condition should go over here. So here's the trick once again. To determine what condition should go over here, you have to ask yourself, when will my search space be empty? When will my space be empty? Right? And based on that, you will be able to come up with a condition. All right? Cool. So this is basically the code of binary search. We started with a search space. Repeatedly, while the search space was not empty, we made a guess and we adjusted that guess. Right? If our guess was perfect, we simply returned that guess. But what if we did not find that element? What will happen then? What if we did not find that element at all? What will happen then? Well, then we will keep on looping. Till the point our search space becomes empty. Right? Till the point our search space becomes empty. So what will happen is we will not be able to return over here. However, we will come out of this while loop. Right? So we will come out of this while loop. We will be over here at this point. And what values of low and high will we have? We will have a value such that low will be equal to high plus 1. Right? That is when our search ends. Right? And what is this location? Can you tell me what this location is? This location is exactly the location where I should insert this element. If I were to insert this element, this is exactly the location where I should insert this element. So when I am at this point, just give me a second. When I am at this point, I know two things. The first thing I know is that low is the index. Is the index where I should insert it. Where I should insert key. If I was going to insert it, then low is the location where I should insert it. Second thing I know is key was not found in my array. Key was not present in my array. Right? Is that clear? Now, once again, if we were to simply find the index of the, if we were supposed to find the index of the key and return -1, if the key was not present, then over here we will return -1. Right? Then over here we will return -1. Right? On the other hand, more practically, whenever you see a library implementation, we don't usually return -1. Instead, we return the index where I should have inserted the key. Right? So over here we can also return the low. Return the low value, right? Because this is the location where I should have inserted the key. Is that clear, guys? Yes. Now, one common question is, if you are returning -1, then your caller knows. That the element was not present, right? Because hey, index cannot be -1. Index of a particular value in an array cannot be -1. Indexes start from 0, right? So in this case, my caller knows that the element was not present. But what if I return low? What if I, instead of returning -1, what if I return low? How will the caller find out if the element was present or not? Yes, the caller has to be able to make that distinction, whether the element was present or not. So how will the caller get to that? Well, the caller can check. The caller can simply check. So it will say that, okay, index equals to binary search, the array and the key, right? And the person can check, the caller can check if AR of index equals to key, right? If AR of index equals to key, then we found the key, right? Then we found key at index, right? Otherwise, it means that we did not find the key, but this index is the location at which we are going to insert it. If we were to insert it, so we can say did not find the key, but if we were to insert it, it should be inserted at index. Is that clear? So the caller will have to make this additional check. Is that clear, guys? Yes? Okay. So Rohit has a question over here. Rohit says, what should we return? What should we return if key is less than AR of 0? Right? That's a very good question. So suppose that we have this array. This is the index 0, this is the index 1, and so on. Right? Let us say this value is 10, this value is 11, this value is 12. And let us say my key was 9. Right? Or let us say my key was 5. So first of all, is my key in the array? Is my key in the array? No, it is not in the array, right? Not present. Not present. If I were to insert this value, where should this key go? If I were to insert this value in the array, where should this key go? Can the key go at location -1? No, right? There is no index -1 in the array. So where should this key go? This key should go at index 0. The 5 should be inserted over here, and everything in the array should be shifted to the right. It's shifted 1 to the right. Does that make sense? So over here, our binary search, when I search for key equals to 5, my binary search should return the value 0, right? It should return the index 0. And that is exactly what our code will do. All right, that is exactly what our code will do. Is that clear? Okay. So let us move on. So I hope that the code and the implementation of binary search is clear to everyone. Now let us look at some improvements that we can make on our code. So one of the most important improvements is that we never try to calculate. We never try to calculate the mid like this, right? And you might have seen this a lot of times. People do the following. People instead of saying int mid equals to low plus high by 2, right? They do something else. They say int mid equals to low plus high minus low plus high minus low by 2, right? So can someone tell me the difference between these two? Can someone tell me the difference between these two? Why do some people do it this way? Why do some people do it this way? Well, let us try to look at the mathematics, right? Let us try to look at it mathematically. So if I have low plus high by 2, right? This is one thing. On the other hand, I can have low plus high minus low by 2. And let us see that if there is a difference between these two. Let us see if there is a difference between these two. So what I can do is I can take the denominator 2 common over here. So what will happen? The numerator, this will become 2l plus h minus l. Right? This will become 2l plus h minus l. What is that? That is simply so one l will cancel out. This will simply be low plus h. Right? This will simply be low plus h. So we see that the left hand side and the right hand side are equivalent. Right? From a mathematical point of view, they are equivalent. So what really gives? Why do people do this? This is more complicated, right? The reason why people do this is, even though they are mathematically equivalent, when we are dealing with computers, we can run into an overflow, right? When we are doing addition, we can run into an overflow. For example, let us suppose that our integer can only store. So let's suppose that the largest value our integer can store is, let us say, 10 to the power 9, right? Let's say 1 billion. Okay. Let us say that our low is 5 into 10 to the power 8. Okay, so our low is 500,000. Let us say that our high is 8 into 10 to the power 8, right, which is 800,000. Right? If I have something like this, what will happen when I try to calculate the mid? What will happen when I try to calculate the mid? I will be doing 5 into 10 to the power 8 plus 8 into 10 to the power 8. Right? This will be low plus high, and then I will divide it by 2. Yes, then I will divide it by 2. But what will happen over here? When I try to add these values, this will be 13 times 10 to the power 8. Right? And we just saw that 13 into 10 to the power 8, this cannot fit in my integer. My integer can only be up till 10 to the power 9. This is greater than 10 to the power 9. Right? This is what? This is 1.3 times 10 to the power 9. Right? So this value over here, this will overflow. This will overflow. And the value that I will get over here will be garbage. Right? It will give me a wrong answer. And then I divide the wrong answer by 2, I will eventually get a wrong value of mid. Is that clear? Yes. On the other hand, if I do it the other way, if I say low plus high minus low by 2, right? If I do it this way, then what happens? Then this will be 5 into 10 to the power 8 plus 8 into 10 to the power 8 minus 5 into 10 to the power 8 by 2. Right? And is this operation going to overflow? No, I'm subtracting things. Right? I'm subtracting things. The answer over here will be less. Right? The answer over here will be less than this value. Yes. So what do I get over here? I get 5 into 10 to the power 8 plus 3 into 10 to the power 8 by 2. Right? And then I can, then this will give me the correct answer, 6.5 into 10 to the power 8. Is that clear? This will not overflow. This will not overflow. Whereas this approach will overflow. Is that clear? This approach will overflow. All right. So Amit over here says that, hey, we can just use a different data type. Right? If we are dealing with an integer, maybe we can switch to a long data type. Right? But I mean, what if you were using a long? Right? Amit, the problem is, what if you were using a long? What would you do then? So in general, it is a good idea to implement the mid calculation via this particular approach. Okay. All right. So that is the improvement we are going to make over here very quickly. We are going to go to our code of binary search. We are going to remove this and we are going to improve it. We are going to say int mid equals to low plus high minus low by 2. All right. Perfect. Okay. I hope that everything is clear till now. Now let us try to analyze the time complexity of binary search. All right. Let us try to analyze the time complexity of binary search. Time complexity. All right. So how do we talk about the time complexity of binary search? So what is really happening is, initially I have the search space of size n. Right? Initially I have the search space of size n, and I guess the midpoint. Right, as my guess. Right? If my guess is too low, then I'm able to remove these elements. Right? I'm able to remove these elements. How many elements was I able to remove? So if this is 0, this is mid, and this is n, then after one guess, if my guess was too low, then how many elements was I able to remove? I was able to remove n plus 1 by 2 elements. Right? Yes or no? On the other hand, if my guess was too small, then I would be able to remove all these different elements. Right? Everything from mid all the way till n minus 1. Right? Even then, I was able to remove n plus 1 by 2 elements. Right? I was able to remove n plus 1 by 2 elements. So what really happens is, every time I make a guess, I'm reducing the search space by half. Right? I'm halving the search space with every guess. Right? So suppose we started with this guess n. Right? We started the search space of n. After one guess, I will have a search space of n by 2. After one more guess, I will have a search space of n by 4. One more guess, I will have a search space of n by 8. Right? And when will I end? So finally, this search space will reduce down. This search space will reduce down to just one element. Right? This search space will reduce down to just one element. Is that clear? So the question is, how many guesses did it take? So it took me one guess over here. It took me one guess over here, one guess over here, one guess over here, and so on and so forth. So how many guesses? How many guesses did it take? Right? How many guesses did it take? So no, guys, it did not take me n plus n by 2 plus n by 4 all the way till 1. No, this is not how many guesses I got. Right? This is incorrect. So remember that when we are moving from this search space to this search space, I am making one guess. I am not making n guesses over here. Right? I made just one guess and I was able to reduce my search space from n to n by 2. Right? So basically, at the 0th guess, when I have not made any guess, my search space is of size n. After first guess, right? After first guess, my search space is of size n by 2 to the power 1. After second guess, my search space is of size n by 2 to the power 2. After the ith guess, my search space will be of the size n by 2 to the power I. Right? Now the question is, at what value of k? At what value of k will this thing become equal to 1? At what value of k will my search space reduce to one single element? And that is the question that we are asking ourselves. So this is the equation that we get, right? So at the kth guess, our search space will be this, and we want the search space to have just one element. So can we find the value of k from here? Can we find the value of k from here? So what can we say? This implies that n equals to 2 to the power k, which implies that I can take log on both sides. Right? I can take log base 2 on both sides, log base 2 of 2 to the power k, right? Which implies that k equals to log base 2 of n. Is that clear? Yes. So I am taking order of log n guesses. I am making order of log n guesses, right? And that is the complexity. That is the time complexity of binary search. Is that clear? Yes. Is that clear, guys? So basically, we started with an array of size n. Then after first guess, we were able to reduce it to half the size. Then after the second guess, we were able to reduce it to 1/4 the size, and so on and so forth. So how many guesses we will take to reduce it to size 1? Well, it will take us log base 2 of n guesses. Right? The depth of this tree, the depth of this is log base 2 of n. Is that clear? Right? Okay. What about the space complexity? What about the space complexity? So let us go to the code to analyze the space complexity. Let us go back to our code and let us see what variables we are using. Okay? So this is our code. Let us see what variables we are using. So we are declaring a variable over here, n. We are declaring a low, we are declaring a high, and we are declaring a mid. Right? All of these take constant space. They are just integers. So overall, our space is just constant. Right? We are not allocating any space that is dependent on the input. We are just allocating a constant space. Right? Notice that this vector, we are not allocating this. This is given to us already. Given to us. Since we are not changing this array at all. So we don't have to allocate the space for the array. All right? The array is given to us. So the space complexity of binary search is going to be simply order of 1. All right, constant space. Is that clear, guys? Perfect. Now let me ask you a question. Let me ask you a fun question over here. So this is called binary search. Right? This is called binary search. Binary search. Why is it called binary search? Because we are splitting into two parts with every guess. right? And we saw that when we do binary search, our complexity turns out to be log base 2 of n. Right? Our complexity turns out to be log base 2 of n. What if instead of binary search, what if I try to come up with something like ternary search? What if I tried to come up with something like ternary search? So first of all, how would ternary search even work? Right? How would ternary search even work? If I have this particular array, then now I have to guess two values. I have to get mid 1 and I have to get mid 2. Right? This is my low. This is my high. In ternary search, what I can do is I can make two guesses. Right? I can make two guesses. I can say mid 1 equals to low plus high minus low by 3. Right? And I can say mid 2 equals to low plus 2 times high minus low by 3. Yes or no? Can I do that? And then I can compare. Right? Then I can compare. So I can compare AR of mid 1 with my key. Right? I can compare AR of mid 2 with my key. Right? And what will I get? What will I get? Either my key will lie in this area, or my key will lie in this area, or my key will lie in this area. Yes, that is all the possibilities, right? My key cannot lie in both these areas at the same time. Right? My key cannot lie in both these areas at the same time. Does that make sense? So after one guess, we were able to reduce our search space by 1 to 1/3. Right? From n, we could go to n by 3. Right? We could eliminate a larger chunk of our search space. Does that make sense? This is called ternary search. And in general, you can extend this idea. You can define something called a k-ary search. And in k-ary search, what you will do is you will calculate mid 1, mid 2, all the way till mid k minus 1. Right? And then we'll compare with all of them. That will allow us to, in one guess, it will allow us to go from n all the way till n by k. Right? Does that make sense? Yes, ternary means 3 divisions. Binary means 2 divisions. K-ary means k divisions. All right? Is that clear? Example of ternary search? Well, the example is very simple, right? We given an array. What I'm going to do is I'm going to make 2 guesses. Right? Instead of making one guess at any point, I'm going to make 2 guesses. And based on these 2 guesses, I'm going to decide whether I should be looking over here, or I should be looking over here, or I should be looking over here. Right? Going back to our original question, when we were supposed to guess between 0 and 1000. Right? Instead of you giving me a guess like 500, you could have given me 2 guesses at the same time. You could have given me 333 and 666. Right? And then I could have told you that, okay, it is less than 333, or it is between this, or it is above this. Does that make sense? Yes? Does that make sense? Right? So the time complexity of ternary search, it seems that the time complexity of ternary search will be order of log base 3 of n. Right? Because we are dividing by 3 every time. Similarly, the time complexity of k-ary search would be order of log base k of n. Yes? Now, which is greater? Which do you think is greater? Is log base 2 of n more, or is log base 3 of n more, or is log base k of n more? Right? For some large value of k, which value is more? Which value is smaller? Right? So which value is larger? Which value is smaller? Well, if we divide by 2, then it takes us certain number of steps to reach 1. If we divide by 3, then it will take us lesser steps to reach 1. Right? If we divide by 3, then it will take us lesser steps to reach 1. So log base 2 is greater than log base 3n, which is greater than log base kn. Right? So it seems like k-ary search should be the fastest. Right? So why do people still use binary search? Why don't we always have k-ary search? K-ary search seems to be very fast. Right? And it seems that I can make it as fast as I want. right? I can just increase the value of k to make it as fast as I want. Yes or no? Yes? Well, let us see what is the fastest value I can have. So maybe when k equals to n, I will get log base n of n, right, which is simply 1. So I will be able to find the answer in just one guess. That is amazing, right? I will be able to find the answer in just one guess. That's very, very weird, right? I was able to find the answer. I was able to search the element in the array in just one guess if k equals to n. Is that correct? Is that correct? Yes, but there's a catch over here. Right? Now what really happened was we had this array and we made every element as a guess. Right? We made every single element as a guess. And then we checked if our guess is between over here or 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 over here, right? In one guess itself, we made we chose n different values and different midpoints, right? N minus 1 different midpoints. So are we really doing an efficient search over here? No, this has reduced to the linear search. Right? This has reduced to linear search. So it turns out that when k equals to n, we were expecting it to take just one guess. It did take just one guess, but inside that single guess, we were doing a linear search. Right? So this is the worst thing that we can do. Does that make sense? K equals to n is the worst thing that we can do. So what really gives? We see that our intuition does not equal our math over here. Right? Math says that this should be faster, but intuition says that this should be slower. So what really gives over here? Right? What really gives over here? Well, there's a catch. Right? There's a catch in the fact that this is big O complexity. Right? There's a hidden constant factor. Let us look at the exact complexity of searching. Right? Let us look at the exact complexity of k-ary search. If I'm doing binary search, then I have one guess, right? I have one midpoint. Yes? I have one midpoint. Do you agree? And what check am I making? I'm comparing A of mid with k. Right? How many comparisons is this? This is one comparison. Right? So my actual complexity is 1 times log base 2 of n. Right? This is in the case of binary search. On the other hand, when I have ternary search, I will guess 2 midpoints. Right? I will be guessing 2 midpoints. And then what comparisons do I have to make? I have to compare A of mid 1 with k. I have to compare A of mid 2 with k. Do you agree? Yes, I have to compare A of mid 1 with k, and I have to compare A of mid 2 with k. So how many comparisons is that? This is in fact 2 comparisons. Right? Now you see the hidden cost. As we increase the value of k, the number of comparisons for each guess increase. Does that make sense? Yes, guys. So for ternary search, our complexity is 2 times log base 3 of n. Right? This is for ternary search. And in general, for k-ary search, our complexity will be log base k of n. But for every guess, we will have to make k minus 1 comparisons. Right? We'll have to make k minus 1 comparisons. Now let us ask this question again. What do you think is larger? Right? What do you think is larger? Is log base 2 of n times 1 larger? Or is 2 times log base 3 of n larger? Or is k minus 1 times log base k of n larger? Right? Which one of these is larger? Well, now we know that actually this is the reverse, the other way around. This is the slowest. This is the largest value, so this is the slowest. And in fact, binary search is the fastest. Is that clear? So we can totally do k-ary search. We can totally do a ternary search. We can totally do a k-ary search. But practically, binary search will work much, much faster. Is that clear, guys? Is that clear? Binary search will work much faster. Right? Cool. Now, there's this question. Now you might be thinking that, okay, you told us about ternary search, you told us about k-ary search, and then you said that, okay, those don't really matter, right? Why did you even tell us in the first place? Right? Why did you tell this to us in the first place? The reason is that in certain situations, k-ary search can become faster. Right? K-ary search can become faster. Let us look at how. Right? Let us look at how. Suppose that we are dealing with some sort of a disk, right? Hard disk. Right? Suppose that we are dealing with some sort of a hard disk. Do you know that hard disk is split into blocks and sectors and tracks? Yes. So basically, we are talking about a spinning hard disk over here. Right? We're not talking about that the new SSDs over here. We're talking about that spinning hard disk over here, the magnetic hard disk. So what really happens is, in a magnetic hard disk, you have several platters. Right? You have several platters, and for each platter, you have a read head. Right? You have a read head that is at a particular platter that is tracking a particular track. Right? That is tracking a particular track on this platter. Right? Now, what you have to do is this one track information across this one track is let's say called a track, right? And let us say this is one block. So usually this can be something like 32 kilobytes. This could be 32 kilobytes. All right. Now, what happens is if you have to read any value within this, then that is very fast, right? Then that is very fast because your disk is spinning, right? Your magnetic disk is spinning at 1000 RPM. Right? So within 0.001 second, you can read this entire 32 kilobyte. You can read this entire 32 kilobyte block. Right? But if you have to change blocks, if you have to move from this sector, if you have to move from this track to perhaps this outer track, right? If you have to do that, then what you have to do is you have to move this head. You have to move this read head. So you have to unplug this read head. You have to run the motor to move it back. Then you have to plug it back, right? And that takes some time. So that moving the read head can take a lot of time. It can take, say, that is 0.1 seconds of time. Right? So that is very, very slow. Is that clear? So it turns out that what really happens, is it could be the case that due to this thing, it could be the case that making comparisons is fast. All right, you read 32 kilobytes of data in the memory, and then once the data is in your RAM, you are making comparisons in the RAM, right? And RAM is very, very fast, very, very fast. On the other hand, making a guess is slow. Making a guess is slow, right? Why? Because for every guess, for making a new guess, you have to change the block. You have to change the hard disk block, right? And you have to move that read head manually, right? Because this is happening at the hard disk level. This is not happening at the RAM level. Okay. So what really happens in this case is making a guess. I want to reduce the guesses. I want to reduce the number of guesses I make. I don't really care about the number of comparisons I make because the comparisons are happening in the RAM very, very fast, right? So in this sort of scenario, I would prefer to use some sort of a k-ary search, right? I would prefer to use some sort of a k-ary search because in a k-ary search, this is the number of comparisons, right? And this is the number of guesses. This is the number of guesses. The larger the value of k is, the lesser my guesses will be, right? The larger the value of k is, the lesser my guesses will be. So basically, to maximize my efficiency, I choose a k which is equal to the block size. Right? And this thing, right? This thing is used all the time in databases. Whenever you are using a database, the database internally is storing the data in a thing called a B plus tree. Right? In something called a B plus tree. And a B plus tree is simply a binary tree that has been extended from. So binary tree works in a binary search manner. Right? On a binary tree, you can have a binary search tree and you can binary search on it. On a B plus tree, you can do a k-ary search. You can do a k-ary search on a B plus tree. All right. How did you come up with this formula? So this formula is what we just saw, right? This formula is what we saw for binary. For binary search, we have one comparison and log base 2n guesses. For ternary search, we have two comparisons and log base 3n guesses. For k-ary search, we have k minus 1 comparisons and log base kn guesses. All right. Is that clear? This is multiplication. Is that clear, guys? All right. So I think we are going to leave it at this, right? We are already above the time. So today we basically discussed binary search. Binary search. We saw how to implement it, right? We saw how to implement it, and we saw that this idea can be extended into a k-ary search, into a ternary search or a generic k-ary search. K-ary search is generally slower, right? Generally, we would like to do binary search, but there are cases. There are cases, like for example, databases, in which k-ary search is very, very valuable. Okay, cool. Now, I would want each of you to, once this lecture is over, to find the link in the video description. There's a link to the assignment, right? Today's assignment. So please go over there and try to solve those problems. So those problems will be on basic binary search. There are some things that we were not able to discuss, like binary search on a rotated array, right? Finding the peak element. We can discuss it in the next class. All right. All right, guys. Cool. Will we cover interview bit problems from your website? Yes, Reshma. So all these problems. So that is why we give you the assignments, right? We are discussing the problems that are part of those assignments. Okay. I mean, of course, when we are actually doing a scalar class, when someone joins our academy, we usually have 3-hour classes, right? And we have classes every single day for 3 hours. So that gives us a lot of time to work with the student, right? So they are able to solve many more problems. We won't be able to do that on YouTube, right? So I understand that you won't be able to get the exact same experience as scalar, but that's to be expected, right? Because this is on YouTube. All right then. So please make sure that you solve the assignment. Please make sure that you are taking notes while you're studying the lecture. And see you in next class. In the next class, I will continue. We will continue with binary search, and we will be looking at more advanced problems on binary search. Okay. Perfect. If you want to join Scalar, well, we don't really announce the dates during lectures. So whenever, if you're trying to join Scalar, just go to scalar.com, right? And any announcement about a new batch, will be made over there, right? So please monitor the scalar.com website, and any announcement about any new upcoming batches will be made over there, right? So let us end the lecture then. All right. Bye-bye, guys. Have a nice day. We are back with another lecture. Today, we are going to continue binary search. We are going to look at some questions that have been asked in companies, in some of the top companies, right, regarding binary search. Now, without further ado, let us start the class. So let me just share my screen. All right. I hope that everyone can see the screen and whatever I'm writing over here. Cool. So let us start with a question directly. So yesterday we had looked at what binary search was and how to implement binary search. Let us dive into one question today. Okay. So suppose that you have been given an array, right? And this array has n integers. All right. Now, it has also been told to you that in this array, all elements but one come twice. All right. Also, it has been said that the array is sorted. So let us first take an example of such an array. Let's look at such an example. Let's say that we have 0, 0, we have 4, 4, minus we have, let's say, 5. All right, we have 5 over here, suppose. Right? Then we have, let's say, something like 7, 7, and we have 8, 8. Right? So in this array, we see that every element has been repeated twice. There are 2 zeros, there are 2 4s, there are 2 7, there are 2 8s, except for one element. Right? Except for one element, every element is repeated twice. Also, this array is sorted. Right? So it is sorted in ascending order. I hope my voice is clear. All right. Cool. Now the question says you have to find this singlet element, right? You have to find this element which occurs only one time. So if this was the array that was given to you as input, then you are supposed to return 5. Is the question clear? Yes. So we have been given an array. It is sorted. Every element in the array occurs twice, except for one element. And we have to find that one element that occurs only once. All right, so let us see some approaches. So Piyush has a very nice idea over here. Piyush says, let's try XOR. Right now, we all know the property of XOR. We have seen that in the bit manipulation class. That XOR acts like a lock and key. Right? Basically, if I XOR the entire array, that is supposed to give me that element that occurs only once. Right? That element. I'm supposed to get the correct answer because all these things will cancel. Right? 0 XOR 0 will cancel. 4 XOR 4 will cancel. 7 XOR 7 will cancel. 8 XOR 8 will cancel. And I will be left with 5. So yes, that's a valid approach. That is totally a valid approach. What is the time complexity of this? How much time will this take? This will take order of n time, right? Because we have to go over each element and check, right? We have to XOR each element, all right? Cool enough. Can we do better? Using this XOR thing, are we first of all making use of this property? We know that the array is sorted, right? So either if we use XOR or if we use a map to keep a count, then we are not really using this sorted property, right? They are going over each element. So let us try to make use of this sorted property and see if we can reduce the time complexity. So this is a valid brute force approach. But let us come up with an optimized solution that exploits the property that the array is sorted. Yes, let us see if we have some other approaches. All right. So yes, binary search would be the answer here. But what exactly are you going to do with the binary search? How exactly are you going to search it? All right. So Anurag over here says that let us check the middle element. All right. Let us suppose we have some middle element. And what Anurag is saying is let us compare it with the previous or next element. Right. And then return. Well, let us suppose that this array was a little longer. Right? Let us say that we had 10 over here as well. So when you find the middle element, let me just add the indices. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So what will be the middle element? This will be the middle element. Right? Cool. Now, if this is the middle element, then we compare it with the left and right element, and what exactly do we do? So we look at both neighbors. All right. This is 5 and this is 7. So how does that help us? It doesn't really help us, right? Okay. So what can we do then? Yes. So Dipanshu has a nice idea over here. Let me just show Dipanshu's comment. So Dipanshu says that let us observe one thing. That whenever a new element comes, it always comes at an even position. Right? Whenever a new element comes, it always comes at an even position. Yes? Is that correct? Until and unless that middle element comes. After that, every new element comes at an odd position. Do you all agree? Yes, the first occurrence of any element is on an even position on the left side of this mid and is on an odd position on the right side of this mid. Do you guys observe that? So we are going to use this property. We are going to use this observation to find out what the single occurrence element is. Right? So suppose that we do something like this. We pick. So we have a high and we have a low. Right? So this is 5 and this is 8. We have a low and we have a high. Right? Let us calculate some mid. Right? Let us calculate some mid. What we will do is this mid will be, let us say, A of mid. Right? This A of mid, it might be the first occurrence of this value or it might be the second occurrence of this value. Right? We don't really know. This 7 that we landed on, this could be the first occurrence of 7 or this could be the last occurrence of 7. Right? We don't really know. So what we can do is we can find the first occurrence of 7. Suppose that we landed on this bit. Suppose that we had landed on this bit. Then we can compare it with the previous element and always find the first occurrence. First occurrence of A of mid. Can we do that? Yes. Given a mid number, can we find A of mid and then can we find the first occurrence of A of mid? It will either be that element itself or it will be just the previous element. Right? Cool. Now once we have that, we can check if the index of first occurrence of A of mid, right? If this is even, then what does that mean? That the singlet element lies to the right of me. Right? Whenever I find the first occurrence at an even position, that means that the singlet element lies to the right of me. So I will move right in this case. Right? On the other hand, if this is not the case, if it is odd, then I will move left. Yes. And I will also have to stop at some point. Right? I will also have to stop at some point. So I can check if A of mid is the first occurrence, and there's only one occurrence, right? So A of mid plus 1 is not equal to A of mid. Then I know that I have found my singlet element because it occurs only once. Does that make sense? Yes. So what will be the very quick pseudocode for this? So we will start with low equals to 0. We will start with high equals to length of, so AR dot length minus 1, right? Then we will loop while low is less than equal to high, right? What will we do? So we will calculate the mid first. So we will say mid equals to low plus high minus low by 2. Yes, we just calculated the mid. Remove the extra string comment, surely. Yes, cool. All right, so we calculate the mid, then we can check. So we will first check. So we know that we have to find the first occurrence of A of mid. Right? How do we find the first occurrence of A of mid? Well, we can check over here. We can check if A of mid minus 1 equals to A of mid. Right? If this is the case, then A of mid is the second occurrence and not the first occurrence. Do you agree? Yes, if A of mid minus 1 is equal to A of mid, then A of mid must be the second occurrence because the previous element is also equal to it. In this case, what is the first occurrence? The first occurrence is mid minus 1. Right? In this case, the first occurrence is mid minus 1. Otherwise, the first occurrence is mid itself. Right? All right. So what I can do is over here is I can do mid minus minus. Mid minus minus. And then over here, my mid contains the index of the first occurrence. Now I can check. If mid is even or odd. So if mid is even, mod 2 equals to 0, then I have to move towards my right. Yes, I have to move towards my right. How do I move towards the right? I say low equals to mid plus 1. Right? Otherwise, else I move towards the left. I say low equals to, high equals to mid minus 1. I simply say high equals to mid minus 1. Right? Perfect. But that does not really tell me when to stop. Right? That does not really tell me when to stop. So I have to make some other checks as well. Also, there is one more problem over here. That what if this mid turned out to be 0? what if this mid turned out to be 0? Then this a of mid minus 1 will give me an index error. Right? I will be trying to index at a negative value. That is not good. Right? So I have to take care of these things. So first of all, what I can do very quickly over here is I can first confirm this. Right? I can first fix this thing. I can say if mid is greater than 0, right, and a of mid minus 1 is equal to a of mid, right, then do mid minus minus. Then do mid minus minus. So after this point over here at this line, mid will be the first occurrence of a of mid. Right? Mid will be the first occurrence of a of mid. Now if mid is even, we do low plus, we increment the low, else we increment the high. But once again, when do we stop? Once again, when do we stop? So we can check over here. If a of mid plus 1, right? If a of mid plus 1 is actually equal to a of mid, is not equal to a of mid, my bad. So we have the first occurrence of this element, right? We have the first occurrence of this element. And if the next element is not the same, then we have found the correct location, right? Then we have found the correct location. So what I can do over here is let me just erase this and write it properly. And also we will have to make sure that we check the boundary condition, right? So we will check if mid is less than n minus 1 and a of mid plus 1 is not equal to a of mid, then what do we have? We can just return. We can just return the mid because this is the correct answer. Is that clear? Yes, is the approach clear? So the approach is very simple. The approach is just saying that once you have these elements, all the elements come in pairs, right? All the elements come in pairs. So 0, 1 will come in one pair, then 2, 3, this will be the second pair, then 4, 5, this will be the second pair, until and unless this singlet element comes. Right? This singlet element comes. After that, we will once again have the numbers in pairs. So 7, 8 will be there, then 9, 10 will be there, then 11, 12 will be there, 11, 12 will be there, right? Now notice that before this singlet element, every new element occurred at an even index. Right? Every new element occurred at an even index. But after this, every new element occurs at an odd index. Right? So that is just what we are exploiting. All right. Cool. So what will be the time complexity of this approach? What will be the time complexity of this approach? So Abhay says, what if a of mid minus 1 equals to a of mid, then what are we doing with this? Right? So basically what I'm saying is, suppose we landed at this element. Right? Suppose we landed at this element. This element was 7. Right? This and its previous element was 7. So if this is mid, then we are checking if a of mid minus 1, right? Mid minus 1, if that is also the same as 7, if that is also the same as the same element, then move mid to the left. Right? Then do mid minus minus. Right? That will make sure that we are always looking at the first occurrence of an element. Right? Cool. So the complexity of this is just order of log n. Right? Why? Because this is a binary search, and at every time we are splitting the array into half. We are reducing the search space by half. Right? Is that clear? Cool. So this was a fairly easy question. Let us move on to a slightly more difficult question. Okay. But before that, let me just give you a brief thing. So when you are finding a number in an array, right? You usually return some index. Right? You usually return some index. Now, what occurrence is this? Which occurrence is this? Which occurrence is this? Basically, what I'm saying is, suppose that I have a sorted array 0, 1, 2, 2, 2, 2, 2, 3, 4, 5, 6. Right? Suppose that I have this sorted array. Right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now suppose I want to find the value 2. Right? I want to find the value 2 in this array. Right? So when I'm searching for the value 2, the value 2 occurs at more than one indices. Right? It occurs at all these different indices. So what index should my binary search really return? That is the question. Right? So yesterday we saw that okay, we were returning an arbitrary index. Right? As long as we found the index, it didn't really matter what occurrence we were looking for. Right? So, I mean, that is perfectly fine. But usually what you will do is you will try to return either the lower bound. You will try to return either the lower bound, right, which is basically the first occurrence, right, or you will return the upper bound, right, which is the last occurrence. Does that make sense? Yes. What if the array is not present? So lower bound is the first occurrence, right? Or if the element is not present, it is the location. It is the location at which I can insert the element. I should insert the element. Insert the element to keep the array sorted. Yes. Similarly, the upper bound is the last occurrence. Right? Is that clear? Yes or no? All right. Cool. So basically, the question now is that if you have been given this, if you have been given an array like this, and I ask you that given a value 2, you have to return both the first occurrence and the last occurrence of this element, then how will you do that? Right? How will you do that? What if lower bound equals to upper bound? Well, that simply means that the element occurs only once. Right, Reshma? That simply means that the element occurs only once. So suppose that the question is that given this array and this value 2, you have to find both the first occurrence and the last occurrence of this array. So basically, if I give you 2, you have to return 2 and you have to return 6. So if the input is this array into, you have to return 2, 6. Right? So how will we do that? Yes, so this is very simple, right? This is very simple. We just have to make sure that we tweak a little bit of those -1s and +1s. Right? We just have to make sure that we tweak a little bit on those -1s and +1s. Right? So usually what we do is we write the loop like this. So while low is less than equal to high, right? And then what do? We say if array of mid, so we have mid calculation over here, we have something over here. We say if array of mid is less than key, right? If array of mid is less than key, then what do? We do lower bound. We do low equals to mid plus 1. We do low equals to mid plus 1, right? Otherwise, else if a of mid is greater than key, then we do high equals to mid minus 1. Mid minus 1, right? Otherwise, if it is exactly equal, in the last class we saw that we can just return the mid, right? We can just return the mid because we have found the location. But now we can't just return the mid. Right? Now, if we are looking for the first occurrence, suppose, if we are looking for the first occurrence, can we return the mid arbitrarily? No, because what could happen is when we calculated the mid, suppose we landed at this particular location. Right? We found the two, but we cannot return it, but because this is not the first occurrence. Right? This is not the first occurrence. So how do I ensure that this is the first occurrence? I will have to check over here that first of all, else if mid should either be 0, right? If the mid is equal to 0, then it is my first occurrence, or a of mid minus 1 should not be equal to a of mid. Should not be equal to a of mid, right? Because if the previous element is equal to the same element, then this mid is not the first occurrence. Does that make sense? Yes or no? All right, that is fair enough. But then what does really happen then? If I write this code, there is a condition remaining, right? There is some condition remaining over here. Yes, there's some else condition remaining over here, right? So what do I really do in that else condition? Well, I have to absorb that else condition. It will have to absorb that else condition somehow. So basically what I need to do is I need to make this thing less than or equal to key. Oh, sorry, I have to make this thing greater than or equal to key. Right? Basically, if I have found the element, but it is not the first occurrence, then I will still decrease my high. Right? Suppose I found the element, I found the element over here, but it is not the first occurrence. The first occurrence occurs over here. Then what should I do? I should move left. I should decrease my height. Is that clear? But once again, the moment I do this, something else happens. Right? Another issue arises. What is that issue? That issue is that if I have this condition in my else if, I will never come into the else. Right? I will never come into the else. So what I will have to do is I will have to move this particular condition on the top. Yes, do you guys agree? Do you guys see the problem? Because if I have less than here and if I have greater than equal to here, then I will never go into that else condition, right? These conditions are exhaustive. Yes? So I will have to move this up. So what will my actual code look like now? What will the correct code look like now? For finding the first occurrence, what I have to do is I have to check first of all. If mid is 0, right? If mid is 0, sorry, if a of mid equals to key, right? If I have found the value and either mid is 0 or a of mid minus 1 is not equal to a of mid, right? Only then, if I found the element and it is the first occurrence, only then can I return the mid. Right? Only then can I return the mid. Otherwise, so let me just put it over here. Right? Otherwise, if a of mid is less than the key, then I have to move up. Right? So I can say low equals to mid plus 1. Right? Otherwise, else I can simply say high equals to mid minus 1. Right? And this is what my correct code looks like now. This is what my correct while loop looks like now. And this is for the first occurrence. Right? This is for the first occurrence. So this code is incorrect, this code is incorrect. Right? And this is the final correct code for the first occurrence. Can you similarly find the last occurrence? Can you similarly find the last occurrence? Yes or no? Yes, you just have to do it the other way around. Right? You just have to do it the other way around. Basically, you have to make sure that a of mid equals to key and mid is equal to either mid is equal to n minus 1 or a of mid plus 1 is not equal to a of mid. Right? That way we find the last occurrence. And when we are finding the last occurrence, this will be less than equal to, and this will not be, this will be less than equal to, right? This will come in less than equal to over here. So that is very simple. It is very simple to find the first and last occurrence of an element in an array. All right. Now suppose that I have an array which is sorted and has size n, and I tell you that given a value x, you have to count the number of occurrences of x in this array. Then what will we do? If we have to count the number of occurrences in this array, then what will we do? Yes? Jay says instead of two binary searches, can we take a while loop both sides and find first and last occurrence? Yes, totally, Jay. We can totally do that. So let us we are going to explore that via this question. Right? We are going to explore that via this question. Suppose that we have this array. Right? Suppose that we have this array. This element is x, 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 and all the way till this location, it's x. Right? Then this is something else. This is y, y. This is a. So if I am supposed to find the count of x's, this is a sorted array. If I'm supposed to find the count of x's, then I have two options. Either I can find the first occurrence, then write a while loop, then write a for loop, right? Till the last location of x. Yes or no? I can find the first occurrence and then I can increment the count one by one. I can go one by one and till I reach the last occurrence of s. And I can do a count plus plus. Right? I can do a count plus plus. If I do it this way, then what will be the time complexity? What will be the time complexity of this way? Well, to find the first occurrence, it will take me order of log n time. But after that, After that, to count each of these values, I will have to count one by one again and again. Right? I will have to count one by one again and again. So it will take me order of n time for the counting in the worst case. Right? What if the entire array was full of the same values? Does that make sense? So in this case, this approach will be linear. This approach will be linear. On the other hand, can I do something better? Can I do something better? Let me just clear the banner. Just give me a second. Yes, can we do something better? Right? So what we can do is we can simply find the last occurrence. We can simply run a binary search to find the last occurrence. Right? This is one binary search. Binary search. And we can also use another binary search, one more binary search, right, to find the first occurrence. Right? And then we can simply return last occurrence minus the first occurrence. Yes? Is that correct? Plus 1. Exactly. Right? Last occurrence minus first occurrence plus 1. All right? And that will basically give us the count of that element. Is that clear? Yes? All right. Perfect. Cool. So I hope this is clear, because this is very important. First of all, because whenever you do binary search, you have to understand that you're either going to be finding the last occurrence or the first occurrence. You're not going to be returning any arbitrary occurrence. Also, because in all of the further questions, whenever you are doing binary search, this is going to be very important for us. It is going to be very important for us. So let us look at another question. Right? Let us look at another question. So suppose that we have been given two sorted arrays. Right? This is a very, very famous question. This question has been asked in all sorts of companies, right? Be it Google, be it Amazon, be it Facebook, be it DirectTime. All the companies have at some point asked these questions, this particular question, and this question is very, very, very frequent, right? And even if you try to search on YouTube, you will find hundreds of videos about this question. So this question is very important. The question is that you have been given two sorted arrays of length n and m respectively, right? So you have been given two sorted arrays. One is of length n, one might be of length m. Right? We don't really know which is larger, which is smaller, and both are sorted. Right? Both are sorted. The question is, we have to find the median of both the arrays combined. Right? We have to find the overall median. Yes. Right. So first of all, let us look at what median is. Right? First of all, let us quickly look at what the median is. So suppose that I give you this particular thing. Suppose that I give you this array 1, 2, 3, 5, 5, 6, 8, 10. Right. Suppose that this is my array, and let me put the indices as well. Right. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right. So what is the median defined as? What really is the median? So median basically is another term for the middle element. Right? This is a loose definition. This is not the exact definition, but median, you can think of median as the middle element, right, of a particular collection. Now, what do we mean by middle element? If you're talking about a middle element, we should have some sort of order. We should have some sort of ordering, right? Yes. So that is why we are talking about a sorted array. So we are saying if we sort a particular array and then we look at the middle element, so in this case, do I have a middle element? In this case, do I have a middle element? How many elements do I have? I have 9 elements in total, right? I have 9 elements in total from 0 all the way till 8. So what will be my middle element? This will be my middle element. Yes, this will be my middle element. Okay. So basically, this is what a median is. Now, some of you might ask, all right, well, what if the number of elements is even? Right? What if the number of elements is even? So let us say that I add up 20 over here. Right? Now I have 10 elements. Right? This is no longer 9, this is 10 elements now. Now there's no middle element, right? The middle element does not exist now. There are two middle elements. Both this and this are middle elements. Yes. Then what is the median? Well, in that case, median is the average of both of these. So in this case, this is both 5 and 5. So the median is just 5. On the other hand, let us try to change the values. So let us say this is 9, this is 9, and let us say this was 8. Right? If this was 8, then what will the median be? It will be 5 plus 8 by 2, right? Which is 13 by 2, which is 6.5. All right? Is that clear? Cool. So this is what the median is. Now the question says that you have two arrays. You have two arrays. Let us suppose 0, 0, 1, 3, 5, 8. Right? And you have another array. Let us suppose 4, 5, 6, 7, 8, 9, 20, 30. Right? Let us suppose that we have these two arrays. So let me put the indices very quickly. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now the question is not asking you to find the median of each of these arrays. That is not what is being asked. What is being asked is the median of the overall array, right? Of the overall collection. So basically, if I were to take all these elements, consider all these elements and sort them, right? Consider all these elements and sort them, then what will be the median? So what will be the median in this case? What will be the median in this case? If I write both the arrays in sorted form, I have 0, 0, 1, 3, 4, 5, 5, 6, 7, 8, 8, 9, 20, 30. Right? Yes or no? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? That's an even number of elements. So the elements, what? The elements 6 and 7. So the median will over here be, the median will be 5.5. Is that clear? Yes or no? Is the question clear? We have been given two arrays and we have to find the overall median of the two arrays. Is the given array sorted? Yes. Both the arrays are individually sorted in ascending order. Right? Both the arrays are individually sorted in ascending order. Right? But I mean, relatively they are not sorted. So it is totally possible that this element is greater than this element. Right? That's totally fine. Okay. There's no relation between the two arrays. It is just that they are individually sorted. Yes. So yes, Shivani has a nice approach over here. Shivani says that let us very quickly merge the two arrays. So where did our comment go? Yes. So Shivani says over here that what we can do is we can merge the two arrays. So when you were doing the merge sort class, you read this merge algorithm, right? Merge algorithm. What did this merge algorithm do? Given two sorted arrays, it created a sorted array. Yes. And how much time did it take? How much time did this merge algorithm take? So if I have total of n plus m elements, if I have n plus m elements, then usually if I just do sorting, right? If I just do sorting in a naive way, then how much time will sorting take me? It will take me n plus m log of n plus m, right? This is how much time sorting will take me. However, if I use the merge algorithm, given that both the arrays are sorted, then I can do it in order of n plus m time. Yes, I can merge the arrays in order of n plus m time. Once I have merged both the arrays, then I can very quickly find the median. Yes, I can very quickly find the median. Right? Find the median. How much time will it take me? If I have merged both these arrays, how much time will it take me to find the median? So suppose that I have merged both the arrays. After that, how much time is it going to take me to find the median? So is it going to take us order of log n time? No, right? So finding a median is just order of 1. You just have to look at a of mid. Right? You just have to look at a of mid. If the number of elements is even, you just have to look at a of mid and a of mid plus 1. Right? So finding the median takes just order of 1 time, provided that I already have a sorted array. Overall, if I do this merge thing, my overall complexity will be order of n plus m to merge the two arrays plus 1 to find the median. Okay? To find the median, which is just order of n plus m. Is that clear? Order of n plus m. Well, that is fine. That is good. That is certainly better than the naive approach. Right? So this was the naive approach. So this is certainly better. But we can still do better. So this is not the best approach that we can use. So can we still optimize? Can we come up with an optimized approach now? What other approaches we have? So Ratnesh has a very, very nice question over here. Ratnesh says, can't we just use the median of medians? Median of medians, right? What does Ratnesh mean over here? Let us suppose that we consider these two arrays, right? Let us consider these two arrays separately. What is the median of the first element of the first array? So this is the first array. What is the median of the first array only? So this array has 6 elements. So the median will be what? So 0, 1, 2, 3, 4, 5, right? It has 6 elements. So the median will be at what index? No. So what Ratnesh is telling us is that let us try to find the median of medians. Right? Let us try to find the median of medians. So first of all, let us consider this particular array, A1. Right? This particular array has how many elements? It has 6 elements from this location to this location. So what will be the median of this particular array? It will be the sum of these two. It will be the average of these two, right? It will be 1 plus 3 by 2, which will just be 2. Right? Similarly, let us calculate the median of this array. Let us calculate the median of this array. Well, how many elements does this array have? This has 8 elements, right? And what is the median of this element or this array? That will be this 3 plus 4, right? This element at 3 and element at 4. So that is 7 plus 8 by 2, which is 7.5, right? Now, Ratnesh is saying, once we have these two medians, can't the final answer simply be the average? Can't the final answer simply be the average of these two? 2 plus 7.5 by 2? Well, no, that is not going to be always true. Right? That is not going to always be true. Is that clear, Ratnesh? Over here, we see that this does not really work. This is 9.5 by 2, which is 4.75. Right? And that is not the answer. The correct answer is 5.5 over here. So it doesn't really work. All right. So let me just remove Ratnesh's comment. So median of medians will not work over here. So we have to do something else. Yes. So what approach can we use? What approach can we use? So now we have to do some sort of a binary search. Right? We can use some sort of a binary search to optimize this solution. Right? So what we are going to basically do is we are going to binary search. There are multiple ways of doing this. Right? We are going to binary search on the index only of. We are going to binary search over the smaller array. Right? So first of all, suppose that this is A1, suppose that this is A2, right? So can I assume without loss of generality that A1 is smaller than A2? Can I assume that the length of A1 is smaller than length of A2? Yes. If that is not the case, then I can just swap those arrays, right? I can call this A1 and this A2 if that is not the case, right? So let us assume that A1 is the smaller array. So what we are going to do is we are going to binary search in this smaller array. All right. So we will have some low, we will have some high, and we will calculate a mid. All right. Now, once we have this mid, the question is, when will A1 of mid be the correct median, be the answer? What has to be true? What has to be true for A1 of mid to be the correct median? What has to be true? If A of mid is the correct median, then how many elements in A1, are less than mid, A of mid? How many elements in A1 are less than A1 of mid? When all these elements are less than A1 of mid? Yes or no? Do you agree? And how many elements are greater than this? Well, all these elements are greater than it. Yes. If A1 of mid is actually the median, right? Then what must be true? What must be true? Then half of the elements, right, across both the arrays, half of the elements must be less than it and half of the elements must be greater than it. Yes, half of the elements must be less than it and half of the elements must be greater than it. Cool. So let us quickly check. So if A1 of mid is actually the median, then how many elements in A2 should be, or if this is the case, if this is actually the median, then how many elements in A2 should be less than A1 of mid? Right, that is the question. Right, so we know that in A1 there are mid minus 1 elements. Oh, there are mid elements, mid number of elements. So the count of elements in A1 that are less than mid is mid. Right? So the total number of elements that have to be less than A of mid. The total number of elements that has to be less than A of mid should be n plus m by 2. Yes or no? Should be n plus m or plus 1 by 2 actually. Do you guys agree? If I have this total sorted array, and this is actually the median, then half the elements will be less than it and half the elements must be greater than it. So if this many elements are less than it overall, right? And out of these, this many elements were already present in A1. Then what is the number of elements that are present in A2 which are smaller than this A of mid? So this many elements were already present in A1. So this must be the number of elements. This must be the number of elements in A2. Number of elements in A2 that are less than mid. A of mid. Yes? Does that make sense? How can you say that length of A1 is equal to mid? No. We are not saying that the length of A1 equals to mid. We are not saying that. We are saying that assume that mid is the correct median. For that to be true, if there are these many elements that are less than it in A1, then how many elements should be less than it in A2? And this is the answer. These many elements should be less than mid in A2. So what we can actually do is, we can start with some low over here, we can start with some high over here, and we can calculate a mid. Now what we can do is, we can put a marker at n plus m plus 1 by 2 minus mid. Right? We can look at this particular index. Right? We will have 4 elements now. We will have 4 elements. We will have one over here, one element over here, one element over here. Right? So let us call these elements A, B, C, D. Right? Now, when is this A of mid? When am I at the correct position? I am at the correct position when A is less than D and B and C is less than B. Right? If this is the case, then this marker, these two markers, they point to my median. Do they not? Yes. Do they not point to the median? Why do they point to the median? Because the number of elements over here and the number of elements over here is equal. Do you guys agree? The number of blue elements is equal to the number of green elements. Yes, and how are they equal? Because I have chosen it to be. Right? Because I have used this formula to make sure that I land at the correct spot over here. Does that make sense? Cool. So guys, if this is not clear to you at the moment, we will make sure to basically explain this with an example. Okay, so we will look at a concrete example, but let me first explain the idea. Right? So basically what we have to do is, we have to binary search for a mid such that this property of the median becomes valid. Right? Now look at a concrete example. Let us look at a concrete example to further establish this. Right? Suppose that we have this array 0, 1, 1, 3, 5, 7. All right, and we have another array. Suppose 4, 5, 6, 8, 8, 12, 20, 30. All right, and let us mark the indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7. All right, now which one is A1 and which one is A2? Which one is the smaller array? This is the smaller array and this is the larger array. Yes, this is the smaller array and this is the larger array. So let us have 2 pointers. Let us have the low pointer and let us have the high pointer. Yes, let us have the low pointer, let us have the high pointer. Also, what is the value of n? The value of n over here is 6. And what is the value of m? The value of m is 8. Yes, there are 6 elements in the A1 array and there are 8 elements in the A2 array. Yes or no? Cool. So now we have this low and high. What will be the mid? What will be the mid? Mid will be 5 by 2, which will be 2. Yes, mid will be 5 by 2, which will be 2. So this is the midpoint. This is the midpoint. Alright. And A1 of mid equals to what? It is 1. Right? Now the question is, how many elements in A1 are less than or equal to A1 of mid? How many elements in A1 are less than or equal to A1 of mid? Well, these many elements, right? This element and this element. Yes, there are 2 elements that are less than or equal to A1 of mid. What is the count of that? Well, the count is simply mid. Right? Mid is the count. Do you agree? Right. Now, if this one was actually the median, then how many elements in this array should be less than 1? Right? In this array, how many elements should be less than 1? Well, total there are 14 elements. Right? Total there are 14 elements. So if there is my median, then half of the elements must be less than it, half of the elements must be greater than it. Right? So basically what I'm saying is 7 elements should be less than or equal to it, 7 elements should be greater than or equal to it. Right? That is the property of my median. Right? Yes or no? Cool. So basically, if this is the case, and two of these 7 elements come from A1, right? 2 of the lesser elements come from A1, then how many lesser elements should come from A2? How many of the lesser elements should come from A2? Well, 2 are from A1, so 5 must be from A2. Right? 5 must be from A2. So all these elements should be less than 1. It should be less than this 1. If 1 was the median, then all these elements should be less than 1. Are they less than 1? Are they really less than 1? Yes or no? They are not less than 1, right? So 1 cannot be the median. Does that make sense? Because all these elements, they are not less than 1, so 1 cannot be the median. So my median is too small. In that case, I have to increase my load. Right? I will try to find the median on the right hand side. Is that clear? Is that clear, guys? Yes. So basically what we are saying is that let us say that we are going to have a low and we are going to have a high, and we are going to calculate the mid as low plus high by 2. Right? Now, how many elements are less than mid, A of mid, in the first array? Well, that is just mid. So how many elements should be less than it in the second array? How many elements should be less than it in the second array? That should be what? That should be n plus m plus 1 by 2 minus mid. Yes, that should be n plus m plus 1 by 2 minus mid. Right? So what we can now do is, so this is the partition. This is basically the partition of A2. Right? Now we can simply check. Now we have 4 elements. We have A1 of mid. We have A1 of mid plus 1. Right? And we have A2 of partition. And we have A2 of partition plus 1. Right? Is that clear? And we can check if this element is less than this element and this element is less than this element, then our partition is valid and we have the correct midpoint. Right? Then our partition is valid and we have the correct midpoint. All right. Why n plus m? Why this plus 1 thing? Well, this is just to make sure that the number of elements that are on the left are greater than or equal to the number of elements on the right. Right? That is just to make sure that the number of elements on the left are either equal to the number of elements on the right, or they are one more than the number of elements on the right. Okay. So if the number of elements is even, then there will be a mismatch, right? You can't have both the same number of elements on both left and right. So we will have one extra element on the left. Is that clear, guys? Just give me a second. Let us look at some code for this. Right? Let us look at some code for this. So what will really happen is, let us suppose that we have 2 arrays. So we have find median, and we have 2 arrays. We have A1 and we have A2. Right? Let us call this A and B. Let us call this the array A and the array B. All right, for simplicity. Now what we are going to do is we are going to make sure that array A is smaller. We are going to make sure that array A is smaller. How can we make sure that array A is smaller? How can we make sure that array A is smaller? Well, we can declare it over here, right? So we can say if the length of A dot length is greater than B dot length, right? If it is in fact larger, then simply swap the values of A and B, right? So this will ensure that that this particular array is smaller, right? And notice that this swap is just swapping the pointers. This is just swapping the pointers. This is not actually moving the arrays. This is just swapping the pointers. All right. So now that we have ensured that A is the smaller element, so now what we can do is we can have a low and we can have a high, right? So we can say that, all right, low, we can initialize low equals to 0 and we can initialize high equals to what? So what array are we searching over? We are searching over the smaller array. We are searching over the smaller array. So we will say high equals to A dot length, right? A dot length, right? And basically, let me also do one thing. Let me also save two values over here, n and m. So let me say, for simplicity, let me say that n equals to A dot length and m equals to B dot length. B dot length. Right? So we have saved the length or the length in nm. So now my low will be 0 and my high will simply be n. All right. Now I can loop. Now I can loop while my low is less than or equal to the high. Right. Now what is the first thing that I should do? The first thing that I should do is I should calculate the mid. Right? I should calculate the mid. And what is the mid? The mid is simply low plus high minus low by 2. Right? Cool. Now this mid is a marker in the first array. This mid is a marker in the first array. What will be my corresponding marker in the second array? As we just saw, that corresponding marker, that is called this partition. Right? This is called this partition. This is going to be n plus m plus 1 by 2 minus mid. Right? Is this clear to everyone? Is this clear to everyone? That this will be the partition? Cool. Now what we are going to do is we are simply going to compare values. Right? We are simply going to compare values. We are going to say that if, okay, we are going to say if A of mid, right? If A of mid is less than or equal to B of partition plus 1. Right? If A of mid is less than or equal to B of partition plus 1 and A of mid plus 1, or basically I can write it the other way. I can write B of partition is less than A of mid plus 1. Right? If this is the case, then what do we have? What do we have? We have two arrays. We have two arrays such that this element is smaller than this element, right? And this element is smaller than this element, right? So A is less than B and C is less than D, right? And we know that the number of elements over here is equal to the number of elements over here, right? If this is the case, then I have found my median. Right? So I have found my median over here. So I have found the correct midpoint, right? And I will actually return the median over here. So we will have two cases over there as well. We will look at that. But if that is not the case, then some other case will arise, right? Then some other case will arise. What case can arise? What case can arise? So either it can be that A is actually greater than B, right? It can be that A is greater than B, or it could be that C is greater than D. Yes or no? If A is in fact greater than B, let us suppose that I have something like 5 over here and 7 over here, right? And I have something like or let's say 12 over here and sorry, not 12. Let us say 1 over here and 3 over here, right? So if this element is greater than this 3, then what does that mean? If this element happens to be greater than this 3, then what does that mean? It means that my midpoint is too high. This midpoint is too high, right? I have to move left. Is that clear? Similarly, if that's the opposite thing, right? If I have 5 and 7 over here, right? if I have, let's say, 12 and 15 over here, right? So if this element is greater than this element, right, then my mid should be on the right. Right? This value 7 over here, this is too low. So I should move to the right. Right? So that is what we are going to do over here. We are going to say else if A of mid is greater than B of partition plus 1, then I have to increase my mid. Right? So I have to decrease my mid. Right? So I will say high equals to mid minus 1. Right? Otherwise, I will say low equals to mid plus 1. All right. So this is the main while loop. Now there are some more conditions that arise. Those conditions are basically, let us take one more example. Let us suppose that we have this particular array and we have this particular array. Right? All right. Now we have two conditions. Either the combined length n plus m, either this is even, or n plus m, this is odd. Right? Either this is even or this is odd. If the length is odd, then what will be my median? If the length is odd, then what will be my median? This is A, B, C, D, right? We know the number of elements over here. So the number of blue elements is either equal to number of green elements, or it is equal to green elements plus 1. Right? It is either equal to it or one more than it. Right? So if I found the correct midpoint over here, then what can I say about the median? The median has to be one of these two things. Right? The median has to be one of these two things. Yes or no? Yes or no, guys? And which one of these is the median going to be? Is it going to be A or C? Well, it is going to be the maximum of A comma C. Yes, the median over here is going to be the maximum of A comma C. On the other hand, if the number of elements are even, then what do I have? Well, in that case, what do I have? I have the max of, I want to find the maximum value on the left, right? I want to find the maximum value on the left. So max of A comma C, and I want to find the minimum value on the right. Right? So a min of B comma D, and I want to take the average of those, because the median will be average of two different values over here. Right? I want to take the average of those. Is that clear? Cool. So basically, what do I have to write over here? I have to check if n plus m mod 2, right? If n plus m mod 2 equals to 0, if it is even, then I have to return basically A of max. So basically I have to return max of A of mid comma B of partition, right? The max of these two plus the minimum of A of mid plus 1 comma B of partition minus 1, right? And I have to take the average of these two. So I will add these two up and I will divide by 2. Right? That's a very long line, but I hope that it makes sense. Right? That is the case when my number of elements is even. On the other hand, if the number of elements is odd, then this is very simple. Right? I simply return. So I can simply return over here the max of A of mid and B of partition. All right, we can simply return the max of A of mid or B of partition. So this will basically be the code for finding the median of two arrays. Now there's one bug over here. Can someone catch that bug? This code is not entirely correct. There is one very, very crucial bug over here. And that bug is basically, let us suppose that I was searching in this array and I was searching in this array. Right? Suppose that while searching this array, either my midpoint became n minus 1, or if my midpoint became 0. Right? Then what do I compare? I don't have anything to compare, right? If my midpoint is this thing in -1, then I can't compare a of mid plus 1 with anything, right? I can't really compare a of mid plus 1 with anything. Yes or no? So for that, to handle that, we can very simply, we can virtually append infinity and minus infinity to the left and right of both the arrays. All right? Yes, exactly. So Jay, even in that case, if the first array is only of size 1, so we will very quickly exhaust the mid. We will very quickly exhaust the mid. So to handle that situation, to handle that boundary case, we need to add infinity and minus infinity on the right and left side of both the arrays. All right? You don't have to actually append it. You can treat it virtually. Right? You can treat it virtually. Is that clear? Yes, आज कुछ ज़्यादा हो गया. Well, I mean, I would recommend that you actually try and code this up. When you try and code this up, this will, so I understand that you won't be able to, you will have to get practice on this. You will have to actually try and code this up to properly understand this. Right? But I hope that the intuition was clear. The code might not be clear to you, but I hope that the intuition was clear. Right? Cool. So now what will be the time complexity of this overall algorithm? What will be the time complexity of this overall algorithm? Yes. So we are doing a binary search, right? We are doing a binary search over what? We are doing a binary search over the smaller array. Right? We are doing a binary search over the smaller array. So what will be the time complexity? It will be order of min. So it will be order of log of min of n comma n. All right? It will be order of log of min of n comma n. Is that clear? Yes, Himadari, there are a lot of edge cases over here. So we always have to take care of the edge cases. I mean, the solution is very elegant, but the code only becomes difficult because of all the edge cases that you have to handle. All right? Tushar says, how are the corner cases rectified? The corner cases can be rectified by just adding a minus infinity to the left of both the arrays and a plus infinity to the right of both the arrays. All right? Basically, you can say that you have 4 values over here, right? You have 4 values over here. You have A, B, and you have C, D. You have these 4 values over here. Well, what if this midpoint was equal to n minus 1? In that case, if that is the case, then there is no A of mid plus 1, right? There is no A of mid plus 1. So what value should you consider instead of B? There is no B. B does not exist, right? So what value should you consider instead of B? You should consider infinity. Similarly, this value over here, if this is partition and this is partition plus 1, right? If there is no D element over here, then you should consider infinity in its place. Similarly, on the left hand side, if mid is 0, then on the left hand side you should consider minus infinity, and same for partition. Is that clear? So once you actually try to code this, things will start making sense. I don't want to give you the exact code right now, because then it will defeat the purpose of us trying to solve these questions. All right, you actually have to code this yourself, struggle a little with the edge cases, and once you figure this out, things will become clear. All right, cool. So let us move on then to the next question. Right. So the question goes something like this. That we have an unsorted array. Right, of size n. All right, and this array only has positive integers. Right? We have an unsorted array of size n, and this array only has positive integers. Now we have been given a value. X, right? And we have to find the largest value of k. The largest value of k, such that no subarray of length k has sum greater than or equal to x, or let us say just sum greater than x. Right? So that's a mouthful. Basically, what we are saying is Suppose that we have some array with some elements. Right? We have some array with some elements, and we have been given a number x equals to 10. Right? Let me also give this array. So this is a 1, 5, 6, 2, 0, 1, 3, 5. All right, let us say this is my array, and I have been given some x equals to, let us make this a little smaller, perhaps x equals to 6. Right? Now we have to find the largest window size. Right? K is the window size. We have to find the largest window size such that in that window there is no window that sums up to greater than 6. Right? There is no window that sums up to greater than 6. So in this case, what will be the answer? In this case, what will be the answer? Is the question clear? So if I make a window of size 1, this or this or this or this or this or this, then is the sum ever going to be greater than 6? Is the sum ever going to be greater than 6 if I have a window of size 1? No, right? So window of size 1 is valid. Right? Window of size 1 is valid. Size 1 is valid. Right? On the other hand, if I have windows of size 2, let us say this window, right? What is the sum of this window? The sum of this window is 6. Right? So 6 is okay. What is the sum of the next window? 5 plus 6. The sum of this is 11. Well, 11 is greater than 6. Right? 11 is greater than 6. So this window is not okay. And because this window is not okay, the window of size 2 is not valid. Right? Windows of size 2 are not valid. Is that clear? Okay. So we know that a window of size 2 will give me a sum greater than 6. So should I try a window of size 3 or above? Should I try a window of size 3, size 4, size 5? Yes or no? I should not try them, right? There is no point in trying them. Does everyone agree? Yes, because we have to find the largest window such that the sum of any subarray of that size must be less than or equal to this summation value over here. Right? Let us take another example, perhaps. So let us take one more array. So suppose this array is 1, 0, 3, 6, 4, 2, 7, 0. Right? And let us say that x equals to 13. Right? Let us say that x equals to 13. Okay. Now what is the largest window? What is the largest value of k such that no window of size k has sum greater than 13? Right? So does k equals to 1 work? Does k equals to 1 work? If I have windows of size 1, then is the sum going to be greater than 13? No, right? So windows of size 1, they all have sum less than 13. Right? So windows of size 1 are valid. Right? Every window of size 1 is valid. So size 1 is valid. This is valid. All right. What about windows of size 2? What about windows of size 2? Well, this has a sum of 1. This has a sum of 3. This has a sum of 9. This has a sum of 10. This is 6. This is 9. This is 7. Right? All the sums were less than or equal to 13. So windows of size 2 are also valid. All right. Let us try increasing the window size further. K equals to 3. All right. Now what do my windows look like now? My windows are, so this is my window, first window. Right? What is the sum of this? It is 4. Then this is the second window with some 9. This is the third window. Right? This has some 13. This is the fourth window. This has some 12. This is the fifth window. What is the sum of this fifth window? This is still 13. This is the last window. This has some 9. Right? So still we see that window of size 3 is also valid. Is that clear? Window of size 3 is also valid. All right. Let us try to increase it further. So let us try k equals to 4. All right. Now what is the size of what is the sum of this? That is 10. What is the sum of this? That is 15. Right? The sum of this particular window is 15, and 15 is already greater than 13. 15 is already greater than 13. So windows of size 4 are not valid. Is that clear? And because windows of size 4 are not valid, windows of size 5, windows of size 6 will also not be valid. Right? All these will not be valid. Is that clear? Yes, is that clear? So if this is my array, if this is the input array, and this is the value of x that has been given to you, then what value of k should you return? What value of k should we return? We should return k equals to 3. Right? We should return k equals to 3 because we have to return the largest largest size of window so that no window of that size has sum greater than x. Is the question now clear? Yes, is the question now clear? All right. So how can we approach this particular question? How can we approach this particular question? So guys, whenever you come across a new question, don't try to come up with the optimized approach right away. Right? Come up with the most brute force approach. Right? First, try to solve the question. Once you have solved the question, then you can try to optimize it. Right? Because some solution that works but is slow, some solution is always better than a fast solution that you never find. Right? So having some solution at least is better. Right? So let's think of a brute force approach first. Yes, so what can we do? All right. So let us look at two questions. Suppose I have a guess. Right? Suppose I have a guess for k. All right. Suppose I say that k equals to, let's say, 5. Right? Suppose I have this array and I have been given a value of x, let's say 20, and I am guessing that k equals to 5. Then how can I verify? How can I check it? How can I check it? I have to consider every possible window of size 5. So how can I do that? I can either do two nested loops. So I can either say for I equals to 0 all the way till n minus 5 minus 1, right? For j equals to 0 till 5 minus 1, right? And then I can say sum plus equals to a of j, a of I plus j, right? And initially sum equals to 0, right? So doing this, what will this do? This will give me, so over here. I will have to say sum equals to 0 over here. So basically, after this inner loop, in each iteration of this inner loop, I will have the sum of one window. Right? I will have the sum of one window again and again. So I will have to check if sum is greater than x, then return that window size is invalid, right? K is invalid. Right? After this entire thing is complete, I can say that k is valid. Right? So given a window size k, this is how I can check it. Yes or no? That seems like a very, very difficult approach to do, right? So can we simplify this a little bit? How can we do that? So are you guys aware of prefix sum? Suppose that this is my array. And I want to find the sum from some start location to some end location. Right? If I want to do many queries of such form that find the sum of all these different elements, then how can I do that efficiently? I can calculate the prefix sum of the array. Right? Let us say that this is the array A, then the prefix sum of array A will be P of A. Yes. Now, if I were to tell you to calculate A of I plus A of I plus 1 or plus A of I plus 2 plus all the way till A of j, then how can you express this in the form of prefix sum? Well, this is simply equal to what? P of j minus P of I minus 1. Yes or no? Is that clear? Yes or no, guys? Alternatively, you can also rewrite this as P of j minus P of I plus A of I. Right? You can also rewrite this as this. They are the same thing. All right. So once I have this prefix sum, if I tell you that find me the size of window of size 5 starting from this location I. Right? If I ask you to find the sum of this window, then how can you do that? How can you do that? You can very simply do what? You can simply do prefix sum of I plus k minus prefix sum of I minus 1. Yes or no? This will give you the sum of this window, right? And to go over all possible windows, you can just write a loop for I equals to 0 all the way till n, right? n minus k basically. Yes. So that is the first thing that we can do to make our sliding window calculation a little simpler. Right? We can store the prefix sum. But the thing still comes that, all right, given a value of k, I can check if it is correct or not. But how do I find the value of k? How do I find the value of k? Currently, the approach that I have is start from k equals to 1 and try increasing it. Right? Try increasing it one by one. Right? If I do that, then what will be my time complexity? What will be my time complexity? I will have a loop for k. This will run for order of n time. Right? Then I will have a loop for checking k. This will also run order of n time. So my total time complexity will be order of n squared. Yes. Of course, I also have to consider the complexity of the prefix sum. But calculating the prefix sum is just order of n pre-computation. Right? Pre-computation. So this is actually order of n squared plus n, which is just order of n squared. Right? This is my naive. This is my brute force algorithm. All right. Can we improve this? Can we improve this? So Teju says that we can use binary search, right? But what should we binary search over? Teju, what should we really binary search over? Yes, so Prakash says that we can binary search for the value of k. So we are going to binary search for the value of k itself, right? So what is the minimum possible value of k? What is the minimum possible value of k? What is that? What is the minimum possible value of k, guys? It is 0, right? It is 0. Basically, if sum a of I itself is greater than x, then I can't have a window even of size 1. Right? In that case, the value of k will be 0. On the other hand, what is the maximum possible value of k? Possible value of k, that is n. Right? If I take if the sum of the entire array is still less than x, then that is the maximum possible value of k. So what I have to do is I have to binary search in this search space. So I can say low equals to 0, high equals to n, while low is less than equal to high, right? I will say mid equals to low plus high by 2, right? All right. Now, once I have the mid, what should I do? I should check window of size mid. All right. I should check window of size mid, and I will have another function over here. Check window, right? That takes a value of k and returns true or false. Right? This check window is going to do exactly this. So it is going to loop. It is going to say for I equals to 0 all the way till n minus k, right? If the prefix sum of I plus k minus prefix sum of I minus 1, right? If this is greater than x, if any of this sums is greater than x, then return false. Right? Otherwise, return true. Right? If all these windows are valid, then return true. Right? This is the check window functionality. Is that clear, guys? Cool. So we have a function for check window now. So what can we see over here? So if I check window of mid and this comes out to be true, if check window of mid comes out to be true, then what can I say? If a window of size k works, then can I return this? If a window of size k works, then can I return that window size as the final answer? Yes or no? No, I cannot. Because yes, this works, but this might not be the largest value that works. I have to find the largest value that works. Right? So if this is the case, then I have to increase my low. So I will say low equals to mid plus 1, right? Mid plus 1. On the other hand, if this does not work, then I have to decrease my value of k, right? So else I will say high equals to mid minus 1, right? High equals to mid minus 1. Well, when do we stop? When do we stop? So we can either stop when this loop exits, or we can explicitly check. We can explicitly check that k works, but k plus 1 does not work. Right? If that is the case, then we can simply return. Is that clear? Even if we don't do that, that is fine, because this loop will automatically take care of it. Is that clear? So we will return when we find a position of k which works, but the immediate higher position, right? K works, but k plus 1 does not work. That will be our correct answer. Is that clear, guys? So after this loop, after this while loop is over, I can simply return what? What can I return? So this will exit when low will become greater than high. Right? Low will become greater than high. How will it become greater than high? When I would just do low equals to mid plus 1. Okay, so I can just return low over here. Right? I can just return low over here, and that will be my size of the window. All right, cool. So what will be the overall time complexity of this algorithm? What will be the overall time complexity of this algorithm? So let us take this step by step. How much time does check window take? How much time does one function call to check window take? This is simply a for loop. Right? This takes order of n time per call. Right? This takes order of n time per call. Well, what about this thing? This is log n search. Right? This is log n search. But inside this log n search, we are doing this order of n call every time. Right? Inside this log n search, we are doing this order of n call every time. So basically, the time complexity will be order of n times log of n. Yes, order of n times log of n. Well, we also have to consider the prefix something. So this is for the prefix sum. This is for the binary search. Oh, sorry. This is for the binary search. This log n thing. This is for the binary search, and this is for check window. Right? So the overall time complexity is just order of n log n. Is that clear? All right. So let us end the class at this point. Bye-bye. Have a good day. Hello, everyone. So we are back again with another class. All right. So today's topic is once again binary search. So we have been studying binary search in the past 2 lectures. Right. So if you have not watched those past 2 lectures, please go and watch them. So let us continue with some more advanced problems on binary search today. All right. Let me just share my screen. I hope that everyone can see the screen. All right. So let us start with a question that you might have seen earlier. Right. It is a pretty famous question. And you might have seen this in the arrays, 2D arrays class that we already had. Right. But this question is relevant to binary search, so let us quickly see it here once again. Question goes something like this. You have been given a matrix. I mean, this is not that matrix movie thing. This is a matrix. It's a 2D array, right? Now, this matrix can have a certain size. Let us say that the size is n cross m, right? Now, this one property in this matrix that each row and each column is sorted, right? So let us quickly take an example of what such one such matrix would look like. So suppose we have 10 over here, 20, 30, 40, 50, right? All right. What other numbers can we choose? So let us suppose that we have 15, 25 perhaps, 35, 45, 55. Something else, maybe 27, right? 29, 37, let us say 48, and let us say 60, right? So let us just add quickly one more row. So suppose this is 32, and suppose this is 40, suppose this is 51, suppose this is 60, and suppose this is also 60, right? So we see that in this matrix, every row individually is sorted, right? Every row individually is sorted, and so is every column. so is every column, right? Cool. All right. Now, what is the size of this particular matrix? Well, over here we have 4 rows, so n equals to 4, and m equals to, we have 5 columns, so m equals to 5. So this is a 4 cross 5 matrix, right? Now we have been given an integer. We have also been given an integer k. Right? So k stands for key. We have been given a key, and we have to search this key. We have to search this key within the matrix, and we have to return. We have to basically tell whether the key exists or not. Key exists or not. Fair enough? Yes? All right. So Rahul has a question over here. Rahul, I guess, is talking about the assignments that were given in the last class. Rahul says that 5 questions in 24 hours is kind of aggressive. Right? So Rahul, you do not have to attempt those questions in 24 hours. Right? So unlike when you are enrolled in Skiller Academy, you will have a lot of guidance. You will have mentors, you will have TAs that will be helping you while you're working through the assignments. Right? We will have remedial classes a lot. When we are on YouTube, we just want to give you as many assignments as we can so that you can practice on your own time. Right? So it could be the case that yesterday, after taking the class, you were able to solve 2 of the problems. Now, maybe 5 days later or 10 days later, you want to come back and try it again. Right? So we just want to make sure that you have some new problems that you can still attempt. All right? So do not worry about the time constraint. This assignment is not timed. Right? So feel free to take this assignment whenever you want, how many times you want. So it doesn't really matter. Okay? Just the assignment is just to make sure that you can practice a lot. Perfect. So yes, Shazia is saying that this question has been done in the previous class. So we are going to very quickly move through this question, all right? But this is kind of important for binary search as well. So as you guys already know that this is binary search question. So let us just quickly recap this, all right? Perfect. So this is the question. You have been given a matrix of size n cross n. Each row and each column is individually sorted. Given a key, we have to find whether this key exists in this matrix or not. Yes. Perfect. So what approach do we have? Well, one of the brute force approaches. So whenever we have a new problem, we try to come up with a brute force approach. Brute force approach, right? In a brute force approach, we will not be using any extra information that we are given, right? So what will be the brute force approach? We simply try to linearly, so linear search. If we search through the entire matrix in a linear manner, then how much time is it going to take? What will be the time complexity? Well, how many elements are there? There are total n cross m elements. We are doing a linear search, so it will be the complexity, the amount of time it will take us for linear search will be order of n cross m. All right, but we can optimize, right? We know that each row and each column is individually sorted. Interesting. Well, let us just worry about the rows for now. So we know that because each row is sorted, we can binary search. Inside each row. Is that correct? So if we binary search, let us call this binary search 1. If we binary search inside each row, then how much time is it going to take us for every row? Well, there are m elements. Well, there are m elements in a row, right? There are n rows and there are m columns. So every row has m different elements. So if we want to binary search among m elements, it will take us log of m time. Right? This is for one row. Now we have to do this for all the rows. How many rows are there? N different rows. So it will take us order of n times log m time. Yes, do you guys agree? On the other hand, if we basically, so this is on the rows. If we binary search number 2 on the columns, right? Then it will be very simple. So it will be m times log of n, because now we are searching within each row, right? We are searching within each column. And how many elements are there in a column? Well, equal to the number of rows. So we can search through a column in log n time, and we have m columns to search through. right? So if we search through just the rows, we will get this complexity. If we search through just the columns, we will get this complexity. The question is, can we do better, right? Now, this might not be obvious from the question itself. We have already tried binary searches, right? We have already tried binary searches, but binary search is not always about this binary property. So just because you are saying binary, that does not mean you always have to split the array into half, right? That is originally what binary search means. But binary search has a more important concept, more important underlying concept. And the concept, as we discussed in the previous classes, is what? The concept is that given a search space, when you make a guess, you are able to eliminate a large part of that search space, right? So every guess allows you to eliminate a large chunk of the search space. Perfect. All right. So that's fair enough. So how can we basically do that? How can we basically do that for this particular question? Well, we can observe. Let us suppose that we are looking at this particular element. Let us just pick any random element and let us say that we are looking at this particular element. Right. Then if we determine that given our key, right? Let's say that we compare this key with 45. Suppose that the key is less than 45. Right? Suppose that we are looking for an element like 29. 29 is less than 45. Right? Then what can we know from here? This key was less than 45. So can this key be over here? Can this key be in this area? No, right? This key cannot be in this area. Why? Why can it not be in this area? In fact, this particular area, because this key is less than 45, and everything in this area, everything over here in this area is already greater than 45, right? So the key cannot be over here. Similarly, so I can reduce my search space, right? I can reduce my search space by a large chunk. This might be a large chunk. Now there's one more property that we get. If we move in a particular order, right? Suppose that we are starting from the top right, then we can also eliminate some more rows or some more columns. Right? So we will see that we will be able to eliminate this top row as well. Right? So over here, there's nothing binary over here. Right? We are not really splitting the search space into half. However, what we are able to do is we are still able to eliminate a large chunk of the search space with every guess. Yes, so Dev has a nice name over here. Dev is saying that we can call this staircase search, right? And yes, Tushar also points out one thing. So Tushar says that this has already been discussed in a previous class. So yes, it has been discussed in the array class. However, it is important enough to bring up again in the binary search class, right? Just to stress the point that binary search is not just always about binary search, right? You can still do sort of a binary search on even though you're not splitting the data into half, right? So very quickly, how can we do the search now? Suppose that we start from the top right. So once again, let us assume that the key we are looking for is 29. We are looking for the value 29, and 29 happens to be over here, right? So we better reach this point. But for now, we don't know where the key is. So let us start from the top right. And we will compare 29 with 50. 29 happens to be less than 50. Since 29 is less than 50, what can I eliminate? What part of my matrix can I eliminate? So where can 29 definitely not lie because of this comparison that I have just made? I know that in this particular column is sorted, right? So over here, in all this column, every element is greater than 50, equal to 50. And we already know that 29 is less than 50. So my key cannot be in this column, right? My key cannot be in this column. So I can eliminate this column. Do you agree? Yes. All right. Once I have eliminated the column, now I have a different matrix, right? The matrix exists only up till this column, right? So what is the top right part now? What is the top right part of the matrix? It is this particular cell. All right. Let us compare once again. So we know that 29 is again less than 40. So once again, by the same argument, since this column is sorted, then 29 cannot be in any of these elements because we know that 29 is less than 40. So let us very quickly eliminate this column as well. Perfect. Let us move on to the next top right element. So this is 30. 29 is still less than 30. By the same argument, we will be able to eliminate this particular column. Does that make sense? Yes. Let us continue. So now the top right element is 20. Right? 29 versus 20. What is it? So 29 is greater than 20. Well, now a different argument appears. Let us look at the different argument. So we know that 29 is greater than 20. Right? So if we look at this particular column, if you look at this particular row, we know that everything to the left of 20, everything to the left of 20 over here, in that same row, right, that has to be less than 20. Everything to the left of 20 has to be less than 20 because the row is sorted. So 29 cannot be over here. So what we can now do is we can eliminate this particular row. We can eliminate this particular row. And notice that these columns have already been eliminated. Right? We move on to the next top right element. So 25 is the next top right element. We compare once again. 29 happens to be greater than 25. So by the same argument, we can eliminate this row. Then we move to the next top right element, which is 29. And now we can return yes, we have found 29 and 29 exists in our matrix. Is that clear? Yes. So we are not doing binary search. We are kind of doing a staircase search, right? We are zigzagging around. So in this particular case, we moved along this path. We moved along this path. There's nothing binary about this, but this is still an example of binary search. Is that clear? Cool. Now very quickly, what will be the time complexity? Time complexity of this approach. So we have already seen that linear search takes this much time. Binary search will take either n log n time or m log n time. What about this particular approach? Well, for this approach, we have to go from the top right corner, in the worst case, to the bottom left corner. Right? From the top right corner to the bottom left corner. And the path does not matter. The path does not really matter because in both the cases, we will be covering n different rows and m different columns. Right? So our total path length is equal to n plus m, irrespective of what paths we take. Right? Either we go this way, or we directly go over here, or we maybe take this weird way. Right? All these cases have the same path length of n cross m, m plus n. So the time complexity will be order of n plus m. Is that clear? So this was a repeated question, but this was still very simple and very relevant to binary search. Let us move on now. So we very quickly saw this question. Let us move on to the next question. So Animesh over here says, can we rewrite this? So Animesh says that, okay, perhaps we can also rewrite this as order of max of n comma m. And that is true. That is true. So as we saw in the very first class on time complexity analysis, we saw that we can rewrite this part as max of n comma m. Right? Because asymptotically, these complexities will turn out to be the same. They are related by a constant factor of each other. All right? Perfect. Moving on, let us see a more challenging question. So this question is very famously called aggressive curves. Aggressive curves. I think this question was originally from the platform Spoj, right? And this question is very, very common. I mean, this question happens to be one of the favorites for all the companies. So this question has been asked numerous times at Google. This question is still asked very frequently at places like DirectTime and Amazon. And this is a very, very nice question. Right? The special thing about this question, as you will see, is that it has a very nice solution using dynamic programming as well. But it can also be solved using binary search. Right? So a lot of the times when a student goes to an interview, they are expecting a difficult interview question. Right? A lot of the students are afraid of dynamic programming, even though dynamic programming is pretty easy. Right? So whenever they see this question, the natural approach, the natural idea that comes to their mind is, okay, I can try dynamic programming on this particular question. I mean, of course, dynamic programming solves this question, but binary search solves this in a faster manner. Okay? So let us quickly see the question. The question goes something like this, that you have n different stalls. You have n different stalls. Right? And the stalls, so let us say n is greater than 2. You have n different stalls. So you have more than 2 stalls. And you have C cows. Right? Once again, C is going to be greater than 2. There's one constraint over here that C is less than or equal to n. Alright? We have n different stalls and we have C different cows. Now, you have been given the location of these stalls. The location of these stalls has been given to you. So let us say that we have 4 stalls, right? N equals to 4. And the location of these stalls are 1, 2, 5, and 8. All right? Or let us say make this n equals to 5. Let us just add one more. And 1, 2, 5, 7, and 8. What that means is that the first stall, the 0th stall, is at location 1. The first stall is at location 2. The second stall is at location 5. Third stall at location 7. And fourth stall at location 8. Right? So you can try to imagine this, that this is one stall, this is the other stall, this is the third stall, this is the fourth stall, and this is the fifth stall. And if this is at 0 meters, then perhaps this stall is at 2 meters, then this stall is at 5 meters. Right? This stall happens to be at 7 meters, and this stall happens to be at 8 meters. So they are unevenly spaced. Right? These stalls are unevenly spaced. Now we also have C cows. Right? Suppose for this example, we have 3 cows. Right? C equals to 3. So now our task is to place these cows. Our task is to place these cows into the stalls. And one cow can only go in one stall. So I'll just draw the cow as a circle. Right? Cows are not sphericals. So, I mean, if you were a physicist, then you would say that, okay, cow is you would consider a spherical cow in vacuum. Right? But we are not physicists over here. So let us just consider this cow in this particular stall. Right? So I can put this cow installed in many different ways. If I have 3 cows and I have 5 stalls, if I have 5 stalls and I have 3 cows, then very quickly, can someone tell me what is the total number of ways I can put them? What is the total number of ways I can take 3 cows and put them in 5 stalls? Well, that will simply be 5 choose 3. Right? I have to choose 3 stalls out of 5 stalls to put the cows in. And oops. So let us go back. Sorry about that. Right? And if the cows are distinguishable, then I will also have a 3 factorial factor coming. Right? That depends on whether the cows are distinguishable or not. Right? Perfect. So suppose I put the first cow over here in this stall. I put the second cow over here in this stall, and I put the third cow over here in this stall. Right? Now, the cows are aggressive. They want to fight with each other. Right? So we want to maximize the distance between the cows. Right? Now, but there are multiple differences, right? So there's one distance between this cow and this cow. And there's one distance between this cow and this cow. So which distance are we trying to minimize? We are trying to maximize the minimum distance. The minimum distance between any 2 cows. Right? So let us suppose that this distance is 6 and this, so let us not suppose that this is 6. Let us just calculate. So this is at 2 meters and this is at 7 meters. So this distance will be 5 meters. Right? Similarly, this is at 7 meters, this is at 8 meters. So this distance is 1 meter. Right? Now the minimum distance among these two is 1 meter out of 5, and 1 is minimum. So we are saying that this is the minimum distance between 2 cows in this particular arrangement. We want to maximize this distance. We want to place the cows as far apart as possible. All right. And this distance, mind you, this distance is not in terms of the stall number. This distance is in terms of the location of the stall. Right, so we have 2 things over here. We have the 0th, first, second, third, fourth stall. We have the stall number. That is not what we're talking about. We're talking about the distance in terms of the location of the stall. Is the question clear? Yes. So very quickly, what do you think should the answer for this particular case be? Suppose that this is the arrangement. I have stalls at 0 meters, 2 meters, 5 meters, 7 meters, and 8 meters. And I have 3 cows. Then where should I put these cows? Where should I ideally put these cows to maximize the distance? Yes, the first cow should go in this particular stall. The first cow should go in this particular stall. All right. Then I can put the second cow in this stall, and I can put the third cow in this stall. Is that clear? Yes. So this will be the ideal case. And what will be the final distance? The distance will be, so the distance between these two cows happens to be 5 meters. The distance between these two cows happens to be 3 meters. Right? And the minimum of those distances is 3 meters. So we are making sure that the cows are 3 meters apart from each other. Any pair of cows is 3 meters apart from each other. All right? Perfect. So now the question is that given you have been given N, you have been given C, and you have been given the location of these N stalls. Right? And you have to tell me what minimum distance can you achieve? Can you achieve by placing the cows as far apart as possible in the different stalls? I hope the question is clear. So basically, if this is the input, you have to give me the output 3 meters. Right? You have to give me the output 3. All right. Now, how will we do this? How can we do this? So once again, let us start with a very, very brute force approach. The brute force approach would be to try all possible arrangements of the cows. Right? Try all possible arrangements. So as we just saw, so are the cows distinguishable in this particular case? Does it really matter what the first cow, second cow, and third cow is? No, it does not, right? All that matters is what stalls they are in. So over here, how many possibilities do we have? We have 5C3 possibilities, right? Or basically, we have N choose C possibilities, where N is the number of stalls and C is the number of cows. So if we do this brute force, we will check each of the possibilities, and then for each possibility, we will find the minimum distance. Right? We will find the minimum distance. So what will be the overall time complexity of this brute force approach? It will be order of N choose C times. So once we have chosen an arrangement, we still have to calculate. So let us say that we have several stalls and we have chosen to put one cow here, and one cow here. That is not done, right? We still have to measure these distances and find the minimum distance between any pair of cows. So that will take us an additional of order of N time, because we have to go through every pair of cows, right? The total of time complexity will be N choose C times N. Well, how big is N choose C? Can someone tell me how big N choose C is in terms of ON complexity? So what polynomial, N to the power what will it approximately be? This is the same as N to the power C, right? N choose C is the same order as N to the power C. Yes, no? Yes, no? Well, not really. Not really, because binomials flip. From the midpoint, the binomials flip. Right? So we are assuming, so this is if C is less than N by 2. Right? C is less than N by 2. So we can rewrite this as, so let us not write this complex expression. Let us just keep this as N choose C times N. And this is in the worst case. In the worst case, this is equal to order of N to the power C times N. Right? Now, if C is very big, if the number of cows is very big, this complexity is perhaps not that big. Right? If there are 10 cows, then you will have to spend N to the power 10 times. That is very, very bad. Right? So let us try to optimize this approach further. Let us try to optimize this. Okay. So those of you who are familiar with dynamic programming, what would you try to do over here? What would you try to do over here? So anyone who is familiar with dynamic programming would say this, that all right, I have several stalls and I have some cows. Right? I have several stalls and I have some cows. That is simple, right? For every stall, I have to make a yes/no decision. I have to make a yes/no decision whether to put this cow in there or whether to not put this cow in there. Right? So people would try to apply DP over here and say that, okay, for the first stall, I can choose whether I'm going to put the cow in or I'm not going to put the cow in. Again, for the second stall, I'm going to choose whether to put the cow in or to not put the cow in. Right? And so on and so forth. I will build my choices. And by DP, I can finally find the answer. Well, that is perfectly valid. Right? That is perfectly valid. And if you do that, your complexity will turn out to be order of N squared. which is not bad, right? Which is definitely better than order of n to the power c times n, right? But we can do better. But we can do better. So the moral of this story is that even if you have come up with a solution, it is still worth checking if the solution can be optimized or not. All right. Now let us dive into the most optimized approach, which will be using binary search. Binary search. Perfect. So if we are supposed to use binary search, we have to have a search space. We have to have a search space. We basically have to decide what we are searching for. What are we really searching for over here? Can we search for the location of stalls? Can we search for the location of stalls? That doesn't really make sense, right? Because we have to consider multiple stalls and there are multiple cows. So how it doesn't really make sense to search for the location of a particular stall. What we can search for is the answer itself. We can search for the answer itself, right? So what is the answer over here? The answer is the minimum distance. The answer is the minimum distance. And we are trying to maximize this particular answer. Minimum distance between any two cows. Between two cows. All right. So now that we have figured out what we have to search over, let us quickly discuss the bounds. Let us quickly discuss how large this search space is. So what is the minimum value for this minimum distance? What is the least possible distance that we can achieve? What is the least possible distance when we can achieve? Well, if every stall, if we are forced to put one cow in every stall, and every stall is 1 meter apart, right? So they're just next to each other. They're just next to each other. Then the minimum distance will be just 1. Do you agree? Can the minimum distance be 0? Can the minimum distance be 0? Not really, right? Not really. What is the maximum possible distance that we can achieve? What is the maximum possible distance that we can achieve? Well, this is my first stall, right? This is my 0th stall is at location 0, all right? And let us say my nth stall, my n minus 1th stall, right? Let us say it is at location, let us say L, all right? And I have to place C cows. I have to place C different cows within this distance. So in the worst case, I mean, even in the best case, doesn't matter how the stalls are arranged, can I achieve, what is the best distance that I can achieve? If all the stalls are equidistant from each other, then I can simply place the cows one in each of them, right? And then basically my distance will be L by C, right? This is the maximum possible distance I can achieve. Can I achieve more than that? Can I possibly get more than that? No, because once I have placed the cows at equidistant locations, if I try to move any cow to the left or right, then the distance between the previous cow or the next cow, this decreases. Right? And we are supposed to consider the minimum distance between any pair of cows. Right? Minimum distance between any pair of cows. So the maximum possible distance that we can achieve possibly is L by C. Right? And what is L over here? L is simply the maximum of the array, right? So let us consider that these distances are given to us in the array, right? So this location of the stalls, this has been given to us in array of size n, right? So this is simply max of A, right? Max of AL for all n. So we now have the bound. We now know that we are supposed to look for a value in this search space. This search space goes from 1 all the way till max of A of I. All right. Now, what else is required for a binary search? So now that I have a low and a high, I will calculate a mid, and this mid is going to be my guess. Okay, this mid is going to be my guess. Now I have to check. Now I have to check several things. I have to check, is the guess perfect? Is the guess valid? And is this the correct answer? That's one thing I have to check. Or I have to check, is the guess too low? Or I have to check, is the guess too high? Because only if I know all these 3 things, only if I know the answer to these 3 things, only then can I adjust my search space. Do we agree? Yes, exactly. We need a proposition. Right? If I don't have these three values, I will not be able to figure out in which direction should I move in the search space. All right. So let us quickly look at how we will do that. So suppose that I tell you, suppose that you have been given this array A of n, size n, and this is the location of stalls. Location of stalls. And I am telling you that, okay, you can achieve a distance. You can achieve a distance of, let us say, 5 meters. Right? We have to verify whether this is true or not. So how will we verify that? How can we verify that? Well, this is very simple, right? This is very simple. What we can do is, so let us suppose that these are the stalls, right? And let us suppose that this is at location 0, this is at location 5, this is at location 7, location 11, location 16, location 23. Let us suppose this is how the stalls look. So what we can do is, we can place the first cow in here. Right? We can always place the first cow in the first stall. Then we can move on to the next stall and we can check what is the current distance. What is the current distance? Is that distance greater than or equal to 5? Yes, it is, right? So we can safely place the next cow over here because we are trying to achieve a distance of at least 5. We're trying to achieve a distance of at least 5. All right, then we can move on. So when we want to put the third cow, we will come to the next stall and check. Is the distance from the previous cow greater than or equal to 5? So is 7 minus 5 greater than or equal to 5? No, it is not. Right? So we cannot, if we have placed the cow in this stall and we are trying to achieve a distance of 5 meters, then we cannot put the next cow in this stall. All right. What about the next stall? Well, the distance from 5 till 11 is 6. So we can safely place the next cow over here. Does that make sense? Moving on. So we can definitely place the next cow over here. And we can also place the next cow over here. Right? So we can place the cows in this particular bag. Now, if we are able to place all the cows, successfully, right? So remember that we have C cows, right? If we are able to place all the C cows successfully, then what can we say about this particular guess? What can we say about this particular guess? Is this the correct guess? Not necessarily. Right? This is a valid guess. This is a valid guess. But we are supposed to maximize this guess. Right? So this is a valid guess, but this might not be the maximum value. So we have to continue searching. We have to continue searching with larger values. Right? We have to continue searching with larger values. Suppose that we were not, so if we were able to place it, then we have a valid distance, but the distance can be higher. All right. What is the other possibility? The other possibility is we were not able to place all the cows. Right. For example, suppose over here, let us suppose that my guess distance was. So let me just erase this. So let us say that my guess was that, okay, I can achieve a distance of 10 meters, right? And let us suppose that I had 3 cows to put. So I will try to put the first cow in this first stall. Then I cannot put the second cow in the second stall or in the third stall. I will have to put the second cow over here, right? I will have to, in this case it will work. So let us just say that we had 4 cows. Let us say that we had 4 cows. So I will put the second cow in this stall. Then I can't put the third cow here. I can put the third cow here. So I will put the third cow over here. Now where do I put this fourth cow? I cannot possibly put the fourth cow because I have exhausted all my stalls. Right? So in this case, we see that we had a guess of 10 meters distance and we tried to place the 4 cows, but we were not able to place all the 4 cows. We were only able to place 3 cows. So that means that my guess is incorrect. Right? That means that my guess is incorrect. Is there anything else that I know? I know that my guess is too high. Right? If 10 meters did not work, then 12 meters or 20 meters or 50 meters will also not work. Right? My guess is too high. I have to reduce my guess. Does that make sense, guys? Yes? So what we are essentially doing is, we are saying that let us initialize the low as 1, the high as L by C. So this is maximum of A of I, right? So maximum of A of A is just the last location, the location of the last term, A of A dot length or n minus 1, right? A of n minus 1 by the number of cows, C. Then while our low is less than equal to high, right? What we will do is we will calculate a mid. So our guess is the mid, which is simply low plus high minus low by 2. Do you agree? Now we have to verify the guess, right? So if works, right, if this array for this number of cows, for this value, for this guess, if this works, so we will write this function works. But if this works, then what can we say? If this particular thing works, then what can we say? We can say that, hey, this guess is valid, but it might be too low. Right? This guess is valid, but we could do better. Right? So we have to increase. We have to increase our guess. Right? How will we increase our guess? We will say low equals to mid plus 1. Right? But this guess worked. Right? This guess worked, so we must also save it. This was the largest guess that worked. So let me also save a variable over here, largest working guess, right? Let me save a variable over here, largest working guess, and this was initialized with, let's say, 0 or minus infinity, whatever you want. And I can say over here that largest working guess equals to maximum of my guess, my mid. So it is maximum of mid, the current guess, comma the largest working guess. All right, I can make sure that whenever I have a valid guess, I save the largest of those valid guesses. Is that clear? On the other hand, if this does not work, then I have to adjust my high. High equals to mid minus 1, right? And at the end of this loop, when this loop is through, I can simply return whatever maximum guess I have found so far. So largest working guess. Does that make sense, guys? Does this binary search make sense? Yes? We still have to write this function, right? We still have to write this works function. Well, this function is very simple, as we saw. How will this function work? So we have to write works. This will take an array. This will take the number of cows. This will take the number of cows, and it will take a guess. So what will we do? We will start from the location first, right? We will say that the previous stall equals to 0, right? We will place the first cow at location 0. Now, how many cows do we have to place now? So for I goes from 1 till C minus 1. Right? We have already placed the 0th cow. Now we have C minus 1 cows remaining to place. Right? So we will go over each cow, and then what will we do? Right? We will try to place the cow in the next stall. So we will also, let me also save a stall number over here. Right? So stall number is 1. Right? I've already used up the stall number 0. So the current stall number is 1. Okay. So now what can I do is I can try to put the cow in over there. So I can say while the location of the current stall, right? While A of stall minus A of previous stall. Right? If this distance, while this distance is less than my guess, I cannot really put this cow in the current stall. Right? So I must move on to the next stall plus plus. Do you guys agree? While this is true, I will do stall plus plus. Right? And finally, I will say that, all right, once I have this, I will say previous stall equals to stall. Right? So I will put the cow in there. So this is my loop. Now, of course, this loop might not always work. Right? Basically, when will it fail? When my stall number has become equal to the size of the array. When I have reached the last stall, but my cows have still not been finished. Right? So I can put a condition over here. I can very quickly check over here. So instead of directly doing this stall plus plus, Let me do a stall plus plus. And now I can check if stall equals to n. If I have already reached the last stall, then I can return false. Return false. Because this guess did not work. I still have some cows to place, but I have exhausted my stalls. Right? So I will return false that, hey, this guess does not work. If I can complete this for loop, that means that I was able to place all the C different cows. I was able to successfully place all the C different cows at a minimum distance of guess. So over here, I can return true. Return true. Does that make sense? Does this function, this works function make sense? Yes? Do you guys agree? Perfect. So what will be the time complexity of this? What will be the time complexity of this entire code? Well, let us take it step by step. Right? How much time does the works function take? Given a particular guess, how much time does it take to verify that guess? Well, we have to linearly search through the array of stalls. Right? We have to linearly check the array of stalls. So this works takes order of n time, right? Where n is the number of stalls. Do you agree? Do you guys agree? So, okay, some people will over here say that, okay, you have a while loop. You have a while loop over here, and you have a loop that goes C times over here. So isn't the complexity going to be C times n? Shouldn't the complexity be C times n? Well, no, right? The complexity of this entire for loop is not C times n, because as we see, this variable stall is strictly increasing. Right? This variable stall is never reset. So it can only increase. And the maximum possible value of stall can be up to n. Right? So it is the complexity of this entire nested loop. It is not C times n. It is simply order of n. Is that clear? Yes, perfect. What about this? What about this binary search? So I think I deleted something from here. Right? What about this binary search? So this binary search takes us how much time? It takes us log of the size of search space. What is the size of search space over here? Is the size of search space n? No. The size of search space is this value over here. Right? This is the size of search space. A of n minus 1 by C. Right? This is the size of search space. So this will be the number of times we will have to do the binary search. And each binary search will take us order of n time. So we can say that the complexity of this is order of log of max of AI, max of AI, so the maximum stall location divided by the number of cows, right? The log of that times n. Is that clear? Yes? Yes or no? Well, C over here. Is that clear, guys? So C is not a constant, so we can't really ignore it. So this will be the final value. This will be the final value. And is this better than n square? So do you guys think that this is better than n square? Well, that will depend. That will depend on how large this A of I is. Right? How large this A of I is. Is that clear? So it might be the case that A of I is 1 trillion. If A of I is a very, very large number, then it might make sense. It might make sense to do this n square solution. But that is going to be extremely, extremely rare. Right? So if n is large, then definitely this log value will be much, much smaller. Right? So in general, this approach will work faster. Is it clear? So we saw the brute force approach for this. Right? That was order of n to the power c plus 1. Right? Then we saw the DP approach for this. We did not discuss this in detail. We will discuss this maybe later. So this was order of n square. And then we discussed the binary search approach. And this turned out to be order of log of max of A by C times n. Is that clear? Yes? Any doubts on this particular question? I hope that you will be able to code it. So this is part of the assignments. So please try and code it. You will actually learn a lot when you implement these solutions. Right? And one more thing, please try to make sure that you make the code modular. Right? So just like we have discussed in the class, please define a separate function, right? That will check the guess. You can also write this. You can also write this code over here as well, right? You can also write this code over here as well. But please do not do that, right? Because then your logic will not be clear. You will be mixing the logic of your binary search with the logic of your checking a guess. Let us keep those two logics separate. Binary search is separate. Checking if a particular guess works or not, that is separate. So please let us do the separation of concerns thing and then keep them in different functions. All right. So let us move on to another question. So this is again fairly challenging question, and this is also a very, very interesting question. Okay. So the question goes something like this: that you have been given an n. You have been given a number n. And this n is a 64-bit number, 64-bit integer. And let us say it is also positive. All right, let us say it is also positive. Let us also say that n is greater than 2. All right, let us also say that n is greater than 2. So basically, what values can n take? So n can take a value from, let us say, suppose 3, all the way to 10 to the power 18, perhaps. Right? N can take all these different values. Cool. So now what we are saying is, let us suppose that n written in some base k. N written in some base k. So k can be either 2, in which case we are writing n as a binary number, right? Or k can be ternary, or k can be 3, or k can be 8, in which case we are writing n as an octal number, right? But if we write k in, if we have n in some base k, and if this equals to 1, 1, 1, 1, 1, dot, 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 right? If this is just a string of ones, right? Then we will say that, okay, this k is a good base. Good base. All right? Is that clear? For example, let us say that n equals to 7. All right? N equals to 7. Then what different bases will work? What all different bases can work? So first of all, this k equals to 1 will always work. Right? Yes or no? I can always write something in base 1. Right? A number n in base 1 is just 1, 1, 1, 1, 1 n times. Do you guys agree? Yes? Let us not do that. Let us not do that. Let us ignore this k equals to 1 thing. All right? Let us ignore this k equals to 1 thing. So we are also considering that k is greater than 1. That k is greater than 1. Okay. Now let us try some other base. So 7 written in base 2. What does this look like? What does 7 in base 2 look like? 7 in base 2 is, so this is base 10, my bad. This is base 10. In base 2, if I write it, then it will be 1, 1, 1. Right? So 2 is a good base. 2 is a good base for 7. All right? Are there any other good bases? Are there any other good bases? Yes, no? Well, what happens if we write 7 in base? What happens if we write 7 in base 3? What do we get? So we get 1, then 4 remains, right? Then we will get, so just give me a second. So the last, so 7 is basically equal to 3 to the power 0 plus 3 to the power 1 plus 3 to the power 2. So this is going to be 3 to the power 3. Yes, so this is going to be 2 times 3 to the power 1 plus 1 times 3 to the power 0. Yes, so this is 7. This is 7. So what will 7 look like in base 3? What will 7 look like in base 3? 7 will look like 2, 1 in base 3. Right? 7 is 2, 1 in base 3. So is this a string of ones? Is this a string of ones? No, this is not a string of ones. So 3 is not a good base. 3 is not a good base. All right, let us continue. Let us continue. So we can check the base 4, we can check the base 5. That is also not going to work. There is some other base that is going to work. Right? 7 in base 7 is also equal to, in base 6, this is going to be equal to 1, 1. Right? In base 6, this is also going to be equal to 1, 1. Do you guys agree? Yes. In fact, if I have any n in base 10, then this is equal to 1, 1 in base n minus 1. Yes or no? 1, 1 in base n minus 1, that is simply n. Why is that? Because see, 1, 1 in base n minus 1, this is equal to n minus 1 to the power 0 times 1 plus n minus 1 to the power 1 times 1. Right? And that is equal to what? N minus 1 plus 1, which is just n. Right? So any number n that I have, I can always write in one less base and get a string of ones. So 7 equals to 1, 1 in base 6. Right? 13 equals to 1, 1 in base 12, and so on. Do you guys agree? So n minus 1 is always a good base. Right? N minus 1 is always a valid base. So this is also a good base. Right? Good. Now the question once again is that you have been given a value of n, right, such that n is greater than equal to 3 and n is less than or equal to 10 to the power 18, suppose. So it is a 64-bit integer, positive integer. We have to find the smallest base, smallest good base. All right, so we found several different good bases, right? For 7, we found that 2 works. So we found that 2 works, 3 does not work, 4 does not work, 5 does not work, 6 works. Right? That is what we found for 7. So what will be the smallest good base for 7? What will be the smallest good base for 7? It will be 2. Right? It will be 2. So smallest good base. So for example, if n equals to 7, then the answer will be 2. And why 2? Why not 1? Because 1 works for everything. Right? If we allow 1, then for every number the answer will just be 1. Because base 1 works for everything. Is that clear? So we are saying that the smallest good base, let us call this k, is greater than or equal to 2. So this is the question. I hope the question is clear. Given an integer n, return the smallest good base. For example, if your value is 7, then you are supposed to return the value 2. All right. So what can our approach be over here? What can our approach be over here? Let us start with the most brute force approach. Brute force approach. What will the brute force approach look like? In the brute force approach, we can simply check all the possible options. Right? We can simply check all the possible options. So we can go from base k equals to 2 all the way till n minus 1. Right? We can check all these different values. Now, once we have a base, we have to convert n into that base, right? Base k, and check if this is a string of ones. If this is a string of ones, well, how much time does it take to convert a number into base k? How much time does it take to convert a number into base k? Can someone quickly tell me that? It will take me log of n time base k. It will take me log n time with a base k. This is how much time it will take me to convert a number. Why? Because I have to repeatedly divide that number by k. Right? I will say that, okay, the last digit equals to n mod k. Then I will divide the number. Right? I will say n by equals to k. N by equals to k. This is not or this is a simple division. Right? Then I will say d1 equals to once again n mod k. And then I will again say n equals to n by k. Right? And this will be in a loop. This will basically be in a loop. That is how I convert the base. So it will take me log of n time base k. All right. So what is the total time complexity over here? I have these many bases to check. And it takes this much time to check each base. So it will be order of n times log n. Right. So my brute force approach takes me order of n times log n time. Is that clear? Yes. Now this is not very good, right? This is not very good. If my n is, let us say, 10 to the power 18, then it will take me 10 to the power 18 steps. That is definitely not possible. I cannot do 10 to the power 18 steps on any computer. Yes? So we should better come up with a faster solution. We should try to come up with a faster solution. Okay. So what can we do over here? What is the first thing that comes to your mind? What is the first thing that comes to your mind? The first thing, since we have been doing binary search, might be that, okay, let me make a guess. Let me guess base B. Let me guess base B and check. if the guess is valid or not. Yes, that is what comes to your mind. That let us take a base b, let us consider a random base b, and let us check if it is valid or not. Well, this is not going to work for this case. This is not going to work for this case. Why? Suppose that my number was 7. I checked the base 2. I checked the base 2 and it worked. What does that tell me? Does that really tell me anything? That tells me that 2 works. That tells me that 2 works, but that is not enough, right? I also have to understand. Is my guess too low or is my guess too high? Yes. Just because 2 works, that does not mean that my guess is too low or that my guess is too high. Do you agree? It might be the case that 7 of 6 still works, right? So for this, for the base 7, 7 of 2 works, 7 of 3 does not work, 7 of 4 does not work, 7 of 5 does not work, 7 of 6 works. This works. So suppose you make a guess. There is a valid value to the right of it as well as to the left of it, and you do not know in which direction you have to go. So if it turns out to be false, if you figure out that okay, the guess did not work. So are you supposed to increase the base or are you supposed to decrease the base? Are you supposed to increase the low or are you supposed to decrease the high? Does that make sense? We have no way of knowing in which direction should we move our guess. So we cannot do the binary search over base. Does that make sense? Because once again, if we go back to the first class, if this is our search space, then we need to come up with a proposition such that all the answers here are yeses and all the answers here are no's, so that we can binary search for this midpoint. For this particular thing, the answer over here is yes, the answer over here is yes, the answer over here is yes, but all the other numbers can be no. Right? We don't really know. It can be randomly. It can be in a random manner. So binary search is not going to work for this proposition. Is that clear? Yes, it seems very, very selective to try to apply binary search over here. I have a base. I can verify if it is a valid base or not. So let me just binary search over the base. That is not going to work, unfortunately. So what else can we do? So we have to look at the question from a different perspective over here. So let us suppose that we are talking in base B. Right? Suppose we are talking about in base K. Suppose base K. Right? Then if basically my number n in base K is a string of ones, I already know what the string of ones is, right? I can construct this string of ones, right? I know that this is in base K. I know that this is a string of ones. The only thing I don't know is how many ones there are over here. Yes, how many ones there are over here. Let us call this value I. Does that make sense? So n written in base 2 will have 3 ones, right? N written in base 6 will have 2 ones, right? So instead of trying to binary search over the value of k, let me try to binary search over the value of I. Okay, but let me first establish a relation between these two. So if n in base k is a string of ones in base k, so n is equal to a string of ones in base k, right? And let us say that there are I ones over here. Then what can I say? Is there any relationship between n and k? Yes, there is, right? What is the relationship? I know that 1 times k to the power 0 plus 1 times k to the power 1 plus 1 times k to the power 2 plus all the way till 1 times k to the power I, right? This thing equals to n, right? If I have this number in base k, then this is the expansion of it, and I know that this must be equal to n, right? What can I say? N equals to summation of k to the power I, or k to the power, let's say, x, for x equals to 0 till I, right? So this is what is this? This is a geometric progression. This is a GP. So can I write the sum of it? The sum of it is simply k to the power I plus 1 minus 1 by what? By k minus 1, right? So the sum of a GP, summation of r to the power I for I equals to 0 till k, this is equal to what? 0 till n. This is equal to r to the power n plus 1 minus r to the power 0 by r minus 1. Right? Yes. So just notice that there is this denominator over here. Right? You can't simply say that the denominator is 1. Right, Shazia? So Shazia, there's a small mistake in your formula. You have to make sure that this denominator is also dependent on k. Right? So we can say that n equals to k to the power I plus 1 minus 1 by k minus 1. This is the relation that we have established between n, k, and I. Now I know that I cannot really binary search over k, but that's okay. Let me binary search over I. Right? Let me binary search over the value of I. All right. Now let us suppose that I have I1s over here. Right? Let us say that I have I1s over here. Right? And this is equal to n. Right? This is equal to n. Then what if I'm trying to minimize? So remember that I have to find the smallest good base. Right? I'm trying to minimize the value of k. So what am I trying to do with the value of I? If see n is my constant, right? N is my constant. I'm trying to minimize the value of k. So what am I doing with I? I'm trying to maximize the value of I. Right? I'm trying to maximize the value of I. Do you agree? Yes or no? Right? Yes or no, guys? So that is one thing we know. Perfect. We know that we are trying to maximize the value of I. All right. Let us also consider what is the search space of I. Search space of I. What is the search space of I? So I can be, so this can be, so let us suppose that I write n in base 2, right? This is the smallest base that I can possibly have. So that will give me the largest possible string of ones. How many ones will I get when I write n in base 2? I know that n is a 64-bit integer. Right? So the maximum search space, the maximum value of I can be 64. Right? So I can have all the way from 2 all the way to 64 ones in my string. All right. Now, once again, the problem over here arises. If I know that this sequence of I works, does that tell me anything about this sequence of I or about this sequence of I? Does that tell me anything about this sequence of I or this sequence of I? It does not. Right? I know that I have to maximize the number of ones. But if this works or if this does not work, it doesn't tell me whether I should increase it or decrease it. So I cannot really binary search. Over the value of I either. That's sad. But how many i's can there be? We just established that the maximum possible value of I can be 64. On the other hand, when we were talking about k, we established that the maximum possible value of k can be up to n minus 1. So what would we rather search over? Should we search over k or should we search over I? This can be up till n minus 1. This can only be up till 64. Right? So this is much better, right? Do you guys agree? Searching over I is much better. So I can simply check for every possible I. For I goes from 2 till 64. Let me check for all the possible. Strings of 1. Right? Let me check all the possible strings of 1. Now what I will check? Now I will see whether n can be written in the form of 1 1 1 1 1 I1s to the base k. Right? Whether I will try to see whether any such base k exists, that will give me this. Does that make sense? I can go over every I. Yes, but how do I find this k now? How do I find this k? I know the relationship between these two, right? I know the relationship between all these numbers. I know that n equals to k to the power I plus 1, right? N equals to k to the power I plus 1 minus 1 by k minus 1. I know this relationship. So now, if I have the value of I and if I have the value of n, can I find the value of k? Yes. How will I find the value of k? That is difficult, right? I will have to manipulate the formula. Right? If I want to find the value of k, I will have to manipulate the formula. I will have to extract k out of it. I will have to extract k out of it. So can someone solve this equation for me very quickly? Can someone solve this equation for me very quickly? Well, you can't really. You can't really do that. Right? Because this k, this I might be a very, very large number. Right? And you don't, so for higher degree polynomials, you don't always have a way of solving an equation. So you can always solve a quadratic. If you have a quadratic equation, you can always solve it. If you have a cubic equation, you can always solve it. Right? But for higher equations, I'm not sure for the fourth power, but I know that from fifth power and above, right, it is not always solvable. It is not always possible to solve a higher degree polynomial. All right. So this equation might not be solvable. So what can we do? Do we have to give up? No. Here is where we can binary search. We can binary search for the value of k. Right? We can try to plug in the value of k and try to binary search for an answer that works. Is that clear? So what we will do now is, we now have to find a k that works. What is the maximum possible value of? What is the maximum possible value of k? The maximum possible value of k, so the minimum possible value of k is 2. The high maximum possible value is n minus 1. And now I can binary search over this value of k. I just have to find one k that works. I can binary search for k which satisfies this equation, which satisfies the equation n equals to k to the power I plus 1 minus 1 by k minus 1. Is that clear? So just like in the first class, we tried to binary search. So we did not do it in the class, but it was part of your assignment. Right? So in the assignment, you had to do a binary search for the square root of a particular number. Right? For the square root of a particular number. Yes, so n minus 1. Right? This is n minus 1. Right? So we can binary search over the value of k. Is that clear? So how much time will this binary search take? How much time will the binary search for k take? This is my search space. Right? This is my search space. My search space has size of n. And I'm doing a binary search, so it will take me log n time. Log n time to binary search for a value of k. But I have to do this 64 times. I have to do this for all values of I. So this will be times 64. So the overall time complexity of my approach will just be 64 times log base 2 of n, which will just be log n. That is amazing. Right? We went from an n log n solution. We went from an n log n. What happened over here? N log n brute force, and we reduced it down to a constant times log n. Is that clear? Yes. So even though the question does not directly involve binary search, there is still an involvement of binary search. And the moral of this particular question is that be very, very careful. Be very, very careful. For binary search, you just don't have to make and verify a guess. You also have to understand, given the guess, if that guess worked, then is the guess too high or too low? Right? If the guess worked or if it did not work, this is not enough. You also have to establish, is the guess too high or too low? Because if you cannot do that, then you will not be able to binary search for your answer. Is that clear? Perfect. Ankush has asked a very good question. Ankush is saying, how can we know whether binary search will be applicable for this particular question? Now, that is a very, very tricky question. So basically, the most common answer you will find to this is practice. Right? The most common answer that you will find to it is that, hey, if you just practice, then practice will make you perfect. You will get to know which way, which approach you have to apply. But that is not the entire truth. There is a separate way as well. So there's a systematic way. There's a systematic way of approaching problems. Right? Now, unfortunately, I cannot teach this systematic way in a YouTube class, right? It cannot be taught in a 1-hour class. So the entire scalar curriculum of DSM algorithms is based on, tries to teach you this systematic way. Right? So that whenever you get a new problem, you can just apply the systematic algorithm and try to come up with a solution for that. Okay, that is what we teach in the scalar classes. All right. So, I mean, we could cover this, but this is going to take a very, very long time. We will have to take a very long class. We'll have to consider all the DS algo things, and then we will have to tell you the approach. Perfect. So that is it for today's class. Let us end the lecture now. and see you then. So once again, you can find the assignment set in the video description. Please make sure that you attempt the problem set. Okay then, have a nice day, guys.
Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they are very straightforward, and then attempt as many questions as you can. There are some standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from the stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top, and you can only remove a plate from top. You cannot insert or remove a plate from in between because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as LIFO data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the 4 operations, that is push, pop, top, and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop, and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions. Okay, so it's push 2. So what we'll do, from where we'll put it from here. So basically 2 will come over here, then it's push 1. So 1 will come over here, then -1, -1 will come over here, then there is 5, 5 will come over here, then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. that's an activity for you, that do try to search that how we can perform an undo redo. So this is actually present in your browser, right? So whenever you go to any page, from any page, and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3, and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do? We can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay. Then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming, so we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay, and now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case that's an overflow. You cannot insert any more elements. So that's a drawback of arrays, and to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I'm calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time, and seventh time, and now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow, okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element, so you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay, so that's how you can implement a stack using linked list. Now with linked list, the concept of space, a lot of space is used in linked list. Okay, so basically you are storing pointers as well, that will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of 1 time complexity. Okay, in just order of 1 time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete, they are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without star. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket. So we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid, because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string, because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay, we have not used any space. Now let me make a question little trickier. Now let's say I have brackets these and these. So this is an extension of the question. Extension hai ye question ka. Now I am saying that I have these 3 sets of parentheses. Now I have to tell, basically my string can contain these set. So I have to tell if those are valid or not. Let's take an example. Examples can be this, 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 then we have this. So this will be given to you. Now you have to tell, are they valid or not? Now can you, how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it. Like how? What's the intuition? So that's is very important. Okay. Some of you are saying that we can use 3 variables. So that will be wrong, because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket ka left, right, iska left, right, then iska left, right. First ka left is 1, okay. Third ka left is 1, okay. First ka right. So we have found a right bracket and this manages to be 0. Then we have third ka right. So this becomes 0. But is this valid? No, it's not valid, because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these brackets. One thing is that since, okay, so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parentheses will also be balanced. As you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that will be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket, okay? So let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past, okay? Just the past. So how and what we can do? We are at this bracket. This is our opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here, this is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here, we have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? And if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case, we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case, you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, So here, as I talked about that, step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be balance. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay. So question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right, just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what do you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are 2 nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the. So basically, this is just so we can actually, make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay, 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? -1. Nothing is on right. For this, -1. For this, -1, -1, -1. Does that make sense? The answer for all of them will be -1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got -1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have a 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So so basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer, to them 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be -1. -1. Okay? So since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. S dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye-bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a FIFO structure. Whatever goes first, it should go out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. and this is the front element of the queue, and this is the last element of the queue, or we can see as rear element of the queue. Now, so as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as the rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now, if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion. And the second operation is dequeue. And here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue. And where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue. That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now, let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have a library, so then we can simply call enqueue function of that library and we can insert 2 in our queue. So when we insert 2, it will come from here. Fine. So now, as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element, so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5. And it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library, it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks.
Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, I think we will solve some of the questions of stack and queues. Proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all 3 questions of this clever stack. Okay, let's start the question. We have been given an array and in that array, we need to find the nearest smaller element gi for every element ai in the array such that the element has an index smaller than I. Okay, let's say we have more boundary, gi is the element aj is j is greater than I. Okay, the basic question is for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array. And for 4, as we can see that no element is less than 4 in the left side. So we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4. So our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2. So for 2 as well, I can see that there is no minimum element in the left hand side. So -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, okay. Now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10 and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So, okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers and I just need this data point only because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, when I have 2 to which I need to figure out the answer, for 2, I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer, for sure. But for 2, it won't be the answer. So after then, I need to store these 2 points, isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I am doing, I am just first checking for the last element and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve, because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try to think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first, what I can do, let me first figure out the size. Okay, let me create my answer, which is of size n, and let me have the default value as -1 for each particular element in that particular array, because we haven't found the answer, and we will follow the algorithm as I discussed here so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack, isn't it? Okay, now I'm done here. So I can new. Okay, if there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. You know? And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future. So I can safely remove it. By the time this thing gets ended, I can say that, okay, now I'm done. Now I can safely add the ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer, and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that first element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n, where a represents a histogram. That is, ai denotes height of ith histogram bar, and width of each bar is 1. Okay, let's say we have been given this histogram, and where the height of first bar is 2, and the height of second bar is 1, and height of third bar is 5, and fourth bar is 6, and so on. And above is histogram, and width of each bar is 1. And we have been given heights like that, and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this is my answer, and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was, we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper, and then it's more suitable. Okay, 1, 5. Okay, it will be 5, and then 6, and then 2, and then something 3. Fine. So this will be my answer in this case. So what I can think is, what can be the brute force way to solve this question? One thing is coming to my mind. I can solve it in a way that, okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first 3 element, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay, so if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment, and to iterate over each contiguous segment, I need to take 2 variables L and R. So it will take order of n square time, and for each contiguous segment I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here, and I have 8. I have something 6. I have again 8, and I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well, and I will consider this segment as well. I will consider this segment as well. I will definitely consider all the segments, If that is the case, that means, but I know that for all these segments, if I did in that segment 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6, and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well, and I can solve this. And I can solve similar for the right hand side and for the left hand side, and I'm done. That is sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1, and in the left hand side I don't have any element. Fine, and so I just end up with the contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n. So which is 1, 2, 3, 4, 5, 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5, the minimum length available, 6 is greater than 5. And okay, I found element 2, which is less than 5. So I can only consider these 2 elements for 5. Now, if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5. So I can consider only these 2 elements for 5. So I have a length of 2. Length of 2 for 5. I have a length of 5. So my answer will be n. If I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these 2 elements are the nearest minimum element for 6. So I just have a 1 length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. and 5 is also greater than 2. Nice. But 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these two elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3 and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can find the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. But with the simplest code to write the solution for this will be, let's first have a size. Okay, I need 2 informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created 2 vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n and the what should be the default value. Okay, I know that if for that element I haven't found any element which is lesser than that element in the right hand side, so I can say that okay, let's just say that okay, so in that case I may end up end of my list, so I can safely mark it as n, okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. And let's say I created a stack. Now let's first solve it for the right side. And let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty, or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate up till my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side, stack dot top. I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, okay, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is a of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think. Maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and n for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements, after solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove, let's say I remove that algorithm from my stack. Okay, so now let's look at the complexity part of it. This is running order of n time, this is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. We have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. A smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. But what this question is saying that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that W numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array, we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 elements of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and -1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, -1 and -3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window, it's equal to 5. Okay. And for this window, if I go in a similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, okay, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we take the random array now. 4, 7, 8, 3, 2, 5, and we have been given b as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum. I do the iteration from start to end, but this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is what I can do. I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. Within a given range, I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because this, I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So, okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment rather than that data structure that will already solve us our problem in order of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers head and tail. we can just add the element, and then we can easily remove the element from the AND in order of one time, and add that element in order of one time. And similarly, what we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of DQ. So we can use DQ in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a DQ where if I have a first element, I just put it and I figure out the second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the DQ, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current, it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element, and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. We figured out everything, what is required, and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like DQ, and let's say it's BQ. Okay, now I need to iterate over my link, over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my DQ is empty, and or if I have an element in the end of my DQ, which is basically greater than my current element. In that case, what we need to do? We just figured out in that case, we may need this information. So in that case, we can add this element in the end, and that will help me to solve this question. Now, if that is not the case, what we can do, we can check while, okay, my DQ is not empty, and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater index and it is greater than the last element of my DQ. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to B. So what we need to do in that case, if that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than or equal to B, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my DQ, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case. If my DQ is not empty. Otherwise, it will give us the segmentation fault. And if my DQ is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the 0th element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus y, because if I at the next window, my I will be b and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do it that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be PQ dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain DQ, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering every cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.
Let's talk about trees and understand why trees are important for an engineer. Trees are used to implement other useful data structures like sets and maps. Heaps, priority queues, and tries are also based on trees. In fact, indexing in the database is also implemented using trees. The underlying data structure used in text editor, for example, is also based on, you guessed it right, trees. As an engineer, it is must to have a solid foundation on the trees. You should be able to solve all the problems related to trees. Companies like Amazon, Google, Microsoft, Adobe love asking questions on this. In fact, I will go to an extent and say that no Amazon interview is complete without solving a tree problem.
Hello everyone, in this video we are going to start study about an interesting data structure known as trees. Till now you might have heard about data structures like arrays, linked lists, stacks and so on. These data structures are linear data structures. For example, take a linked list. In linked list you have a set of nodes where each node points to the very next node. In this linked list, suppose there are 3 nodes. Let us say this node stores the data 4, this stores 1, this stores 8, and this is an end pointer. What is the start of this linked list? Correct. This node points to the start of the linked list. As you see that in a linked list, there is a logical start, there is a logical end pointer, and also there is a logical meaning of the next element. These are the properties of linear data structures. What is a data structure basically? Data structure is nothing but a way to store and organize data in a computer system. How will you choose which data structure is perfect for a particular problem? You might choose this based upon some different kinds of criteria. The first criteria might be the type of data that you are representing. The other decision might be to reduce cost or time complexity for frequent operations. Example, suppose you are given a problem that hey, we are given a set of numbers and multiple queries where you have to find if a particular number exists in the array or not. What data structure you will use? You can use an sorted array and apply binary search, or you might also use a hash map. Sometimes the choice of data structure is based upon reducing space complexity. Tree is a data structure that is most suited for hierarchical type of data. Consider the organizational hierarchy of a big corporation. There is a CEO. Under the CEO, there might be multiple presidents. Similarly, under each president, there might be multiple vice presidents, and so on. This is a type of data that is one of the most common types of data that can be represented using a tree. Why is it even called a tree, by the way? There is a very similarity between this data and an inverted tree. What are these things in the tree? Yes, these are the leaves. Similarly, in our tree data structure, the end nodes, had there been no other nodes downside it, are known as leaves. What is this in the tree? This is a root. Similarly, the top of the tree data structure is also known as the root of the tree. So basically, a tree data structure represents an inverted tree. Now, let us look at some terminology related to trees. Let me draw a formal tree for an example, and let me number the nodes in some way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The very first terminology that is related to tree is the root of the tree. Root of the tree is nothing but the node which is at the very top of the tree, or the node under which all the other nodes of the tree lie. So in this example, 1 is the root of the tree. Now let us discuss the parent-child relationship. As there is an edge from 7 to 9, 7 is known as the parent of 9. Similarly, 9 is a child of 7. Now, what is the case of 6 and 7? As 6 and 7 have the same parent tree, 6 and 7 are known as siblings. Okay. Now, the very common term that you will see when reading about tree algorithms is a leaf. A leaf is a node that has no child. So, in this example, node 8, node 5, node 6 and node 9 are leaves of the tree because they have no child of themselves. Now consider a path from the root of the tree, that is 1, to a particular node, for example 8. We see that on this path the nodes that lie are 1, 2, 4 and 8. If a node lies on the path from root to a particular node, for example 2 lies on the path from 1 to 8, 2 is an ancestor of 8. Conversely, 8 is descendant of 2. Now we studied about ancestor and descendant. Now let us see for a particular node 8 again. What is the length of the path from 1, that is root, to 8? As we do here, the length of the path from 1 to 8 is 3. The length of the path from root to a particular node is known as depth of a node. In this case, the depth of node 8 is 3. Similarly, what is the depth of node 3? As the length of path from 1, that is root, to 3 is only 1, which means depth of 3 is 1. Similar to depth, there is another term which is height. People tend to confuse between depth and height. As depth is the length of the path from root to a node, height is the length of path from node to farthest leaf in the subtree rooted at node. Let us take the example of node 3. In node 3, what is the subtree rooted at node 3? Correct. This is the subtree that is rooted at node 3. What is the farthest leaf from 3? As you can see that the farthest leaf from 3 is the node 9. So, what is the length of the path from 3 to 9? It is 3, 7, 9. So, the length of path is 2. which means height of node 3 is 2. So make sure you understand the difference between height and depth clearly and don't confuse between those. This was the definition of height of a particular node. Now, what is the height of the tree? Height of the tree is nothing but the height of root node. So, in the example above, what is the height of the root node? Clearly, the longest leaf from the root 1 is 8 or 9. What is the length of the path from 1 to 8? As we saw earlier, it is 3. Thus, the height of tree in the above example is 3. Great. So we have till now discussed some of the terminologies related to trees. Let us discuss a few properties of the trees as well. The very first property of a tree is that a tree with n nodes has n minus 1 edges. Why do you think that is the case? Let us go back to the tree that we draw above. We see that for all the nodes other than the root node, there is an edge pointing to the node. For example, for the case of node 2, there is one edge that is pointing to the 2. Similarly, for node 4, also there is only one edge pointing to the node 4. Similarly, for node 5 and all other nodes. So we see that there is one edge from to any node other than the root. So for n nodes, all nodes other than root have an edge pointing to them. This means there are n minus 1 edges. Based upon the properties of the trees, different types of trees are also defined. So, for example, if all the nodes of a tree have less than or equal to 2 children, this means the tree is a binary tree. Extending this thing, if all the nodes of the tree have less than or equal to n children, implies that the tree is an n-ary tree. Let us take an example. Do you think this particular tree is a binary tree? No, this tree is not a binary tree because we see one node has 3 children. Implies that not binary. Do you think this is a ternary tree? Ternary is also known as 3-ary. We see that this node has 3 children, this node has 1, and all other nodes have 0 childs. As we see that all the nodes in the tree have less than or equal to 3 children, this means that this is a ternary tree. Similarly, there are many other properties of the trees of different kinds of trees. For example, there is a binary search tree. We will discuss this in depth in a future video, but as an overview, a binary search tree has a property that all nodes in left subtree of a node have values less than the node value, and all nodes in right subtree have values greater than the node value. Now let us move to some of the applications of this tree data structure. A tree data structure is a very important data structure and is used in many real-life applications. As we discussed earlier, that tree data structure is the by default data structure for hierarchical type of data. So it is used in applications that resemble hierarchical data. Example, the file system of your computer. How is a file system type? There is a parent directory, or which is also known as the root directory. Inside this root directory, you might have multiple other directories and files. For example, this is a directory D1, D2. This might be a file F1. Similarly, there might be another directory D3. Each of those directories can in turn have other directories under them or files. For example, suppose D1 has one more directory inside it and 2 files. A file cannot have anything inside it, so file in a file system will be a leaf node. There might be a directory, for example in this case T2, that might not have anything inside it, which can be an empty directory. I hope it is clear as to why tree data structure is one of the best data structures to represent your file system. The second application of tree data structure is by different types of trees that exist. For example, there is a tree known as trie. Trie is a data structure that is very good to represent dictionary. It allows us to search if a word of length m exists in the dictionary in order of m time. We will study trie in depth in one of our future videos. Similarly, as I talked briefly before, there is a type of tree known as binary search tree. Binary search tree allows us to find if a data exists in the node, exists in the tree in order of height of the tree. That is why you will see that height of the tree is very important factor in analyzing the complexity of tree algorithms, and we will study it in depth also in future videos. One last application of tree that is commonly used is in routing protocols and internet. Are you guys aware of a DNS? A DNS is represented like a tree. Suppose you have to find the address of www.google.com. A DNS server is organized like a tree. There is a root domain dot, inside under which there is a .com, under which there will be a .google, under which there will be www. Similarly, suppose it had to represent facebook.com as well. To represent facebook.com, the root domain will remain the same, .com will also remain the same, but there will be another Facebook here. Great. I hope it is clear as to how a DNS server might now be resolving your queries.
Myself Robin, and we will solve some of the simple questions of tree today. Let's solve some basic questions today. Let's start with the simplest question with the binary trees. Now we have been given a binary tree and we need to figure out whether that given tree is height balanced or not. Okay, what is the definition of height balanced binary tree? It is defined as a binary tree in which the depth of two subtrees of every node never differ by more than one. Okay, I need to return 0 or 1 for this problem. I need to return 0 if my tree is not balanced, and I need to return 1 if the given binary tree is balanced. This is the input that is being given to me, and I need to figure out whether the given binary tree is balanced or not. Okay, as we can see that the height of the left subtree here is just 1, as well as the height of right subtree is also equal to 1. It means that, okay, the difference between the heights for the left and right subtree, it's equal to 0. Okay, if it is 0, that means it is less than 1. So the answer for this case, it should be true. Okay, fine, nice. Now if I just visualize this input, in this input, as we can see that in the left side we have 2 nodes, but in the right side we don't have any node. It means that, okay, the height in the left subtree, it's equal to 2, but the height of the right subtree is 0. So if I take a difference, then the difference for this as a rule, it's equal to 2 minus 0, which is 2. And as it is greater than 1, so that means I need to return false or 0 in this case. Okay, now we got the question. Okay, now let's try to visualize how we can solve this question. Okay, the question is, we have been given a binary tree. Let's say this is the binary tree that is being given to us. And we need to figure out whether that given binary tree is balanced or not. Okay, the simplest thing is kind of a really simple question, that what we can do in this case, I need to first check if that given binary tree is balanced or not. That means that first of all, the left subtree also should be balanced, as well as right subtree also should be balanced. That should be true. If both the things are true, and if I just calculate the height of the left subtree as well as the height of the right subtree, if I figure out height of both the subtrees, then the difference should be less than equal to. If these three cases are true, that means I can say that, okay, that given tree is height balanced. Okay, now if I need to do that, in order to solve for my complete tree, whether that complete tree is height balanced or not, what I need to do, I need to check for my left subtree whether my left subtree is height balanced or not, or as well as my right subtree is height balanced or not. And again, when I just reached at my left subtree, and again I will check whether the left child of left subtree, the left subtree of the left subtree, is balanced or not. Similarly, I will check for the right side, and for here as well, I will check for both the sides. So it seems to me kind of a recursive approach in which the way I can solve this question if I build some sort of recursion. Okay, I need also some sort of information which will help me to evaluate the height in the left side as well as in the right side. Simplest approach that is coming to my mind is what I can do. I can make a function, pass the root, and check whether the left side is balanced or not, or also check whether the right side is balanced or not, and somehow evaluate the height for the left side and evaluate the height for the right side as well, and then just check the difference. And if this gives true, and height is less than equal to 1, in that case I will return true. In other case I will return false. If I just apply that algorithm, that will give me the answer. But now let's try to analyze the complexity of it. Okay, I'm doing some sort of one traversal over the tree, which will cover my recursion part, and also I'm evaluating the heights. Okay, if I will evaluate the height, that means if I am at some node, I need to traverse each level if I want to figure out the height of the given tree. Okay, again, that can go up to order of n. And at each step, I am just figuring out the height. So the complexity if I solve by this algorithm will be order of n square. Okay, can I do better? Okay, if I want to do better, that means I want to somehow pre-store the height information. Okay, so one approach that is coming to my mind, that what we can do, first evaluate the height of every node. Okay, but then it will take off an extra space. Okay, though, so two solutions comes to us. One of them gives us, solves our question in order of n time, order of n square time, and order of 1 space. And the other solution solves our question in order of n time and order of n space. Can we think of something better? Okay, such that we can solve this question in order of n time and order of 1 space. Okay, let's try to think first. Okay, the point is, just we need to check one thing only, and that thing is basically the difference between the heights of left and right subtrees. Okay, and if I check this information at each level and at for each node, and each nodes just give me the answer, the difference less than equal to 2, then I am damn sure that that given tree is height balanced. So but one thing that is coming to my mind, that forget about this thing, just try to solve in such a way I can just figure out the heights, because I know that if I want to figure out the height of a tree, it will be, I need to figure out the height of my left subtree as well as I need to figure out the height of my right subtree. So if that is the case, and the height of this will be, because anyways, if I want to calculate the height of a tree, I want to evaluate the height of the left and right subtrees. So the whole recursion part, it can also be covered here. So one thing that I can do, I just evaluate the height of every node, because if I want to evaluate the height of every node, I am checking this condition. I'm doing this thing. So, and I can check whether the difference is less than equal to 1. If it is, that means I'm done. That means, okay, if it is greater than 1, that means I just found a node such that that node is not height balanced. If a particular subtree of a given tree is not height balanced, that means I can't say that the whole tree is height balanced. That means the whole tree is also not height balanced. Fine. So the one thing that is coming to my mind, that what I can do, I can keep a one global variable which just track this information. And if I just solve in that way, I'm done. Sounds like a good solution. Okay, let's try to solve this now. So the way I think is, so let's first make a global variable is complete tree balanced, and I can initialize the value here for this global variable. It's completely height balanced, and I should initialize it with true. Okay, now what I can do, I can calculate the heights for each node, because I know that while I'm calculating the height, I can check the overall height balancing thing. Let's calculate the heights. Let's say first for A, and it should return me integer value. So let's calculate height for a given tree node. This is the case. Now, if A, let's try to handle the edge case. If we don't have A, then I need to return 0. Otherwise, the left subtree height, if I need to evaluate, then I need to calculate left calculate height. Again, that function with the left node. If I want to evaluate right subtree height, same function with the right side. I need to follow this procedure, and now I can check this thing. If the difference between left subtree height and right subtree height is less than equal, is greater than 1, that means I'm done. I just found a node, or I found a subtree in more specific sense, that is not balanced. So I can change my global variable is complete tree height balance or not to value false. Nice. If I do in that way, I can surely achieve something, and I need to return the height of that given tree, which will be equal to max of left subtree height or right subtree height plus 1. Nice. If I just solve in that case, and I can return that global variable, because if it is true, I need to return integer. I just need to check if it's complete tree height balanced. I need to return 1, else I need to return 0. That is it. Let me check. I just created a global variable is complete tree height balanced. Okay, now I'm checking the height, calculating the height. The left subtree height is, I'm calling the same recursive function again. And for calculating the right subtree height, again I'm calling the same recursive function again. Now I am checking whether if the difference between the left subtree height and right subtree height is greater than 1, that means I am just updating my variable. Otherwise, I'm returning the max of left subtree height and plus 1, adding 1 to it, and I'm initializing it with true, and I'm calculating my height, and I'm done. Nice. Let's submit my code. Nice. Oh, we already got 261 points. Nice. Let's solve some other question. Okay. He said you took some basic question. Okay, let's try to solve some good question. Let's pick this one. Okay. I don't know, but this. Okay. Okay, given the in-order traversal of a Cartesian tree, and we need to construct the tree. Okay, what is Cartesian tree basically? Cartesian tree, it's basically a heap ordered binary tree where the root is greater than all the elements in the subtree. Okay, you may assume that duplicates do not exist in the tree. Okay, nice. So the thing is, we have been given a Cartesian tree, and he cleared me the definition of Cartesian tree as Cartesian tree is basically a heap ordered binary tree. Okay, if it is heap, that means whether the root contain the maximum value of the given tree or it will contain the minimum of the given tree. And it says that the root is greater than all the elements in the subtree. That means root maintains the information that is the maximum value of that given tree. So I need to construct a tree, or I have been given in-order traversal of the tree. Okay, if somebody, or if most of you who don't know about Cartesian tree, let me briefly tell what the Cartesian tree is and all those things. Cartesian tree, it's basically the concept Cartesian tree comes because the thing is it's a kind of BST plus heap, or in some sense we can also call this tree as tree. And the way we have the definition that we have been given a Cartesian tree in that form. That is we have been given the in order part of it, because we know that if the given tree is BST, we can, if we have been given some order, with some specific in order. Let's say that in order is 1, 2, 3, 4. We can construct so many binary search trees. One of the binary search tree that we can construct is simply 1, 2, 3, 4, because in that given binary search tree, the in order is 1, 2, 3, 4, and with the same in order, we can construct so many binary search trees. The point is, so the way Cartesian tree comes, it just gives us the unique binary search tree. And that uniqueness comes because of that heap part. Because in that case, why that heap thing helps me? Because the way heap we design the tree now, such that the root contains the maximum value, and it also maintains the in order part. That's the basic property of BST. Okay, let's say we have been given a tree 1, 2, 3, 4. Let's say the maximum value is 4. So I can say that, okay, the 4 should come as a root, and the elements, let's say the elements before, after 4 are, let's say the elements are 3.7, 2.8, something like that. And that is the in order. I know that that is the maximum value. That means that, and I need to maintain in order as well. So it means that all the nodes which are less, which has having a index less than 4, that means all these nodes should come into the left subtree. Why? Because I need to maintain in order. I know that the in order of a BST is left root right. If that is the case, that I know that the in order is left root right, it means that, okay, first I need to evaluate left and then root and then right. So I can say that all the nodes after this node will definitely go into the right side, and all the nodes before this node will definitely go into the left side. So we have been given the in order of a tree, and the heap is kind of a max heap. We need to construct that tree. That is our question. The question is quite simple. Okay, let's try to first construct a tree. This question is also not too complex. The point is, we have been given the in order of the given tree in the form of an array. Okay, and I need to construct the tree. Fine. Okay, in this question as well, I can just somehow apply some sort of recursive approach, and in that recursive approach, what I can do, first of all, I have been given a complete vector. What I can do, I just figure out the maximum value in it. Let's say I just figured out the maximum value in it, maximum value in that complete vector, and I just make it as root. And now what I can do, I can just now recursively call for the left side as well as recursively call for the right side. And now what I can do, I can just construct this as a tree as well, and I can mark the left child for this root as the root of the left subtree, and I'll mark the right child of that node as the root of the right subset. If I just solve in that way, then I can solve this question. Now first, before jumping into the code, let's first try to analyze the complexity for this question. Okay, first what I am doing, I am just calculating the maximum value. At each instance, I am calculating the maximum value. Okay, I'm calculating the maximum value which is of kind of order n, and I am calculating the maximum value at each step. Let's say I have a function which gives the root, so it has a node which gives me the root of the tree when it takes a given array. Now what I need to do, first I need to find the maximum element in that given array, and then I need to call the recursive function again. Let's say the index I just got after calculating the maximum value from that given array, it's let's say I. So I need to call the function from the left side to the I minus 1, and that same function again with the I plus 1 to right, because this should go into the right side and this will go into the left side. And what I can do, I can mark the left as this and right as this, and I can return this. Now the complexity is the order of n, just because I am traversing over each of the node, over each element of the array, and also I am figuring out the maximum value in that array as well. So the overall complexity for this solution, it will go up to order of n square. Okay, so we just figured out the solution which is of order n square. Now the point is, can we solve it in a better way? That is the point. Can we solve it in a better way? One thing we just figured out that what we are doing, we are just concerned about the maximum value. Okay, and somehow I know that if that is the maximum value, and so all the nodes here are comes to the left side of it. Okay, let's say I have a sequence. Let's see the sequence. Let's see the example. Let's say we have a given sequence as 5, 4, 8, 3, 1. Okay, if we have that given sequence, what we can do now? As we can see now that we have a 5, and if we just found an element which is lesser than this element, so I can safely say that as 5 is greater than 4, that means the 4 should go to the right side of it, for sure. Okay, now if I figured out 8, now can I say anything if I figured out 8? Now I know that, okay, if I have some elements, let's now try to construct something such that we can able to solve our question in less complexity or better complexity. Now let's try to think what we can do to solve our question in a better complexity. Okay, the thing is, let's say I have 5, nice, then I come across 4. If I come across 4, I know that 4 is less than 5. That means what I need to do, I need to make it as a right child, of 5 for sure. Let's say I just do that operations as well. Let's say I just keep it as right child. Now, okay, do I need the information of 4 ahead? Will it help me in any further processing? Okay, I don't know. Let's see. Let's say I just found the value 8. If I found a value, let's say now 3. After 4, let's say I found a value 3. Now what I can do? Okay, if I found a value 3 and I know that 3 is less than 4 and 3 has a greater index, that means 3 will go into the right side of it. Okay, so I just figured out a solution. If we have been given an in order in such way, then I just need to map as a kind of right child of that particular node. Okay, if that is the case, then I am happy. If so, that means I am just keeping the information, and the time I am getting the value which is less than the particular value, in that case I just need to mark it as a right child. Fine. If that is not the case, let's say I am just getting a value which is greater than this value. Let's say I am getting a value which is 4.8. Now, so that means what should be my structure now if this information is given? If this information is given, then I know that, okay, let's say we have 5. I know that all the elements, these are less than these, the elements I am storing here, it's kind of in reverse sorted order. So if it is greater than 3. Nice. So that means all these nodes should go into the left subtree of this, because I need to maintain a heap kind of information. So this particular node should be the root for these two nodes for sure. So what I can do now, the overall structure at the end, it will be something like 5, then the right child 4.8 will come, and in the left subtree I will have 4, and I know that structure. So what I need to do now, what I am just doing now, if I am getting a value which is, let's say I am iterating over the array, if I am getting a value which is less than that particular element, then I am just making that node as a right child of it and just push that something. And if I am getting a value which is greater than this thing, then I just pop all the elements which is in this stack or some data structure, because I just said stack because it is following that property. Why? Because what we are doing, we are adding the elements in the end as well as we are removing the elements from the end. And if we follow the same procedure, somehow we will be able to achieve our solution, isn't it? Does it sound good to everyone? The way I am approaching or the way I am dealing this problem, if I want to achieve it in a better complexity. So the point is, if we follow the same way, we can now the complexity. Now let's try to think about the complexity. If we just try to solve in that way, the thing is, what we are doing, we are just inserting an element in the stack. If that element is lesser than the topmost element of the stack, and I'm marking it as right child of the topmost element, fine. Otherwise, if the given element that I just encountered, it's greater than the topmost element of the stack, then what I need to do, I just need to pop out some of the elements from my stack. Let's say I just popped out these two elements in that case. So the last element which I popped out, I need to keep track of that information about the last element. And I need to make the left child of that particular node as that particular element. And now the topmost element which is present in the stack, I should make that particular node as the right child of that particular node as 4.8. Because in the end, my structure should be something like this, isn't it? If my structure is something like this, only then I can say that that is maintaining some sort of heap information as well as maintaining in order as well. So if I will solve in that way, I can solve my question from order of n square to order of n. Nice. And we know that we can't solve better than this complexity. This is the best complexity that we can achieve for this particular question. Now let's try to solve this question. So as I just told you, we need a stack to maintain all this information. Let's say I created an empty stack, and okay, now let's iterate over my entire array. Let's first keep n as size. Now what I can do, as I know that, okay, let's first check the big edge cases. Let's say if my stack is empty. If my stack is empty, that means I don't have any elements in my current stack. That means that the particular element should be the root. Or if that is the case, or okay, let's first create a root. So that means in that case, let's say my root will be new tree node, and I have been provided a constructor in which I can just pass the value of integer and it will create a node. So I just need that value which is a of I. Nice. And kind of I'm done. Okay, now I figured out the root, and it's better to maintain a stack of tree node. So I can push into my stack, the value of root. Fine. Now the point is, now the case is something like I have an element in the stack, but the current element that I figured out, it is less than the topmost element of the stack. The topmost element of the stack, and I need to just concern about the value of that particular element. So because I am adding the basically nodes into this stack. Now, if I just do in that way, in that case, what I need to do, first of all, let me create a new node. Okay, with the value k-ary, and mark the right child of the topmost element of the stack as that given node, and I can push that given node into the stack. Fine. Okay, if that, even if that is not the case, that in other case, the other case is I have a value, that means AI is greater than the topmost value of this stack. Then in that case, I need to pop out some elements, and I need to just concerned about the edge case as well. If my stack is not empty and the value at the top, it's basically less than AI, we are happy because we don't have given any duplicates in the tree. So we can do in that way. We shouldn't have to handle the duplicacy case here. So we are good with that. Now, if that is the case, then what I just told you, then I need to keep track of the last element which gets popped out, because that last element will be the left child of that particular element of AI, isn't it? So if that is the case, then I can make last, and I can update my last as toto, and I can remove the, I can keep it as null. Okay, now what I can do, I just figured out the last element. So let's first create a new tree node for that particular element. With the value of AI. Now what I can do, the value for that particular node, the left child of that particular node will be my last, and the right child for the topmost element. If let's first check whether we have a topmost element in the stack, or there might be a case that my stack gets empty. So I need to check that thing. If my stack is not empty, then but I need to check whether the, I need to mark the rightmost child for the top as the given. If I just do in that way, I will somehow solve this question. Looks like a good approach to me. And I need to return true. Let's again check the way we think and the way we applied the algorithm. Are they both matching or not? Or have we missed any case or not? Let's first check. Okay, what we do in the starting, we just created a stack and which contains all the nodes. Nice. And we just take our n, which is the size of my array. Nice. I just iterating over my array, and I'm just checking whether my stack is empty. Because I know that stack will be empty, only in that case, I need to push now that element as well. Sorry, I just forgot that thing. Okay, because if that stack is empty, that means this is the first node, kind of. So that means I need to make it as a, okay. Oh, sorry. I just need to push. Okay. So that means I can't say that it will be my root. The root must be the topmost element in this stack for sure. But yeah, I need to construct a node here, and I just need to add the node if stack is empty, because I can't do anything else. And the other case will be if we have our value, it is less than the topmost value, then we are sure that in that case, we need to mark it as our right child for that particular element. So we are doing this thing. So it seems right to me. Now the other case will be if AI is less, if it's not less, then it will be greater. So that means it should be the root of some of the nodes. So I'm just checking out all the nodes. So for that, what I'm doing, I'm just checking up till when I have that given value, it's greater than to the topmost value. So I'm just maintaining my last node because it is required. And what I am doing, I am just creating one new node, and just what I am doing, and just mark the left child for that particular node as a last. Nice. If I do in that way, it seems like a good thing. Now let me test. Okay. Oh, sorry. Nice. Let's submit this code. Oh, okay. What's wrong? Let's try to see. Have we done anything wrong here? We have been given the tree as 231. If we have been given tree as 231, first what we can do, what we are inserting 2 here, and it shouldn't be that. It will be the first element. It shouldn't be the last element of this stack. Okay, so I need to maintain the last information. Let's say it as null. Because the way we are maintaining our stack, it's in reverse sorted order. If it is in reverse sorted order, what does it mean? That means the maximum value should come in the front of my stack. And I am popping the element in that a way that if we have a maximum element, it won't be go out of my stack. And it will always be appear in the starting of my stack. So I need to update as this, and I need to pop. If I do in that way, then it should work. So, sorry. Why now? I'm updating my last here. Okay, it's not stacking. Sorry, I'm doing some silly mistakes today. Let's check. Nice, we solved this question. It took us some time, but we solved this question in order of n time. That's good. That's good for us. Okay, let's solve one more question today. Let's solve this question. I don't know what's this. Okay, the question is, we have been given 2 binary trees and we need to check whether they are equal or not. Okay, 2 binary trees are considered equal if they are structurally identical and the nodes have the same value. Okay, I need to return 0 or 1 depending upon this. Okay, let's say I have been given this tree and this tree. I just need to check whether both of the trees are equal or not. It's kind of a very simple problem, but I need to check if the both of the trees are equal. That means the node itself will be equal, as well as the left subtree and right subtree, both left subtree and right subtree also should be equal. If all those things are fine, then I can safely say that the both of the trees are identical. To solve this question, it shouldn't take much time. Then what I can just first concerned about the edge case, and you can see that this simple question, it's been asked in Amazon as well. So, but the point is, are we handling all the edge cases? Are we come up with a good solution at one go or not? So, what are the edge cases? What will be the edge cases in this question? The basic edge case for this question will be kind of, let's check whether we have been given both the nodes as empty or not. If we have both as empty, both the trees as empty tree, then I can safely return 1. Because I know that in that case, both of the tree are identical. If any of them kind of, if both are not kind of empty, one of them is empty, that means both the trees are not identical. And in that case, I need to return 0. So this will be kind of one more edge case. Now I end up with both the trees such that both the trees has some elements. Now in that case, the idea is very simple, but I need to check whether the basically value for both of them are equal or not. And it is equal, and I say that is the left subtree for both the nodes, are they equal or not? Oh, sorry. I need to concern about the left subtree only. And also we need to check whether the right subtree for both the nodes, are they equal or not? If all these 3 conditions met, then only I can say that both the given tree is identical. Otherwise, both the given trees are not identical. If I just solve in that way, I am done. Sounds like a simple solution to me. Okay. Oh, sorry. Today I'm doing a lot of silly mistakes. Nice. Let's submit our code now. Nice. We got a really good point. गोयल दोनों नॉन नल होने से ट्रू कैसे कह सकते हैं? I didn't say that, Goel, but I just said to you that basically if both of them are null, only then we are saying that as true, because in that case both of the trees are empty. If both of them are non-null, then I am checking. Then I'm checking all the three conditions. Where the first condition is whether the value of the nodes are equal or not. If both the trees needs to be identical, okay, fine.
Hey guys, in this video we are going to talk about the problems of code drift day 1. The topics are binary trees and tries. So let's get started. The first problem is BST sum. The problem description states that the cost of an array ARR is the sum of all the values in the left subtree of the binary search tree formed by inserting the elements of ARR in the order they appear in it. Find the sum of the cost of all the permutations of length A. Since the answer can be large, we need to return it modulo 10 raised to power 9 plus 7. A permutation of length n is an array consisting of n distinct integers from 1 to n in arbitrary order. The problem constraints are n can vary from 1 to 10 raised to power 5. Now let us discuss the problem with an example. Now let us look at this example. We are given A as 3. That means we have an array of length 3 which have elements from 1 to 3, right? So all the elements are 1, 2 and 3. Now the permutations we can make out of these 3 elements are this one, this one, this one, this one, this one, this one. These are all the valid permutations we can make. Okay. Now we need to create binary search trees out of all these permutations. So let's do that now. So the first binary search tree will be, first we have 1 as the element, then we'll insert 1 here, then we'll have 2. For 2 we know 2 is greater than 1, so it will come to the right of 1. Then for 3 we know that 3 is greater than 2, so it will go like this. From 1 3 is greater than 1, so it will be on right of 1. From 2 it is greater than 2, so it will be on right of 2. So 3 will be here. Okay. Now let's talk about second binary search tree. In second binary search tree we have 1 3 2. So first we need to insert 1. After that 3 is greater than 1, so 3 will come on right. Then after that we can see that we have element 2 as the last element, so we need to insert 2 here. Now from 1 I know that 2 is greater than 1, so it must be on the right of 1. Okay. From 3 I know that 2 is less than 3, so it must be on left side of 3, so 2 should be here. So in that way we can create binary search trees. For the third one it will look like 2 1 3. Similarly in this fashion we can create all these 6 binary search trees. Now the answer to our problem is sum of all the values on the left subtree of each and every binary search tree, right? So the left subtree of first binary search tree, it has nothing on the left, right? So we don't have to add anything to the answer from this subtree. Now again for second one we don't have anything on the left, so we don't have to add anything here again. Now for third binary search tree we can see that we have one value here, so we need to add 1 to the answer. Let's say our answer variable is stored here and currently it is 1 because of this, right? After that fourth binary search tree have 1 in its left subtree, so I am going to add 1 here as well, so the value will become 2 here. Now for the fifth binary search tree I can see that we have 3 on the left subtree, 2 and 1, that is 3, right? Similarly here as well I can see that we have 3 on the left subtree, so I need to add 6 to the answer, so our total answer will be 8. So that is our final answer in this case. Now let us talk about the solution to this problem. Let's say we are given any binary search tree which is rooted at some integer a, right? Now all the values which are less than a should be on the left subtree of this a. Okay, let's say all those values are x, so all these values should be less than a, right? Similarly what will have on the right subtree? All the values which are greater than a, right? Now from this observation the conclusion that we can draw out is that all the values which are less than a should be present on the left subtree of a, right? So if we have any binary search tree that starts with a and it is some permutation, then I need to add all the values from 1 to a minus 1 to the answer. because all these values will lie on the left subtree of our current binary search tree, right? And as we know, the root of binary search tree is the first element of the array, right? So for each permutation, basically I need to add 1 to a minus 1 to the answer, sum of all these values to the answer. Now again, let us look at this example and try to solve it using the observation we just made. So for the first element, I need to add 1 to 1 minus 1, that is 0, to our answer. Since this range is invalid, we don't need to add anything. For this, again, we don't need to add anything. For this one, I need to add 1 to 1, or basically 1 to the answer. For this, again, I need to add 1 to the answer. For this, I need to add all the values between 1 and 2. So I need to add basically 2 plus 1, 3 to the answer. For this one, again, I need to add 3 to the answer. So the answer of all these permutations will be 3 plus 3 plus 1 plus 1, and that is 8 again, right? So basically, what we can observe here, if I know the root of some array, then I can calculate the answer for this array with a simple formula, right? What I need to do, I need to sum all the values from 1 to a minus 1 if that range is valid. Now the next thing that we need to notice is we are given all the elements from 1 to a, which is a permutation. Then let's say I fix the first element to x, then I have to choose rest of the a minus 1 elements, right? So that I can do in a minus 1 factorial ways, right? So if I fix my x, I know that I can choose the rest of the elements in a minus 1 factorial ways. So that basically gives us the contribution of this element to the answer. Now for any element x, the sum of all the values from 1 to x minus 1, it will be x into x minus 1 by 2, and I'll multiply it with a minus 1 factorial, because I can have this permutation a minus 1 factorial times with x as the root element, right? Now let us talk about the code. So our formula was we need to iterate from 1 to a, and for each number x, we are using this formula x into x minus 1 by 2, and we are multiplying it with a minus 1 factorial, right? So that is basically what we are doing here. But since we need the answer modulo some number, in this case 10 raised to power 9 plus 7, so instead of dividing by 2, I have already pre-calculated a mod in 2. It is basically the mod inverse of the current number. So instead of dividing by 2, I am basically multiplying by inverse of 2, or 2 raised to power minus 1. Now 2 raised to power minus 1 modulo 10 raised to power 9 plus 7 is stored in this number, right? So now whenever I need to divide, I'll just multiply by this mod in 2. And each time we also need a minus 1 factorial. So we are pre-computing a minus 1 here. Okay, so after pre-computing, what we'll do, we'll run a for loop from 1 to a, and we'll use our formula I into I minus 1. This is divided by 2, right? So that's why we are multiplying with the inverse of 2. And then we are multiplying that value with factorial a minus 1, and then we are taking the mod. And after that, we are just adding it to the answer, and then we are returning the answer. So it's quite straightforward. Now let us move on to the second problem. The second problem that we're going to talk about is max base pair, and the prerequisite to this problem is tries. You should know how the tries data structure work. So I'd highly recommend you to learn about tries first. Now the problem description is, you are given an integer array a. There's a function f for two integers x and y with another variable b base, right? Now for calculating the functional value, first convert x and y in base b, and then the ith bit of f x y b will be xi plus yi mod b. You have to return the maximum functional value possible for any pair of elements of array a in base b. Please note that you can take two elements for pair from the same index. Note, array elements are in base 10, and you have to return your answer also in base 10, calculated value from equation in base b. And the problem constraints are, a can vary from 1 to 10 raised to power 6, and each element of the array can vary from 2 to 10 raised to power 6, and the bases can vary from 2 to 9. Now let's talk about this problem with an example. Let's say we are given this example here. We are given an array of length 10, and we are given the base as 3. That means we need to first convert all these elements to base 3. So let's do that first. Now here I have converted each and every element to its base 3 representation. I need to find a pair whose sum is maximum base 3, right? And the sum that we are talking about it, let's say we are given two numbers. Let's say I choose this one, 12 and 101. Then how do I need to sum them? I'll write them here, 1 2 and 101. So what I'll do, I'll add these two, it will give me 3. I'll add these two, it will give me 1. I'll add this, it will give me 1. Now for each digit I need to again do a modulo by 3. So for 3, if I'll do it modulo 3, it will become 0. 1 modulo 3 will be 1 and 1 modulo 3 will be again 1. So the answer for adding 12 and 101 in this manner I am getting is 110. So that's how we need to add when we are talking about two pairs. Now we need to maximize the answer, right? In this example, we can see that if we take these two pairs, that is 100 and 101, and if I repeat the same procedure that I did here, that is 1 plus 0, that is 1, 0 plus 0 will be 0, 1 plus 1 will be 2. Now doing modulo by 3, it will remain 1, it will remain 0, it will remain 2. So I'll get 201 here. So for this specific case, 201 is the best we can do. Okay, so that's what we need to calculate for any array given to us. And if I convert 201 back to integer, it will be 19. So for this specific case, the answer to our problem is 19. So in this way, we need to solve this problem. Now let us talk about the solution to this problem with the same example. So basically, I have taken that same example. These elements here, they represent the value of 1 to 10 in base 3, right? So we have b equal to 3 here. So what we can do, basically we need to find any pair which can maximize our sum, right? So the first thing that I'll try to maximize is the most significant bit, right? Let's say we are given some number here, 2, 1 and 6. Now if I'll add 1 here, then I'll get 217. But if in the same number I am adding 1 here, I'll get 316, which is way bigger than 217. So basically the whole concept is, first off we'll try to maximize the most significant bit, and then we'll move on to maximize the second most significant bit, and in this manner we'll go from left to right. Now that we know we need to go from MSB to LSB, let's say we are at some number right now. Let's say it is 101. Let's say we are at last number right now. Then what I'll do, I'll try to find any number which can maximize it. Okay, so what is the maximum I can get at the most significant bit right now? The maximum value that I can make at most significant bit is b minus 1, right? That's what I can make. Currently we have 1 here. Then what is the value x that I will add to this most significant bit so that I can make b minus 1, right? That means I need to add b minus 1 minus 1. Okay, that is x, right? So the first thing that I'll try to search for is, do I have any number which is equivalent to b minus 1 minus 1, or basically b minus 2. Okay, so in our case b is 3, so 3 minus 2 is 1. Do I have any number in the third place which is 1? If we look closely into the array, we can see that we have one candidate here. Okay, the third digit of this number is 1, right? So we have just one candidate here, so we'll put 100 here. Why didn't we go further? Because we have only one candidate, right? But let's say we don't have one candidate now. Okay, let's take one more example here. Let's say we are given these 4 values which are in base 3 already, and we need to get the maximum pair I can have for each and every value, right? So let's say I want to maximize this 100. I want to find some pair that can maximize it. So what I'll do, I'll write 100 here. Then I'll go from the most significant bit. Okay, so what is the best I can make out of it? That is b minus 1 or 2. b minus 1 is equal to 2 here. Now what is the number I need to add to 1 which will make it 2? So obviously that number is 1, right? So I'll search for the candidates which have 1 on third place. The first candidate will be this one, second will be this one, third will be this one. All three satisfies the condition, right? Now let's move on to the second most significant bit, or this one. Now the second most significant bit is 0. Now again I'll do the same procedure. I'll try to maximize this 0. So what is the maximum I can get at this position? It is again 2, right? So I'll do the same calculation here. What is the value I can add to x that will make it 2? So I'll see that x equal to 2. So I'll try to find among all the candidates that I have selected, do we have any candidate which have 2 at its second place? So I'll see that I don't have any candidates, right? None of them have 2 at second place. Okay, fair enough. That means we cannot make our second digit equal to 2. Now since I cannot make 2, I'll try to make 1 at first digit, right? So what is the value I'll add to 0 so that I can make 1. So that is 1 obviously. Now I'll try to search for a number which has 1 at its second digit. Okay. Now out of these 3 candidates, I can see that this one and this one has 1 in its second position, right? Now this candidate is also neglected. So now we have 2 candidates which is maximizing my value currently, right? Since we have 2 candidates, let's move on to the last digit. Now again, I'll try to maximize my last digit. In order to maximize it, the best I can do is I'll try to make it 2 first. In order to make it 2, I'll try to find the number which have its last digit as 2, right? Now if I look at my candidates, these two, I don't have any of those values, so I cannot make 2. Now I'll try to make 1. Now again, I'll check which one of these have 1. So I'll see that my last candidate has 1, right? That means this guy can actually maximize my sum while I'm talking about this 100 value. So in this manner, we can solve this problem real quickly. But there's a catch. We need to find these candidates each time, right? For each digit, we need to iterate over all these candidates. But we can do it faster by using prefix trees or tries. So let's do that now. So basically, if we are given some array, what we'll do, we'll iterate from left to right. And let's say we are currently at this element, ith element. Then what we'll do, we'll try to build a try over all the previous elements, and I'll try to maximize my current element using the try I have built on the previous element. Now let us try to build try over these 3 values first. Let's say this is the root node of our try. Then the child at each level a try can have is b. Why? Because we can have values at any position between 0 to b minus 1. I'm going to insert this element first. So it has 1. So let's say this is 1. Then again 1. Then let's say this is again 1. Then 0. Let's say this is 0. Okay. Then I'm going to insert this value. Then it will be like 1. Here 1. Then again 1. Now another 1. Right. Now let's try to add this value. It is 1. Then it's a 0. Then it's a 1. Right. Now this is the try structure that I have built right here. Let's say currently I'm at this value. Then I need to find the optimal pair for it, right? So this is my value right now. So I'll start from MSB, that is 1. Now I will try to make it 2 first. Okay, so I'll search for a 1, and in our try we'll see that we have a node which corresponds to 1. So we'll iterate on that. We'll go there. We'll say okay, we are here now. Now from this node we'll try to check the second digit. Okay, what is our second digit? This is our second digit. We say that we need 2 here. Okay, so from this node I'll try to search for 2, and from this we can clearly see that we don't have any node which corresponds to 2, right? We have just 2 nodes. The first one corresponds to 1, the second one corresponds to 0. Okay, so we cannot make it 2. So now I'll try to make it 1. Now we can see that we have 1 here, so I'll go there. Okay, we can make 1. Okay, now that we are here, now I'll iterate on the last digit. So what is the best I can get at last digit? I'll try to make it 2. So I'll search for 2 here. I won't find any 2's, right? We have only 2 nodes, 0 and 1. So again, I cannot make 2 here as well. So I'll try to search for 1. Now we'll see that we have 1 here. So it will go in this direction. So what is the value that I got? I got 1, 1, 1. So again, I got the same pair 1, 1, 1, right? So in this manner, with the help of try data structure, we can do it efficiently. Now that we got the optimal pair for this element, so we can do it for each and every element of the array by iterating over elements from left to right. So that's how we can solve this problem. For better understanding, let's look at the pseudocode now. Now let us talk about the pseudocode. So let's start off with the solution function. So here is the solution function. We are given an array A and a base B, right? So basically, first we are converting each and every element of the array into its corresponding base B form, and then we are pushing that number to a vector named VEC. After that, we are creating a try node, which is basically the root node, and we are inserting one element. Why so? Because in order to get a pair, we at least need one element already inserted in try, right? After that, basically we are iterating from 1 to n minus 1 here, and what we are doing, we are searching for the best element before the current element which can pair up with our current element. So as we have done already in an example, for 100, this function will return 1 1 1. Okay, after that we are combining that and using another vector. So if we combine these two, I'll get 1 1 plus 0 1 1 1 plus 1 2, and doing it modulo 3, I'll again get 1 1 2, right? So that's what is going to get stored inside this answer vector. After that, I am getting the current answer by converting this digit back to decimal or base 10. Okay, and after that I am checking if this answer is the best answer, then I'll just insert it into the global answer variable, right? And after doing all these things, I am inserting our current element into the try data structure. Okay, so in this fashion we can get the answer, and whatever we get at the end, that will be the maximum optimal answer we can get. Okay, after that we are returning the answer. Now let us quickly see what these functions do. This first function, it converts a number to its base b form and returns a vector. Okay, and this function right here, it basically converts the given vector back to its base 10 decimal representation. Okay, and after that we have the standard try node, and then we have an insert function. In order to understand these functions of tries, you need to understand how actually tries work. And in this function we are basically iterating over the try and trying to find the best we can get for our current element. Okay, and this combine, the last function is this combine function. This basically do this operation. It basically adds up both of those vectors and then do the modulo thing. Okay, and then it returns the answer, which is again a vector. So that's pretty much it, and if you enjoyed the video, please hit the like button and do subscribe. Thank you for watching.
Hello everyone, my name is Abhimanyu. I am one of the co-founders at Scalar Academy and InterviewBit. And today I have Utkarsh with me.
Hello everyone, myself Utkarsh Gupta. I completed my BTech in CSE last year. So during my college days, I used to do a lot of competitive programming. And I receive a lot of questions to people asking how to start with competitive programming and what kept you going that you reached like high levels in Codeforces and CodeChef, like master in Codeforces and 6-star in CodeChef. Because what happens is many people start doing the competitive programming, but then in the between they stop. So today I'm here to answer all of those questions or any other question which you have. Also, in few days, we will be going live along with one of our Scalar Academy students, Naman, and we will also discuss about journey to Google. So that session will be held completely on Google questions and our journey, how we started programming and how we landed up in Google. Because it's very hard when you are from Tier 3 college to get a job at big companies like Google, Facebook, and so on. So me and Naman both are from Tier 3 college, so you will get to know how we practiced and how we reached Google.
Awesome. So, Utkarsh, I will start with some of the questions that were kind of very common when we were asking. So, I'll start with when and how did you get to know about the competitive programming during your engineering? How did you get to know about it, and when did you get to know about it?
Okay, so many students get to know about programming even in school days, but I was unlucky in that case. So I get to know about when I joined college. In my college, we have a NUT programming hub. I was lucky to have a programming hub in my college where my seniors used to tell us about the online platforms and the term competitive programming and also the benefits of competitive programming. So basically, I started with HackerRank practice session when I joined, and there was a lot of practice questions to do. And eventually, I switched to CodeChef because for a starters, if you take part in short contests, it's very hard to solve questions in limited time. But CodeChef long contest helped us in solving a same question in longer duration of time. So basically, you have 10 days to solve 10 questions. So even I used to spend 4 days on a particular question if I was unable to solve it. So this was my starting in competitive programming background.
I'll jump to a further question that when you started competitive programming, so what were the different platforms that you explored, and how did you choose, like, or how do someone choose that which platform they should focus most on for competitive programming?
Okay, so in the start, basically my college seniors told me about CodeChef and HackerRank. I started with CodeChef, but I found it very difficult because initially when you participate in any contest, you are unable to solve questions or you are able to solve only one question. So I switched to practice session. So HackerRank practice session I started for a while, and then again I started with competitions. Also, once I practiced a particular language and some data structure and algorithm. I also started with interview bit practice session, because in interview practice session we have topic wise questions, and I like the UI because whenever we click the particular question, the timer starts. So that timer keeps you motivated that you have to submit it as fast as possible. So if you will check out the interview practice session and you will click any particular question, you will see the timer and you will get to motivation to do it. And in the start, sometimes what happens is we see a question and we are unable to solve it completely, but we are able to think to some of the extent. So there we also had a hint section in which we can click hint and we can see some of the optimizations or some of the help which can lead us to an optimal solution. So that was also really useful, because when you are starting programming and you don't have anyone to tell us, either you can like do it on your own or you can see the complete solution. So to have something which is not telling us the complete solution but giving us some hints so that we can move towards the solution, that was really helpful for me in the start.
How different is reaching 6-star in CodeChef versus getting rank 1 in Google Hash Code? That you have been at both the places. How different are these?
Okay, so reaching 6-star in CodeChef is very different from getting rank 1 in Google Hash Code. Reason being, in CodeChef you have 3 contests every month, like CodeChef long and short contests. So every month you can try and do participate, and maybe if you are lucky enough, you can have higher increase in the rating or sometimes fall in the rating also. So rating keeps on changing every month. On the other hand, Google Hash Code occurs only once a year. And last year was the first time when Google Hash Code was live for the global, like for everyone, for every country, because before that it was limited to some countries. So last year, India got the chance to participate in Google Hash Code, and luckily I was able to score first rank in Google Hash Code from India. And globally, my rank was 47. I was about to go to World Finals, but unfortunately, they selected till 41 rank only. So if you have to like get a good ranks in international competitions like Google Hash Code, Google Code Jam, or Google or Facebook Hacker Cup even, then you get only once a year chance. So that is pretty hard compared to increasing ratings on platforms like CodeChef and CodeForces, because there you can practice frequently.
Great. How to master DP? Please suggest.
Okay, it's a very common question among all the programmers who start programming and like computer programming, because there is no thumb rule to solve any DP question. I mean, it can only come with practice. Practice is the main key for dynamic programming. However, you should start step by step and not start with directly very hard dynamic programming questions, because sometimes what people do is they see a dynamic programming question which is of a harder level, like dynamic programming on trees or digit dynamic programming, and they think that dynamic programming is really hard. I mean, not of their type, but that is not true. I mean, if you start step by step solving easy problems for dynamic programming first, and then medium level questions, and then jumping to a harder questions, you will realize that it's not that complicated, because all you have to do is find a pattern in a particular question and see how that pattern leads from a smaller solution to a bigger solution. So start step by step and do as many practice as possible. I mean, as much practice as possible, because practice is the only key for dynamic programming. That is what I can say.
Yeah. Why did you leave Google?
Okay. The main key or the main line is that whenever you are doing any particular job or you are spending a lot of time on particular thing, the question that comes to your mind is, are you enjoying it or not? So during my college days, I did a lot of internships and I had a lot of experience in different companies like HackerRank, InterviewBit, Microsoft, even Geeks for Geeks. And my personal experience was that I enjoy working in companies which are startups compared to companies which are MNCs. Reason being, in startups, you get a lot of ownership, you get a lot of pressure over your head, so you have to complete the work at particular time, and even whatever you do can directly come into production and you can see the users using it, compared to MNCs where you have to do a small task in a big project and you have to take a lot of approvals before pushing it to production, and you feel that I was feeling that my work was little small compared to the bigger picture, which is actually true, because in big companies even the small change can impact a lot of people. Also, the second thing is I like to teach compared to do software development, because since my college days I used to take lessons on programming and used to teach my juniors, even my college mates. And so here at interview bit, I got both the opportunities. like to be a lecturer at Scalar Academy and also to do some development tasks. So being a lecturer is really an good opportunity for me here. That's what I can say, because that I really enjoy and like to continue for a long time.
Cool. How to improve speed in solving code forces div to C and D problems? Like speed, of course, is one of the key factors. So what was your strategy to improve speed in during competition?
So for code forces competitions, very good thing is that we have an option of doing virtual contest. So virtual contest is like you can select any contest and you can start a virtual contest anytime you feel like, and you will feel that an actual contest is going on because you will see the submissions as they were submitted in the live contest. So after 5 minutes, let's say someone has submitted a question, you will see that after 5 minutes only. So it's kind of having a contest whenever you feel like, but it will not affect your rating. So if you have solved, like if you want to improve your practice or improve your speed, you can have like daily a virtual contest or as frequently as possible. So you will get a 2-hour window and you can see how many questions you can solve in that 2-hour window. So that will help you improve your speed, because in 2-hour window, let's say currently you are able to solve only 2 questions. Then over the period of time, if you will do like 5 or 10 virtual contests in a go, you will see that, okay, those 2 questions I'm able to solve really fast. And now also I can solve C question. And one more important thing is, even if you do a virtual contest or a live contest, doing a contest is not important as compared to doing the upsolving, because in contest, you do whatever you know. I mean, you implement your knowledge and it gets submitted. But the part where you increase your knowledge is basically upsolving. Now, what is upsolving is, let's say if I have solved 3 questions in a code forces round, A, B, and C, and I tried D question, but I was unable to solve, and there may be a lot of reasons for that. Maybe because I was having very less time, I was having, let's say, 10 or 15 minutes to solve that question, or maybe the topic which was required for that question, I was unaware of that, or maybe some corner cases are missing. So after the contest, if you check the D question, maybe you can try it a bit more, but if you are still unable to solve it, then try to see the editorial and try to learn from it. The reason why you were unable to solve the question is what is the new learning for you. Because let's say if you are able to solve that question after the contest or after seeing the editorial, then you have gained some knowledge which will help you improve in further contests. So every contest you should at least absolve either 1 or 2 questions. But also sometimes people say that why not absolving all the questions? So like if you will see the last question of a contest, like div 2E questions, sometimes the submission are very less, like even less than 100. The reason being that some topic which is required in those questions is very rare and it's not asked frequently. So for a beginner, learning those topics is not required. So if you see a question which has very less submissions, you can skip that for the starts. But as you grow up and as you improve in competitive programming, then eventually you will see that maybe now it's the time to solve those questions which have very few submissions. So for the starts, skip those questions with few submissions, but try to absolve the questions which you are unable to do during the contest.
Cool. I'll take up this question now. How did you practice and prepare for the hash code? And given you managed to get rank 1 in India, which is a great achievement, it would be to hear from you. I'm sure for all the students who are watching, that what was your strategy to prepare for that?
There was no particular strategy to prepare for hash code, because I mean I was not sure whether I will secure a good rank or not, because it was just out of fun that in the final year we were free and we saw that there's a hash code competition going on, so let's participate. The hash code is different from other competitions in a way that it only has one question. That question does not have any particular solution. You have to give your best solution and relatively the markings will be. So the person who has submitted the best solution will get the highest marks, and our solutions will be compared to that particular person's solution, and based on that we will be evaluated. So we have different test files, but the question is only one. Now, to prepare for such a contest, we don't have a lot of platforms. So, but in CodeChef long contest, there is one question which is based on relative ranking. So if you are preparing particularly for hash code, I recommend solving the question on CodeChef long, which is relative question, which does not has any particular solution, but your best solution will be evaluated. based on someone else's best solution, and you will see the difference between the scores. So this is a particular strategy for preparing for hash code.
Cool. So Anish says that he is afraid of taking part in short contests, although aware of the importance. So Utkarsh, if you have ever felt this, because this is very natural, I'm sure in the early days when we are not that well prepared, there is certain hesitation to even participate in things that we believe is harder. How did you overcome that?
Yes, so as I mentioned, when I started computer programming, I tried to solve contest on CodeChef, the short contest, but I was able to solve only one question in some and even no question in any contest. So that time I was also nervous, and I thought that maybe this is not a thing for me and I will never be able to do it. But the right way to do this was to see what we are lacking. So there I noticed that I did not know even the basic things. Like, so I do computer programming in Java. Most of the people use C++, but it does not matter whichever language you use. You should at least know all the STL or all the inbuilt functions in that. So let's say if I have to solve a question on strings and I don't know how to find a substring, then it is not a right start for doing competition. So what I did was I first learned all the inbuilt functions which are there in Java, like all the string functions, then the array list, then using the stacks and queues, which are really, really important. And then when I learned the basic concept, like very few basic concepts which can help you solve easy questions, then I switched to solving competitions. And I recommend start with virtual contests and code forces. So in virtual contest, you will not have any rating change or anything, and you can see that how well you are doing or what improvements you can make. And once you do a couple of virtual contests, you will be confident enough to now sit in a real life contest. So just first step is to learn all the basic stuff in the programming language in whichever you code, maybe C++ or Java, or even Python if you code in Python. But I recommend Java or C++. And try to learn all the inbuilt functions. Even the stacks and queues are really important for the beginners. So just learn. It's very easy. Just when you solve one or two questions based on that, and you will see how you can use stacks, queues, or array list, or string functions. And once you do that, then you can start with competitions, and you will feel really, really confident. Because in every competition, the starting questions really do not require any hard code algorithm or any hard data structure. First two or three questions are really simple. They just require some thinking process and some basic knowledge, which you can easily learn in few days. So start with virtual contest and then switch to real contest if you are afraid of taking part in short contest.
All right. Please tell us about the mathematical approach for problem solving and what are the good platforms to get better at problem solving. So about the mathematical problems, back in our days when we graduated in 2010, we used a lot of problems on Project Euler. That it was pretty good platform to solve mathematically hard problems. But yeah, so Project Euler is one. So would you like to share more resources on learning the mathematical approach for problem solving?
Yes, sure. I mean, as sir mentioned, Project Euler is really good platform for only mathematical questions because you can learn from every question which is present on Project Euler. Even I used to do Project Euler a lot in my college days because I also faced a lot of problems in mathematical concepts. Even some topics like geometry and probability are really hard in the startings. But when you solve as many questions on each particular topic, then it becomes really comfortable for you. So let's say I have to practice on probability. First, what I used to do is I used to study basic things in probability. And basically for probability, the basic requirement is PNC, permutation and combination. So study that a little bit. And then start practicing at least 10 or 20 questions on probability, which are available anywhere online, maybe past code forces round contest or code chef contest. You can easily filter them. The strategy which I used was to sort them based on the number of submissions. So if you can see that if any question is submitted by, let's say, 7,000 or 8,000 people, then you can assume that yes, that question is easy because therefore a lot of people have submitted that question. So start with an easy question of a particular topic. So you get little by little confidence. That's how our mind works, right? I mean, if you do anything in life, first, if you pick up a hard part of that, let's say if you join a gym and you try to pick up 30 kilo of weight, you won't be able to pick it. And you will feel that, okay, gym is not my kind. And similarly, competitions is the same. You cannot do hard question in the start. So step by step is the strategy to do it. So any particular topic, even maths or probability, just learn some basic concepts of maths first, then start with easy questions of that, and then step by step move to the hard questions of that. And for the platforms, there's a Facebook link in the description below. You can check that out, where I have listed all the links, all the useful links in that Facebook page which I used. Even dynamic programming is organized, properly mentioned, step by step, how you can learn dynamic programming from basic to advanced level. Even maths, I have mentioned a lot of links, including the project where you can check that out. And there are a lot of available links online. But the main key is to do things step by step and not to do hard questions in the start.
How much time in a day should one keep in reserve to practice dynamic programming?
There is no fixed duration of time. Like every day, you cannot fix 1 hour that I will sit and do 1 hour computer programming, and then rest of the day I will do something else. So it depends on your schedule, your personal schedule. Let's say if you are in college and like during daytime you have to attend college lectures and all, and evening you have to do some projects. So the night time is the best for college students, which I can say, because I also used to do computer programming or my stuff at night. After dinner, you can sit around at 9 p.m. and used to go till 2, 3, 4, maybe 5 or 6 and do breakfast and then sleep. So it depends on your personal schedule. So if you are an employee, then you have to get up early in the morning to go to job, and so maybe evening time will be suitable for you. Also, just do it regularly. The main key to do any practice in anything is to do it regularly. So you cannot say that every weekend I will practice, because that will break the schedule. So let's say if Saturday, Sunday I solve 20 questions, and next Saturday, Sunday I sit and again I try to solve 20 questions. There's a lot of gap, like 5 days gap. So that is also not good for mind. So try to solve at least one question daily. That is the minimum possible what you can do. But if you have a longer duration of time available, then try to solve as many questions as possible. Also, the count of question does not matter. The learning you gain from every question matters. So during the start, even for one question, I have spent 4 days. So when I used to do CodeChef long challenges, I used to solve 1, 2, 3 questions, but the fourth question was really hard for me, and I used to spend literally 4 days thinking of that question everywhere I go. In the lecturers also, I used to sit and solve and try to see what is the solution. And sometimes it works, sometimes I get to the solution and I used to submit, but sometimes I was unable to submit it. Then don't regret, even if you have spent, let's say, a complete day. Just don't regret that, okay, I wasted my day. What you learn that day is that how you can differently approach that problem. So let's say if you have spent a day solving a particular problem, then you might have approached that problem in many different ways, and neither of them gave you an answer. So when you will see the complete solution, or when you will see the editorial, you will get to know the difficulties or the problems in each of your approaches. So each of your approaches will get clarified in your mind. Okay, when I was applying this approach, this thing will not work. So next time I will keep in mind that this approach cannot be applied on such particular type of questions. And I can give you an example. Like few days ago, I tried to solve one question on code forces. It was like E-level question. And I spent literally 2 to 3 hours on that. And still it took a lot of time to solve. 2 to 3 hours. And still I was unable to solve it completely. So I checked the editorial and I was missing one small thing. What can happen is that you spend a lot of time and you were lacking with one small thing. So in that case, please see the editorial, and even after seeing the editorial, try to submit the solution. Sometimes people just see the editorial and see that, okay, this I can code, just leave it. That is not right. After seeing the editorial, if you code and submit that the concept of that question will become more clear to you. So please try to submit the question even after seeing the editorial. I hope that will help.
Cool. I want to give Google Kickstart. I'm a 3-star on CodeChef. Was attending CCD SAP Advanced on 22nd, but it got cancelled. And Kickstart is difficult. What kind of problem should one practice on?
So if you have to practice particularly on Kickstart, I recommend solving the previous questions which have appeared on Kickstart. So if you will go to the link of Google Kickstart, you can see the past contests and the questions which have appeared in past. So try to solve the questions which have appeared in past. That will help you realize what kind of questions you can expect, because Kickstart questions are little different from the questions which you see in normal competitions of Code Forces and CodeChef. So Kickstart questions, if you are practicing specifically for them, just try to solve previous Kickstart questions and you can map what kind of strategies are required. Because they do not require hard code algorithms and advanced algorithms. They require a lot of thinking. So that is, I can say, is the best strategy for practicing on Kickstart. Also for 3-star on CodeChef, don't worry. I mean, if you give a lot of contests, it will eventually improve. Just don't stop giving contests. That is many people do. They stop and then they regret it. So just keep on going and eventually you will move to 4-star, 5-star and 6-star and so on.
So yeah, I'll pick up this one. Try another disjoint sets, etc., and similar other advanced data structures. Do you think they are important or not? If they are,
Yes, for segment trees and DSU, disjoint set union, they are really, really important concepts. I mean, either you should know segment tree or Fenwick tree. Otherwise, you won't be able to solve questions which are related to range queries. So for range queries question, the main topic is segment trees. I mean, some questions can be solved in other ways also, but segment trees is really important because whenever you see a question of any range query, let's say you are given a range and you have to find the sum of all the elements, and their or update is also required. I mean, in the queries, you can either update the element or you can find the sum of all the elements. So such kind of questions can only be solved in segment trees. Otherwise, if you will try brute force, it will be order n square and you will get TLE. I mean, so even some companies also ask some range query questions which can be solved using Fenwick tree and segment tree, but they are really easy. So you cannot expect really hard segment tree questions on companies, but for competitive programming purpose, they are really important. Secondly, for try, yes, it is also a really important data structure because it helps you store the string in an organized fashion. So if you have to store a lot of string like in dictionary order or so, then try is the only data structure that you can use. So my recommendation is to learn segment trees, tries, and disjoint set union kinds of data structures because they are really, really important and they are not really hard. I mean, if you solve 10 or 20 questions on that, they are easy. Some concepts are really hard, such as heavy light decomposition or centroid decomposition or persistent segment tree. For such concepts, I can say that you can leave them for now. And once you are starting object programming, just ignore those topics. Just focus on these topics. And with time, when you get comfortable solving these topics and you get comfortable in solving these questions really fast, their questions really fast, then you can pick up hard topics like heavy light decomposition or centroid decomposition or FFT or so. But don't go with them in the start. But yes, segment tree is really important in the start.
so where to find the best Python resources? And actually, the context of the question is a little different. That often, when even when knowing the approach, the right approach, and the best optimized approach for a problem, often Python, given it is by design slightly slower, it accepts time limits, right? So, is it advisable to switch to C++ or other languages? Such things from a competitive programming point of view, and for Kickstarter as well, or does it make more sense to try to learn more optimization techniques of Python itself?
So to answer this question, I mean, both the approaches are correct. There is no right or wrong in this because the competitions like Kickstart or any online competition, they are tested for Python. So you can expect that there is a Python solution which will run. But sometimes what happens is that we are unable to optimize it, and sometimes we think that Python is slow. I mean, Python is relatively slow, like for in comparison to C++, it is 5 times slower, you can say. But the time constraint for Python is again 5 times. So you can expect that there is a solution in Python which will submit. But as you mentioned, for the resources, since we do not have a lot of programmers or competitive programmers which are doing in Python, so it is really hard to find resources on Python. So I recommend to switch to a language like C++ or Java because you can easily find a lot of resources, so you can easily learn them. And also you can be sure that they will be submitted. Because let's say if any Kickstart contest is there and a C++ solution is not working, then there will be a lot of students who will say about this that the question is not working in C++ or we were unable to submit because of lack of testing or so. So in that case, jury will take serious actions. But for Python, I guess since few people do it and few people approach or few people say that the solution is not working, so that is not, I mean, taken that seriously compared to C++. So I recommend to switch to C++ or Java. But if you are very bold or very stubborn about Python or you love Python with your life, then you can study Python as well. I mean, there is a solution in Python which is acceptable. You can trust the testers of the competition for that.
Great. I'll pick up the next questions. This is an interesting one. So while definitely in most of the times, we have college students pushing on to the CV. Of course, there is no age to do computer programming, right? It is a lot of fun. And once we start doing it, we see how fun it is, right, to be into that arena. So here, Sahil has a question that as a 3-year experienced Java developer, what would be your tips as a working professional and still participate in CP?
Okay. So for college students, initial push they get is to get a job, and CP will help in get a job. But as you are already a working professional, so that is not a reason for you. I can understand. Now, the reason behind you starting CP should be clear to you. I mean, if you are doing it for a particular reason, like if you want to achieve good ranks in international competitions like Google Code Jam, Facebook Hacker Cup, and so, then you should practice them on regular basis, very frequently, because they are really hard. I mean, a lot of best programmers are doing that. So if you are aiming for international competitions, you have to put a lot of effort. But if you are doing it for fun, then you can map it with your schedule. So I can understand being a working professional, you have a lot of deadlines, lot of projects to complete. So based on your schedule, you can take out time like twice or thrice a week and then solve any competition or practice questions if it is just for fun. Because even if it is just for fun, it keeps your mind sharp and improves your thinking ability. So the problem solving skills really improved. And the problem solving skills which you improve here are not only applicable to computer programming, they can also be mapped in real life. So if you will do a lot of computer programming, you will realize that even in real life, whenever you face any problem, you are able to approach the solution to that particular problem in multiple ways. This I have personally experienced. So I can share my experience with you. I mean, it's a little funny. So when I was in Munich, I mean, in Munich, the bathrooms do not have that place where the water goes because it is little above the floor where you can only take baths. So near the toilet seat or near the basin, you do not have that place where the water goes inside. So by mistake, I spilled a lot of water, and I was not knowing there is no place there water can go. So water was coming out in the room, and it was like all watery. So at that time, it struck me what are the different ways which I can solve that or what I can do. So I quickly looked at a toilet paper. So I just unfold the toilet paper and spread it in my entire room and entire bathroom. So the liquidify water become little solid. So you can pick up a toilet paper which is wet, but you cannot pick up water, right? So all the toilet paper become wet and it soaked all the water. And I used to like pick it up and throw it in the dustbin. That is the way I used to like stop water from entering the entire room and like making everything wet. So in real life also it is really helpful.
No, for sure. Being able to figure out elegant, simple solutions to seemingly harder problems is, it's a life skill, right?
Yes.
Which level problem should I participate for a start, Div 3 or Div 2?
Division 3. Okay, so code forces have three divisions: Division 1, Division 2, and Division 3. Division 1 is really hard. Division 2 is for medium level, and Division 3 is really for the starters. Now, if you are starting computer programming, then Division 3 is really best place to do it, because in Division 3, the first 4 or 3 questions do not require any data structure or algorithm knowledge. Only requirement for following first 3 or 4 questions is that you should know a programming language and you should know the basic functions as I mentioned. So if you are good in problem solving and good in thinking solutions which are not relevant to any particular topic, just you are given an array and you have to do some optimizations on it, then you will be able to solve really easily division 3 questions. And definitely division 3 is really the best place for any programmer to start computer programming. That will I surely recommend. But back in my college days, we do not used to have division 3 because then it was only division 2 or division 1. So starting on code force was really hard. But now they have introduced division 3, so please take advantage of that. That is really, really helpful.
Great. How did your schedule change when you were preparing for Google?
I will not discuss the details, but there was no change in schedules. I mean, basically, when I was practicing for computer programming, it was in my first, second, and third year, or even my second last semester when I was participating in ICPC. But my last semester, I was really free. I mean, there was no lot of work to do, and there was no competitions coming up. I mean, there was hashcode, but was not actually preparing for that. So for preparing for company interviews like Google and lot of other interviews which I gave, like coordination and other interviews, what I did was I saw platforms which are dedicated to helping us solving questions which are asked in interview. So you can see the interview bit practice session, and you can see the questions are tagged with a particular company. So I used to solve the questions which are asked in Google previously. So I can assume that, okay, similar type of questions will be asked to me in Google. But really, if you will see, if you are a good competitive programmer, then solving algorithms and data structure of interview level question, interview level question is really easy compared to solving a D or E level question on code process. So if you are a good competitive programmer, then solving interview algorithm data structure questions is really, really easy for you. So don't worry about preparing for Google interviews if you are good competitive programmer, because the good thing in Google is that they don't ask theoretical concepts like operating system or database. They just ask algorithms and data structures if you are applying for a fresher. This I'm only talking for a fresher because I directly joined Google after my college. If you're applying after experiences, then yes, there will be system design rounds. For that you have to prepare separately. But for a fresher, you just need algorithms and data structure knowledge, which you can learn from while doing CP as well. But if you have shorter duration, then I recommend going to platforms and solving only company specific questions, which are already asked in Google before. So that will be a good strategy to do it.
Great. So here is the question that Mansi has asked, that how to create new innovative problems for contest as a problem setter. So this is like slightly different side, right? That one as a participant in the contest, and of course you have been also creating and setting quite problems. So shed some light on that. How do you come up with ideas for new problems?
Okay. So my first problem setting was done when I was in college, and when you were in third year, like as I mentioned, there was a programming hub. So when I was in third year, I used to manage my programming hub, and we used to have contest every semester. So I used to organize contest and make some questions for that along with my friends. So there I learned is that problem setting is not that difficult. What you have to do is you have to make a problem statement which is based on maybe some particular topic, if you want to involve a particular topic, or some thinking process. So such that, let's say if you are given an array, then there are a lot of things you can do with array. So just try to think that what are the possible things you can do with array. So let's say if I've been given an array, then if I want to make a question of 2 pointers, then I can take 2 elements and do anything with that. So I can return ai minus aj modulus of that, or I can return ai's or aj of that, or I can take 3 variables on that. Or let's say if I have to make a question on segment trees, then what I will do is I will make a range query question, or I will try to make a question which will not look like a range query question, but eventually it will become. So if you want to a hard level question, then we have a concept in trees, tree flattening, in which you will flatten a tree based on their levels and then you apply segment tree on that. So if you are clear with whatever the concept you want to apply in that particular question, then just think what are the different ways you can modify that concept, and then you will be able to come up with a question. Now the thing is, sometimes people think is that let's make a question only if it is solvable in order of n, and if it is order of n square, then it is not a good question. That is not a right strategy. Sometimes I even prepare a question which has order of n cube complexity, and that is the best complexity possible. But people are unable to solve it because people just start with order of n complexity. They forget to see the constraints and they start, okay, let's see how it can solve this in order of n, and in the end they were unable to solve it. So whatever question you are setting or problem you are setting, just don't worry about the time constraints. Just worry about the topic, or if you are making an ad hoc, then the question concept, and then try to solve that particular question which you have think in a best possible way, and that will make a question. And don't worry about the solution for that question first. I hope that will answer.
What is a better approach, following a CP book like Felix Salim, or going through A to OJ ladder, or going through contests and editorials? And of course, it's like, when there are so many things, it is obvious to get overwhelmed and thinking that by picking one, we are missing on something.
Okay, so for this particular question, Shivam, I can say that there is nothing fixed. No strategy is better than the other strategy. But the main key is that you should fix to one particular strategy. So let's say if you like to read books, then pick up a book like Corman is there and a lot of other books are there, and try to read that, and then just ignore the A to OJ letters and ignore the practice session of the contest. If you don't like to read books like me, I mean, I don't like to read like computer programming books because I used to practice them online. I like when I submit the question and see the green tick. Then in that case, yes, A to OJ ladders are really helpful because they have ordered questions from starting from easy to difficult, and the ladders are based on their code forces rating. So you can see that if you are like having 1400 to 1500 rating, you have a particular set of questions dedicated to you. If you have high ratings like 18 to 1900 ratings, you have a particular set of questions dedicated to you. Then A to OJ ladders are really useful. But the main thing among all these is that you should regularly take part in contest. You should never skip contest, even if you are doing reading books or you are practicing online, because contest will help you know like how much you have improved. So let's say if you give a contest right now and you score a rank of 1000, and after 1 month you give a contest and you score a rank of 700, you will see the improvement, and that improvement will keep you motivated to move further. So one thing which I used to do is I used to target my rank. So when I used to start, I used to target like I will score under 1000 rank in this contest, and I will score under 500 rank, then under 200 rank, and so on. This keeps us pushing. So initially, if you are targeting for 1000 rank and you are giving contest, few contests you won't be able to achieve it. That is true. But after a few contests, you will say that okay, one day you achieved it, and that day you will really be happy that I set up a target for myself and I was able to achieve it. That will give you motivation to move further, and then you can set a target of 800. When you achieve a 800 target, then 800 rank target, then you will be really again happy. And you should always celebrate when you achieve your targets. I mean, setting small goals, achieving them, and celebrating them is the key to do anything in life, not just computer programming, but anything. Because I know you all have big goals in life, but try to do step by step. So set up small goals, try to achieve them, and when you achieve them, just celebrate, because you will get motivation. You will get motivation and you will move further, move more ahead, and you will improve in life. That is the best answer I can give.
Utkarsh, that like climbing a huge hill, if we can just step every single achievement, that is when we can we can get anywhere. But just keep just dreaming of something really big and not measuring what we are doing every day, that doesn't get us anywhere.
Yes, so true.
What is the key difference between a problem solver and a coder? What steps to follow to become high level problem solver? Because I would love to hear you. I would also maybe share my 2 cents on it.
So the difference between the terms problem solver and coder is that if you are a coder, then you are able to solve a particular problem in any programming language and you are able to submit it. Even if you are good in development, then developers are also coders because they code a particular, let's say, mobile app or a game. And problem solver is a term which is in general for any problem, like problem of life or any even computer programming or any other problem. So these are two different things. For being a coder, you need to like have some concepts, like you have to learn a particular language and you have to learn some data structure algorithms and so on. For being a problem solver, you just need clear concepts in whatever field you are working on. If you, let's say, want to do dance, I mean, dance is not my field, but let's say if you want to do dance, then if you just play a music and then you start dancing, that is not, I mean, that is good fun, but it is not a right way to learn that. So even dancers or even sport persons like badminton players, cricket players, they follow some particular strategy to solve, like to improve. Because problem solving is a skill which you can implement in anywhere in life. It is not just limited to computer programming. So you can assume problem solver is a superset, and like computer programming is a subset of that problem solver. And coder comes when you implement that problem in a code, and maybe development or computer programming both.
That if you look at people who have, like, even as a coder, people end up being extremely high impact even as a coder. Usually they are also great problem solvers. I can also give one example, that the other co-founder of Interview, he has been an excellent problem solver. And we were in college, so both of us, we were in college together. When we were in college, he represented India in ACM, ICPC World Finals twice back to back. They couldn't third time because ICPC doesn't allow the same team to come more than twice, right? And at the same time, he is also the person who led the team which built Facebook Messenger. So while building Facebook Messenger, scaling it to 500 million users or more, they were functioning as a coder there, maybe developing something, but the capabilities to solve extremely complicated problems as a problem solver, which also led them to grow a lot and achieve big things in competitive programming, also helped them to be exceptionally good at building something which 500 million people, like half of India, like can use at the same time. Right? That's a big achievement.
Yes.
So being a problem solver enables you to be much more capable coder as well. Right?
Yes.
As Utkarsh said, that being a problem solver is the superset. Competitive programming is a subset of that, and being a coder is another subset of that. Becoming a problem solver enables you a lot more to achieve much more in all the spaces. It's a life skill, as I was saying earlier, that being a problem solver is a life skill. It's not just code.
Okay. One question which generally people ask me is how to prepare for team contest versus individual contest. Let's take that. So if you are preparing for a team contest, it is different than preparing for an individual contest, because in individual contest you have to practice all the concepts on your own. But if you are preparing for a team contest like ACM, ICPC, then you have 3 team members, right? And it's not good that all the 3 members are really good in maths and not good in graphs, let's say. So what my strategy and what I suggest you guys to do is that if you have 3 people, then first step is divide hard concepts. Like one person can take the responsibility of solving maths questions like probability and geometry. One person can take the responsibility of solving dynamic programming questions. And one person can take the responsibility of solving graph related questions, because these 3 are the topics which require really hard work if you have to become good in them. And the smaller easy questions, I guess all the 3 can do. The second important thing in team contests is that the trust, which people sometimes do not have, which I see that 2 people have a solution to a particular question and they start fighting that my solution we should write and my solution. You should trust your teammates. I mean, if you are a team and someone is saying that he or she has a good question or good solution to a problem, just trust them and then let them submit. Also, the third important thing is to prepare before the concept is that who will solve the initial questions, because initial questions are really easy and everyone can solve. So give that responsibility to someone who is a fast coder in your team. That person maybe can submit first 3 questions. Meanwhile, you can solve a hard question and then later on you can submit that. So team strategies are really little different from individual strategies. And if you are preparing for ACM ICPC, I recommend having a team 6 months at least before the competition, so that you can practice in team a lot, because that really helps.
No, very interesting, Utkarsh. And actually, another parallel that I can draw, that the strategy or how you function in a team contest is different. And there are a lot of parallels that I can see between building a startup, running a startup, and the contest. 2 key things, like actually me and Anshuman, when we were in college, I remember when preparing for the contest or building projects as a group. Now running this company for 5-6 years. 2 factors. One is complementary skill sets, right? That, as you said, that you divide topics, that some person can just focus on getting much better at, say, graphs or dynamic programming, and someone else picking up another subset of topics, which that means that if team members are, getting very strong at complementary things to each other, then they can much more capable as a team, right? And second one is having trust in your team, right? Being in a competitive program or running a company together, one very important thing is that you just trust the people with you, right? That if they are saying something, often you just take it at the face value. You trust the person that if he's saying it, it must be right. Because 99% of the time it is right, and for 1% fine, it is okay. So definitely very, very interesting inputs on the team dynamics of succeeding in team contests.
Yes.
Thank you, everyone. Thanks, Utkarsh.
Hi, everyone. Thank you for joining. My name is Anshuman, and I'm going to be taking this session on how to get started with competitive programming. Now, before I begin, a little bit of background about why am I able to even advise you on how to begin with competitive programming. I myself was a very active competitive programmer back in my college days. So I graduated from IIIT Hyderabad in 2010. By that time, I had represented India twice in ICPC World Finals. This was in 2009 in Stockholm and 2010 in Harbin, China. That, along with, I was very, very active in a lot of programming competitions. So back then, me and my team, we had won a lot of contests as well. And we had a bunch of learnings during that time, and therefore I'm here to just share some of those learnings on how to begin, what approach to take, and what common mistakes do people make. Now, before I begin, let me first set context on when should you even look at optimizing for competitive programming. It is very, very important to understand that competitive programming is a sport. And if you're just doing it because you want a better job, then you don't need to do competitive programming. It's an overkill. You probably are better off maybe by referring to sites like Interview Bit, Lead Code, understand the topics, and which are again fewer in nature in the case of interview prep. Do practice on problems there. Competitive programming is much wider in nature. For example, there are topics like computational geometry that probably would never surface in a interview. Or for example, there are advanced topics in graphs like network flow or articulation points and bridges that might not surface in an interview, but there is a very high probability that it would actually surface in an interview. The other thing is, for example, in a real life competitive programming in setup, you might have problems with precisions that you would have to deal with as you calculate probabilities and so forth. Again, those kind of problems you might not face at the same level in an interview. So if your purpose of doing competitive programming is to make sure that you do well in interviews, it's an overkill. I would say do it because you love it and you see it as a sport, not really the right thing to do, or maybe right thing to focus your effort on if the end outcome is only an interview. But that being said, let me actually talk about how do you get started with competitive programming. The first thing, and this is the most common mistake that I see people do, the most common advice you will get from all seniors is that the only way to learn competitive programming is practice. Practice as much as you can, and then look at problems, look at solutions, which is a good advice. However, it is important to make sure before you start following that advice, there is a base of concepts and there are fundamentals that you've built. So there are basic topics that you already have studied. You have done practice on easy problems there. You're comfortable with those topics, and then you start this second phase of practice. So therefore, plan is phase number one. Phase number one is where you start with basic topics. Now, what are basic topics? If you go on, some websites actually do list out those topics in increasing order of difficulty. But let's say you're somebody new to data structures and algorithms. The first thing you should do is cover whatever is there in data structures and algorithm. For example, there is, if you go on interviewbit.com, which is a free website, there you would see the topics laid out in increasing order of difficulty. So you have arrays, then you have math, binary search, strings, bit manipulation, two-pointer approach, which is window approach, linked lists, then you have stacks and queues, then recursion and backtracking, hashing, heaps and maps, tree data structure, dynamic programming, greedy algorithm, and then finally graphs. These are, again, like when I say like go through these, you first, read through the concepts. For example, when you study about dynamic programming, what exactly is a dynamic programming? You start doing some very easy problems on those. That helps you at least understand those concepts well. There are obviously, like for competitive programming, going to be more concepts, more data structures that you'll have to learn. I'll share that too in the meanwhile. But if you directly jump to competitive programming without understanding this, then you will struggle. You'll struggle. It will just be a longer journey for you. So that's point number one, which is going through this. The second part is then what are the additional topics required for competitive programming? There are few that are actually unique to competitive programming and probably are not part of the most commonly used data structures algorithms. There are data structures like segment tree and Fenwick tree. Those might not be very, very commonly used in normal DSA setup, but like they are fairly common in the competitive programming circle. So that's one. The second is there's an entire field on computational geometry. Now this is where you have to like calculate the convex hull of a given set of points, or you have like circles and you have to calculate the area of union of circles, or there are a bunch of things there, like for example calculating whether a point lies within a polygon or not given the points or the edges of the polygon. Those kind of problems, they lie in the computational geometry field, which is again a very well studied field. It's not like there isn't material to study. That is, however, additional to the regular DSA that you see. So segment trees, Fenwick trees, computational geometry, even within string algorithms, there are certain algorithms which become important for competitive programming, but maybe not so important for DSA. For example, maybe being able to quickly implement KMP, that might or might not be very, very important for interviews, but that's decently important for a competitive programming setup. Being able to understand suffix arrays or suffix trees or suffix automata, that's definitely not important for interviews and DSA for interviews, but it is very, very important for competitive programming. I have a sheet here which I will share with all of you guys, which is the basic curriculum we had prepared back in 2010 for people who were preparing for ACM ICPC. We took a camp in 2010 in Amrita University, where we actually invited a lot of students and we took classes for them. This was the curriculum for those classes. So we had prepared some basic curriculum and we had taken people through that. The other thing that is also very important is that maths for competitive programming becomes wider in nature. For example, number theory itself gets fairly wide. You have to be aware of modulus arithmetic. You have to be aware of Fermat's theorem, Euler-Toscan theorem, Chinese remainder theorem. You have to be aware of like what kind of primality testing algorithm exists apart from the brute force square root of n1. Those also, I mean, when I share this curriculum with you, it is going to be a part of that. Very similarly, like probabilities and combinations, they are also important for competitive programming. Some of it is also important for interviews, but like just wider in nature. There is an entire field on game theory, especially like algorithms like game of NIM, etc., which are again like very important for competitive programming, but maybe not important if you are just preparing for interviews. So that is why I just highlighted that if you are doing competitive programming only for the sake of getting into an interview, then this is an overkill, because there's so many topics that you probably don't need to study. So I'll share this curriculum doc with you. That's the first starting point, which is you have concepts, you understand those concepts, and you solve very, very easy problems on those concepts. That's step number one. Step number two then is that then you start your practice. Now again, practice as well has to be structured. What I mean by structured, so you have to make sure that when you start your practice, you directly don't jump into very hard problems, but rather go step by step. For example, if you go on CodeChef, or if you go on CodeForces, on CodeChef you have a repository of problems where you'll find very easy problems, then easy problems, then medium, then hard. First start tackling very easy problems, then go to the easy problems, and then medium, and so forth. Very similarly, when you go to CodeForces, CodeForces has division 1, division 2. Instead of directly jumping to hard problems of division 1, you should first look at easy problems of division 2. Then go to the medium problem of division 2. Then go to the harder problem of division 1, and so forth. So there also you need to follow a pattern. You need to follow a ladder instead of directly jumping into solving hard problems and solving problems from random topics. Once you've done that, and this is, by the way, you have to understand that this is a long process. nobody has ever become good at competitive programming by just starting and then like getting good at it in a month or 2 months. Competitive programming, given again, it's a sport. Imagine if you're training for Olympics, you don't get really good at it in just a month or two. It takes a while. So competitive programming is at least a 1-year journey, if not more. It's actually usually several years, but at least a year, if not more. So you keep doing this on a regular basis. I remember when I was in college, a lot of days we would just sleep in the computer lab where we would be coding because we were practicing all this while, right? So there were hours and hours of practice. We would practice on average of 4 to 5 hours every day on competitive programming, and that's how we got really good at it. It takes a while. It takes a lot of practice. It takes a lot of hours. So that's the recipe. If I have to summarize the recipe again, first start with the concepts that are arranged in increasing order of difficulty. For example, you'll find the starting set of topics on interviewbit.com. You can go check it out. Then there are additional concepts for competitive programming. I'll share the syllabus sheet. You look at that as step 2. Once you've gone through the concept, then you start solving problems. Start with the very easy problems on platforms. 2 platforms to refer to if you're doing competitive programming is CodeChef and CodeForces. Those are 2 great platforms to refer to. Start solving problems of previous contests there, easy ones. Then slowly move on to medium problems. Once you are at the level where you are solving medium problems, then you can start competing as well. You can start competing in ongoing CodeForces contests, CodeChef contests, and so forth. So those are the number of steps. What are the things to keep in mind though while you're following those steps? Actually, 2 things that are very important for competitive programming is 1, coding accuracy, and 2 is coding speed. When I say coding speed, I don't mean typing speed, but rather the time it takes for you to get to a correct solution. So those things are important because usually in competitions, you'll be doing it in a timed setup. A contest would be 2 hours, 3 hours, and you'll need to solve maybe 4 or 5 problems in that 2 hours, 3 hours. That means you need to be really fast. So as you actually practice, make sure you also keep timing yourself, and then make sure your time to solve problems is getting better. The first aspect is being able to figure out solutions consistently. Second aspect is being able to continuously being able to code it the way you think it. If your approach is correct, then the second thing you should start evaluating yourself on whether I'm able to code them really well or not. So as you follow the steps that I had mentioned, make sure you also are timing yourself, make sure your coding accuracy is getting better, your coding speed is getting better. If you do those, then while this is a longer path, this might take a while, I guarantee you will get really good at competitive programming. It's not very hard to do so. There are fixed number of patterns to problem solving. You'll start seeing those patterns. So that's a very quick brief on how to get started. I have 3 years of experience in service-based company and have never done competitive programming. What should I focus on for better career growth? Now, again, just making it very clear again, competitive programming is not the thing to focus on for career growth. Data structures and algorithms are different than competitive programming. So to be able to actually get better at problem solving and better at data structures algorithm, you don't necessarily need to do competitive programming. In most of our college circuits, unfortunately, competitive programming is used interchangeably with data structures and algorithm. And it's a very common trend where students believe that if you have to get into, let's say, an Amazon or a good product company, the only way to do so is by doing competitive programming. That is not true. Companies care about your problem solving skills, your data structures and algorithm skills, where, as I just described, there are so many topics that are only specific to competitive programming. They're not specific to interviews or the company's definition of data structures and algorithms. So firstly, your career growth and competitive programming, 2 separate things. Your competitive programming skills are not going to help necessarily with career growth. They're good to have, they're great to have, They might increase your probability of getting better with data structures and algorithm, which in turn might lead to you clearing a few interviews. But that does not necessarily make you a better engineer. There are so many other things to an engineer. You would have seen that in your day-to-day work, for example, there are so many other things, right? Like you might require to learn a tech stack. So the learning of that is important. As your experience is 3 years plus now, then being able to understand how software is designed, which is low-level design, high-level design, those become important. Being able to having a very good rationale around like what tech stack or what technology to choose versus not to choose and why that decision is being made. That is very important. Competitive programming, not so much important for career growth. Do it because you like it. Question is, I'm currently working as a cloud support associate in Amazon. Is it possible to transition into an SDE role? What is the path for me? So in general, I mean, I don't know whether it is possible within Amazon or not, because that is dictated by the internal policies within Amazon, which I am not the best person to comment on. That being said, going from any job vertical to another job vertical is always possible. That just means that you need to understand what are the things required for that job vertical, and then how do I build those. For example, if you want to transition into an SDE role, following are the things that I would advise. One is build a project on the side. Some project, there's some idea that you have in your mind, try to implement that using a tech stack. That would get you to learn at least one tech stack really well. And then put the code base on GitHub, host the project on a Heroku app or AWS, so that any interviewer can also go and check it out, what you've built. That gives you one edge. The second thing is then you need to get really, really good at data structures algorithm, basic low-level design, CS fundamentals, which is basics of operating system, networking, and databases. Study that as well. And once you have done that, then sure, I mean, any transition is feasible. I have personally seen a lot of those kind of transitions happen into SD roles. Question, which is, I've joined Scalar Academy. Will that be helpful for me to be good at competitive programming? But what else should I do apart from that? So Vinay, as I mentioned, like data structures and algorithms, that's the piece that is covered within Scalar Academy, which is great if you are like, if you're seeing that from the lens of your career and interviews, etc. But there are additional topics, as I had just mentioned. For example, computational geometry, Fenwick trees, segment trees is covered as part of Scalar, but let's say certain advanced concepts around probability, combinations, so certain other things in number theory that would not have been covered in Scalar Academy, which you'll have to study on your own. And you'll see like there are a bunch of other topics for competitive programming. That is, however, still the step 2. The first step is learning the DSA piece. If you don't know that, please go and learn that first. Don't directly jump into the advanced concepts, while it might be very, very tempting. All right, okay. So there's a theme of problems or like questions where questions are structured around, I am from a different background, be it a cloud support associate, be it a sales background. I mean, cloud support associate is still a little closer to engineering, but different background, which might not involve writing code on a daily basis. But then how do I switch to becoming a developer, software developer? I would say like the following are the steps for that, right? One is evaluate whether you really, really want to do software engineering or not, which means start learning coding on your own, see whether you like it or not. If you figure out that you like it, then following are the steps. Step number 1, pick up any tech stack. And I mean, the easiest ones usually are Python, Django, with maybe just vanilla JavaScript or a React.js. So pick up a tech stack, try building some project using that. Like again, like think of some problem statement that you see around yourself. Maybe there is a problem in your society. There's some things that are people are not being able to manage. Can you build a web application for that? Build that, and as I said, like host it publicly on AWS so that other people can also use it. Other people can see your code base as well, so they know what kind of code do you write, what kind of projects have you built. Then you start learning data structures algorithm, then you start learning low-level design, and then you start interviewing. If you know the right things, it's very important to understand. Tech is a area where degrees don't matter a lot. If you know the right things, if you're skilled, if you can get the job done, then yes, obviously transitions are possible. Knowing the right thing and being able to get the job done, that is the prerequisite, and that is the harder part, to be honest. So as long as you have a learning path to do that, sure, all kind of transitions are possible. I already earn a 6-figure salary, but a non-tech role. If I decide to switch to software developer role now, will I get the same salary, or do I need to start from the beginning? There is no guarantee that wherever you switch, you will get the same salary. It's every company has their own salary bands. Right? For example, for an SD1, an Amazon would have a band, a range, X to Y. Let's say, hypothetically, 17 to 24 lakhs. Right? So no matter what background you come from, if you get hired as an SD1 at Amazon, that's the salary that you get paid. Since your background is not relevant, since your experience is not relevant, then the probability that your previous salary gets accounted for and then you get a hike on top of that, that's very, very low. You have to always understand that when you switch to a different field, you're resetting more or less. You're starting unless like you've had relevant experience in some form or the other, you're starting as a fresher, more or less, in the new field. Look at it from that lens. If you want to build, your career is 40-year long journey. If you want to build a long-term career in a software engineering field, sure, you could look at doing that, understand whether you like it or not, and whether you want to build your career in that or not. I started data structures and algorithm few days ago. After completing any topic, should I solve practice problems only, or with it I must do competitive programming? Do not do competitive programming right now. First, just solve practice problems. It is one of the most common patterns that I've seen in Amica is that people start with competitive programming. They see that they are not able to solve problem. And there is a reason for that, right? Like the reason is that most problems you'll see are not just from one topic, but they're a combination of multiple topics. So you then are not able to solve the problem, and then you feel bad about yourself, and then you end up giving up after 2 or 3 of those iterations. It's important to avoid that distraction in the beginning when you're learning the topic, right? For example, imagine today I decide that I want to become a cricketer. I want to become a world-class cricketer. And today is the first day that I start to hold the bat and maybe just start to play a few shots. If somebody puts me in the arena where, let's say, an IPL match is happening, I would obviously fail miserably. And that would demotivate me. So better not to put yourself in the IPL arena right now. Maybe just build those skills and then you apply those skills. The phases, build and apply, build and apply. What to do after DSA? So once you've gone through the topics of DSA and Amica, there are these additional topics which are specific to CP, competitive programming, which are specific to that. What you can do is you can start learning those in parallel while you start doing some practice. I'm from PHP background of 6 years. Should I learn Java or Python for DSA and system design? If the goal, I'm sure, is that you want to get into a product company, and therefore, the answer differs based on whether you want to go to a product company or grow within a service company. Most product companies don't care very heavily about your current tech stack. What they care about is your ability to learn any new tech stack if required. So therefore, your interviews would probably focus on data structures, algorithm, and system design. Not very heavy focus on what current tech stack are you using. So they are tech agnostic that way. And then when you join the job, you'll figure out internally, maybe the internal text is very, very different from what you've seen externally. For example, Goldman Sachs has their own version of Java. Or for example, when I got into my first job, my first team was working on Java, the other team was working on Python. I had another team that was working on PHP at Facebook. So I had to work across 3-4 different tech stack. And as the need arose, I learned it, and then I started delivering that. So don't be limited by the tech stack that you have today. As long as you're comfortable learning a new one, then I would say just focus on DSA and system design, and you should be golden. So I have 6 years of experience in software industry. I have an SD2 position and planning to explore jobs in USA. Please suggest me what are the best paths. Someone suggested me to prepare for GRE exam. It will help. I've done a session on, by the way, whether to do masters from US or not. You should go and watch that video because that is very relevant in this case. That being said, just a very quick answer. H1B mostly directly to the US is not possible. H1B visa is not feasible. There is very, very low probability of getting that. So there are two reasonable paths to get and work in US if you are really, really keen on doing that. India's ecosystem is, by the way, evolving at a similar pace. It is in no way inferior to what is happening in the US. But that being said, if you really want to explore, there are two paths. Path number one is you get into a product company, which has presence in US as well. So, for example, an Amazon or a Microsoft or an Adobe, or there are a bunch of other companies. And internally, those companies might have rules of shifting people who are SD2 or above. And most of those companies are okay doing that. That is path number one. Path number two is that you actually prepare and do an masters from the US. In such a case, you get a visa that lets you work in the US for a year or two, and then post that you have to apply for an H1B. Those are the two most commonly explored paths. I'm a front-end developer with 6+ years of experience, no good experience in developing scalable backend systems, trying to switch to Fang. Could you please advise, should my focus be front-end only? Absolutely. All of Fangs, they also hire front-end engineers, so your focus should be front-end only. That being said, even for front-end engineers, high level of problem-solving skill is still desired. So DSA, you should be really good in DSA, even if you're a front-end engineer. And the design part changes slightly, which means when we talk about system design and high-level design, there the focus for front-end engineers isn't necessarily how would the systems work in the back-end, but rather front-end architecture. Now, what is front-end architecture? Web architecture or front-end architecture is where you really, really understand when you type google.com, then what really happens, what kind of request goes to, how are DOMs rendered on browser, what are the kind of optimizations that you can do. Those things you understand extremely well. What kind of optimizations can you do in a given scenario? For example, let's say if I'm building a type ahead, right? I start typing characters and then Google starts showing me search results. Then what kind of delay factor to add there post the key press so that my backend systems are not bombarded with requests. Those kind of things are part of front-end architecture, right? So those are still important. Low-level design, which is like how do you use object-oriented programming principles to be able to design code the right way, that is still important for a front-end developer. So back-end system design, not really important, but the front-end system design and low-level design, those are very important. According to you, how much time is required for a beginner to learn BSA from scratch to a level where one can easily crack coding interviews? If you start from scratch, and I would love to understand what is the definition of scratch. If the definition of scratch is that you already know how to code, which is you understand a few programming languages, you can write code, you understand how coding works, a particular programming language works, right? What are variables? How do they work? Does memory get allocated, etc.? Like if you understand that, let's say that piece is sorted. Then if you follow up a very, very solid regime, getting good with DSA probably would take you, and assuming you devote enough number of hours, probably will take you about 4 or 5 months, and you should be good with that. It is, however, we still in those 4 or 5 months, you have to follow a regular schedule, a proper structure, make sure you solve enough problems. You're solving daily and 2-3 problems, if not more, then you should be good. If you're starting from scratch. How to revise data structures and algorithm stuff efficiently if we are also working in a company. If you already know the concepts, if it is just about revision, then what I would say is, as I told you in the beginning, interview bit has a bunch of topics. while like that website has a fairly filtered set of problems, I would say like per topic, just maybe pick 2-3 problems and solve that. There are about 12-13 topics in total. If you pick 2-3 from every, then you get probably 26 to 30 problems. That is probably around a 30 to 40 hours of time commitment, which if done over a month is basically 1 hour of time commitment every day. That is what I would suggest if you were just quickly revising stuff. I just joined service company 3 months ago and I want to switch to product companies within a year. How should I prepare to make this switch? Right. So you need to be good with data structures algorithms. So start practicing that. I gave one reference website. The second piece is maybe focus a little bit on low-level design. High-level design is probably at your experience range not so important. So maybe a little bit of low-level design, object-oriented programming-based design. And if you can build a project on the side, or if your current work doesn't have very, very exciting work, then if your current work is awesome, then great. Don't need to build anything on the side. If you can build that, that is an added advantage. And if that happens, I mean, sure, I mean, the switch isn't very, very hard. Do lead code stars matter? And if yes, how to earn them? So I'm assuming the question is, do they matter in context of an interview? So lead code stars or Codeforces rating or CodeChef rating, they will help you maybe get an interview. What I mean by that is, imagine I am Amazon, or imagine I'm just Scalar, right? When there is a job opening, there are a lot of applications that we get. Now, how do we differentiate between those applications? We might look at college. We might look at your profiles at various websites. We might look at your projects that you've done. Now, your profiles on websites, for example, the number of stars you have on lead code, or your rating on Codeforces, or your rating on CodeChef, those would help you stand out against everybody else. That is not the only way to stand out, but they are one way of standing out. And therefore, that increases your probability of getting an interview. However, it is important to note that once you've gotten the interview, your interview performance and the judgment of how you did in the interview, etc., has nothing to do with your lead code stars or your CodeChef stars or Codeforces stars. It is just like in the interview, how do you do? That's all that matters. So to answer your question, Shashwat, it might help you in maybe getting noticed by certain companies when you apply to them. And on how to earn lead code stars, I mean, that probably I'm not the best person to answer. I haven't been practicing heavily on lead code yet, so I don't know what's their criteria of awarding stars. In Codeforces or CodeChef, for example, you compete in competitions. And as you compete in competitions, your rating goes up and down. Okay, there is a Scalar specific question, which is any future plans of Scalar in the domain of ML and AI? As a matter of fact, there is something to look forward to. We'll probably an announcement in a few days, and we'll launch the first batch that will start in the month of September. Sir, logic ही नहीं बनते, कोडिंग क्वेश्चन सॉल्व ही नहीं होते, बैठे सोचते रहते हैं, लास्ट में हर बारी सॉल्यूशन ही देखना पड़ता है. Which is a rough translation is that it is very hard to get to logic. And usually what I end up doing is that I end up looking at the solution and what should I do? This is exactly what I have heard from a lot of other students. And the core reason there I have seen people jump to practice way too early. So the first thing, Jatinder, is if you can start with basic topics and basic problems on those topics. That's the step number one. If you can't skip that step, if you skip that step, then it will become really, really hard to catch on to logics. Because, I mean, if you look at yourself, like you not only have to understand a new topic, but you also have to come up with the logic for a new question using that topic. Something that you haven't studied in the past. That is a much, much harder job. So therefore, step one is start looking at each topic one by one. For example, I'm just posting a link which has all topics in increasing order of difficulty. What I would advise is that go through those topics one by one, solve the easy problems there or for those topics. And you'll find that once you know the topic, then there's so much of content even on YouTube for those topics. So I mean, once you know what you have to learn, then you'll find content. But go in that order. Learn those topics, solve easy problem, and then the step 2 comes where you start practicing. But you can't skip the step 1. If you skip the step 1, then this is exactly the kind of problem you'll get stuck in. So I've completed BCA and I can code in C, C++, and Java, and I have solved practice problems on Geeks with Geeks. Should I start with competitive programming and apply for a job or pursue masters? Okay, competitive programming definition wise isn't linked to a job. As I said, like competitive programming is if you want to, let's say, compete in the ICPCs of the world or code forces of the world, that's when you start with competitive programming. So one, I mean, that is not linked to a job. DSA is linked to a job. Data structures and algorithms is linked to a job, and that you should definitely learn irrespective, right? Because even after you go and do a master's, even post that, you'll set for a placement season if you ever intend to do a job, and for that, then DSA becomes important. So why delay that? Why not start learning it today? So learn data structures and algorithm, practice more coding, and then I mean take a call, right? It's very important to understand why you want to do masters. If you want to do masters because you want to go do research on certain topics that you're really excited about, sure, then do masters. But if the purpose of doing masters is to get to a better job, then why take that long path? Why not learn the right things on your own time and then apply to the right jobs? Is it a myth or reality that do not learn DSA in Python because many companies don't include Python in the coding interviews? That's a myth. That's not true. Look, I mean, certain companies would have, and these are very few companies that have preference for a tech stack, which means, for example, let's say there is a bank. The bank might say that all of my code is in Java, so I want to look at people who can code in Java. And in that case, they would not even look at people who code in C++ or C or Python. So there is nothing wrong with Python. There's sometimes, however, concerns are raised because Python is a slow language. It is not as fast as C++ or Java. C or C++ being fastest, Java being slightly slower, Python being kind of slow. So in some cases, if you're doing competitive programming, you'll find that a lot of times Python solutions, for some reason, they start to time out. Whereas like the same solution, let's say in C++, that works. Happens in very, very rare cases, very rare cases. But that might be one of the reasons why some people say that maybe don't learn DSA in Python. But there is nothing wrong. I'll tell you right now. I have been an interviewer at Facebook. I have interviewed more than 500 people there. There is nothing wrong in using Python. Python is a perfectly good language. I had learned the collection framework and I had started with Codeforce's Div 3. People say that you don't need DSA in 800, 900 problems. But when I had given contests, I was not able to solve any of the problems. Again, you skip the step 1, as I said. Don't listen to people. Don't go and solve Div 3 problems just because you've learned the collection framework. Go step by step. Step 1 in my formulation was, I think you've done the step 0, which was learning Java and then learning the collection framework, which is good. Now do the step 1, which is I've posted the link, go through the topics one by one, solve easy problems there. Then look at other things. Firstly, like getting that is important. That also gives you, by the way, a lot of practice on topics as you are learning them. Is lead code enough to clear the online coding rounds of companies? I'm getting stuck in online rounds only. Yes. I mean, so lead code in the structured setup where you, for example, if I have never touched dynamic programming because I feel that's very advanced, while lead code has a bunch of problems on dynamic programming, that is not going to help, right? Because all topics are important. So as long as you've gone through all topics, as long as you have studied or solved questions from every topic, going through lead code is enough. Yes. Again, don't however, I mean, practice lead code in the framework that I have these problems and I know the solution to these problems. That's not the right framework. You don't want to memorize solution in any form. Lead code or any platform where you practice, the primary purpose is to help you start recognizing patterns of problem solving. For example, when you see a problem, then you can start to see whether you can apply a binary search here, or maybe I should use a hash map here. Those kind of thoughts, they start coming to your mind. So I got a front-end job from Institute, but I didn't know DSA. Now I want to learn DSA, but I'm not finding the right path to do it due to limited amount of time. What can I do? You'll always be short on time, Shashwat. The only way to do that is that you start be a little more disciplined. And I'll tell you, like, at least what has worked for me. What I would do is whenever I want to start a new activity, I block a time on my calendar. Usually all of my meetings, all of what I do is on the calendar. So I block a time, for example, 8 p.m. to 9 p.m. And in that time, I do nothing else except for what I have planned. As long as you do that, just like, if you wanted to start going to gym, you would extract out 1 hour, 2 hours for that. If you extract that out and then you start repeating that, you make it a habit, then things will get easier for you, right? And in that time slot, there you start with learning and solving whatever you can in that time slot. That's fine. So the process will be slow, but you'll eventually get there. And I'm going to pick questions on the common themes. For example, one of the most common theme is, I am in some XYZ job and I want to get into a great product company. What kind of level of coding problem should I learn? Again, as I stated, competitive programming is not required in such a case. If you can learn the topics in a structured format, and therefore I posted the link to interview bit, because at least there is some structure there on what topics to do first, what topics to do later on. For example, you don't need to go to the graphs or dynamic programming before you've done recursion, or you've studied like what sorting algorithms, what searching algorithms exist out there. So go in a order, and there at least start solving easy, medium problems one by one. In some cases, you will struggle. Initially, in fact, when you start solving problems, you'll find that solving problem takes me a few hours, and you'll feel really bad about yourself. That's okay. It happens with every single person. Initially, it takes you time to solve problems. Initially, you make a lot of mistakes. Initially, your code has a lot of bugs. And even if you knew the approach, maybe getting to the right code took you 1.5 hours or 2 hours. That's fine. Happens with every single person. But everybody has to go through that to finally get to a state where getting or writing code becomes a breeze. So go through that phase. Don't get demotivated during that phase. And once you've gone through that, once you've solved a bunch of problems, you will be able to get into Amazon. Interviewbit.com is the roadmap. If you study them, if you solve those problems, you would have learned all techniques. That isn't to say that you'll get the same problems in the interview, but you'll have learned all the techniques. There is another question, which is, would you recommend, and this is another theme of a question, which is around what programming language to take. JavaScript is perfectly fine. But again, like if you're using JavaScript, then my assumption is that you are a front-end engineer. But yes, if you are solving DSA problems, you don't need to go and learn a different language just for the sake of DSA. It is perfectly okay to practice it in JavaScript, or if you know Python, then Python. If you know Java, then Java. If you know C#, then C#. You don't need to learn a new programming language just for the sake of DSA. The questions which are around how to stay motivated. How to stay motivated for a elongated period of time. There are 2-3 tricks that I see working. There are 2 or 3 things that I've seen work. One is, if you can find companions like yourself, right? For example, why do people do well in classes or in colleges? Because if you have people like you who also want to do the same thing, then you push each other. Some days I don't feel up for it. My friend will push me. And there is some sense of progress, right? Because when I overtake my friend in doing something versus they overtake me, then there is this thing that I have to look up to. There is a sense of progress. I'm making progress. So that's one thing that I've seen work, which is if you can find a peer who can practice with you, that's usually a great motivator. There is always something or the other happening that helps you stay motivated. You're not just doing it in the silo. If you notice, most social media platforms have a lot of activity. For example, people post about their food and everything on social media because that gives them validation. This is one form of validation. The second thing is that be able to, so what you can do is, and this is another form of motivation, is like if, for example, your end goal is getting into a job at Amazon, you'll find that on interview bit, on lead code, there are problems tagged as Amazon. List out those problems in topic wise, in the order of difficulty. As you practice, you'll start to see that the easiest problems, at least if you've ordered them by topics and difficulty, you're slowly and slowly able to solve those kind of problems. When you do that, that also gives you a sense of progress, and that also again then motivates you. In my case, however, one of the, again, as I said, like I was very fortunate to have very, very good teammates who were there with me, and they were the ones who motivated me a lot. I always had something or the other to discuss with them, some or the other problem statement to discuss with them. If I was stuck, they would push me. If they were stuck, I would push them. That worked a lot for me. But again, like all humans crave for some sense of progress. I want to see that I am getting better from where I was yesterday. So all of these hacks are just way of being able to measure progress with yourself. Peer community, comparing your progress against theirs, or having these problems that you were not able to solve before, but you're able to solve now. Those 2-3 things help you stay motivated. With that, I'll end the session here. Thank you so much for joining.